I wish you a Merry Christmas. I wish you a Merry Christmas and a Happy New Year. So, guys, so here is your Santa, right? So, welcome to Vedantu J English, all the aspirants out there. And do let me know in the chat box what is the wish, what is the gift that you want from your Santa, right? And this beard is oof, very suffocating. Right, so I'll just remove that. Yes, so everyone, Merry Christmas to all of you. And as tomorrow you have another marathon, so I'll not be taking your class. So let's celebrate Merry Christmas today. And today we will celebrate it with inorganic chemistry. And what is the other gift that you want, right, from your Santa, right? Yes. What is the gift that you want from your Santa? Everybody, let's see in the chat box. And organic chemistry one shot. Okay, let's see. Do you want me to take organic chemistry in one shot? Do you want me to take physical chemistry in one shot? What do you want from your this Santa? Right? I'll definitely do that. Yes, ma'am, chapter order will be what that I'll tell you, ma'am. Santa mechanisms tomorrow. Okay, tomorrow to nahi, but I'll definitely do the mechanisms. Don't worry about that, right? In full inorganic organic one shot, I'll think about it, but I want to see that how many of you are willing to do that, right? Yes, everybody out there. Yes, with questions, organic chemistry, physical chemistry, neat seat, J seat, awesome, whole chemistry in one shot. Okay, we'll do that, don't worry. Your Santa is going to do everything, right? Your Santa is going to grant all of your wishes, right? Firstly, your Santa, let the Santa wears the specs, right? Oof, because your Santa is little defected piece. Your Diksha ma'am is little, from eyes I am little defected piece, right? So yes, so guys, today it took me a lot of time to actually it took a lot of time. A lot of time means you will see the PPT and you will yourself feel that what all I have done for you, right? So you can see this over here. This is how many slides? This is around 340 slides. So I am not joking when I am saying that I'll be taking full inorganic chemistry, right? And how long will be the session? So session is going to be, guys, like maybe 10 p.m 11 p.m. It is going to take like that, along with the breaks as well, right? Okay, now if you see this over here, right, what is going to be the order of today's class? Firstly, I'll do chemical bonding, then coordination chemistry, then DNF block, then I'll do then P block, then DNF block. That is going to be the order here, right? Okay, so all the, yeah, these, this beard was not good quality, I must say, right? So all we are going to do is full inorganic chemistry today, right? But I want your dedication till the end of the lecture. Do you promise me you will stay here till the end of the lecture? Ma'am, is it from basic beta? Ha, you know nothing about inorganic. Now you will be able to do this. Okay, I am not going to give you a question answer, no, right? Chemistry, I know there are so many students out there who are thinking that I want to skip inorganic chemistry. I will not let you skip anything here, right? All the important things, actually important, most of the things I have covered, right? Only those things I have skipped that they have never asked. You can imagine that I have also covered dipole moment, bond angle, everything I have covered here, right? Okay, yes, everybody, it is from the scratch. It is, yes, it is from the scratch. Now everybody fill the chat box with the green hearts. If you promise me you will not even skip one single minute, I will give you break. First I'll give you 2-3 breaks here. From 3 we have started, so I'm thinking to give you break around 5 to 5:30. Like I want to complete chemical bonding. I'm thinking that chemical bonding and coordination chemistry, if we can complete. Otherwise, I'm thinking that I'll give you break after completion of one chapter. Like chemical bonding, let's complete it by 5 p.m. Then take a break of 10 minutes. After that, coordination chemistry by 7 p.m. Then take a break for 15 minutes or maybe half an hour for your lunch, for your dinner. And after that, I'll start with block chemistry, right? Okay, right, everybody? Yes. Arey, video got stuck. Arey, bhai sahab, what is happening with you? Wait a minute. Yes. Okay. Right? Done, 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 done. Yes, yes, it's done. It's done. Oh, such a long time it got stuck, huh? For how long I was stuck? Uh-uh. I just realized I was stuck. Do you want me to wear this cap throughout the session? Or do you want to see normal, ma'am? No, you can stay normal. Yeah, now okay, right? Okay? Yes. Chalo, let's start with chemical bonding. First thing is chemical bonding. Let's start with that. Let's start with chemical bonding. I'll do just one thing here. Because I don't want that in between the session also it gets stuck and then your ma'am also doesn't know that it is stuck, right? Then that will be a problem. Yes, I think now it's perfect. I think now I can also see your chats as well. Okay, perfect. P block, D block. Okay, I'll just write it here. See, we'll do chemical bonding, right? We'll do P block, we'll do D block, we'll do coordination chemistry, we'll do periodic classification. I know it is very difficult to digest that I'll do everything in one day, but we are going to do that, right? Okay, no more. Yes, P block also I'll cover, right? Okay, yes. Chalo. Let's start with that. Let's start with chemical bonding. Let's start with chemical bonding, everybody. So in chemical bonding, what you have? Tell me. In chemical bonding, what you have? In chemical bonding, what all we are going to discuss is some important things here. First is VSEPR, hybridization, and its shape, geometry. How do you calculate? Then in this, we are going to discuss MOT, molecular orbital theory. In this, we will discuss the bond order. We will discuss some important tricks here to find that out. Then this is all along with the previous year questions, okay? So then the third one is, you can see VSEPR, hybridization, MOT, this, and after this you have dipole moment, right? From here, these are top hot topics, and from dipole moment or hydrogen bonding or bond angle, they can ask you one question, right? From this, so definitely they will ask you one question, and this is also very high probability. From dipole moment, H bond or bond angle, one of them they can pick and ask you the question. Okay, so we'll do according to that, right? Let's see. Let's start with the question. So what you have, let's start with the hybridization part. So in the hybridization part, right, first thing, beta, how I am teaching you now, just look at that, right? Now your whole focus should be that you should not be like moving here and there. Your mind should not be distracted while you are in the class. Please, it's a request. Don't distract your mind in the class. Don't, when I am doing hybridization, I am teaching you something, focus on that thing. Don't go here and there, right? You will end up wasting your time. Utilize the full like hours that I'm giving you here. Utilize it properly. You don't have much time. Let's utilize every single minute here. So that's why I want to see in the chat box what I am writing here. According to that, if you have any problem what I'm writing here, what I'm teaching you, ask that question. When I'm asking you any question, answer that. Don't move here and there. Don't chit chat in the chat box. Okay, that's my advice to you. Rest is totally your choice. Now see, how do we do a hybridization? We'll understand the application part of that. Now in hybridization, what exactly you do? Intermixing of orbital to generate new orbitals. Like here you have S and P orbital, they intermix to form two sp orbital. One s and 2p orbitals intermix to generate 3 sp2 orbitals, right? One s and 3p generate 4 sp3 orbitals. That means the number of hybrid orbitals getting intermixed is equal to uh, the hybrid orbitals that you are forming. If you're let's say adding s and p, that will be sp. If you're adding s and 2p, that will be sp2. If you're adding s and 3p, that will be sp3. If you're adding s and 3p plus d, that is going to be sp3d. If you're adding s and 3p plus d2, that is going to be sp3d2, right? That is the definition of hybridization that you have. But they don't ask you questions from definitions, right? They will not ask you that kind of what is hybridization, that they will not ask you. You should have an idea about it. So what questions they ask you? First thing is you should know how to calculate the steric number. Once that also I'll teach you how to calculate the steric number with the help of questions only. I'll teach you that, right? Now, if your steric number is 2, it is sp hybridization. If it is 3, it is sp2 hybridization. If it is 4, it is sp3 hybridization. If it is 5, it is sp3d hybridization. If it is 6, then it is sp3d2. How you can remember it? 2, 3, 4, 5, 6, sp, then add 1 p, sp2, add 1 more p, sp3, add d, sp3d, add 1 more d, sp3d2. That is going to be your hybridization corresponding to the steric number that you have, right? Now, corresponding to the hybridization, you will have the geometry, right? Geometry of sp is linear, right? Linear shape means this kind of geometry. This is a linear geometry, right? That is having 180-degree angles. That is linear geometry. I am writing it over here. It has 180-degree angles here, right? Trigonal planar. Can you tell me how does a trigonal planar geometry look like, right? So I'll just tell you that. Wait a minute. I forgot to make this one shape here, right? Rest of it I have done, but one shape I forgot to make, right? Just give me a second. Yes, this one. Wait a minute. Yes. So this is how a trigonal planar geometry looks like. See? Okay? Yes. Now, if you see this here, can you see this over here? Beta, है ना? ऐसे तो you will make me very angry in the starting of the session. Ma'am, you have skipped hybridization. अच्छा, tell me in which PYQ they have asked you that what is hybridization. This is hybridization only what I am teaching you. ठीक है? You calculate the steric number, from that you tell the hybridization. Right? Okay? Right? So please have some patience. ठीक है? ऐसे तो you won't be able to understand anything, right? You sit here, you cry, do whatever, right? In the starting of the session, this and that we want to say, right? We don't know anything, but we will just say, ma'am. Don't have faith, you can go. You don't have faith, go from the lecture, watch someone else's lecture. Doesn't matter, right? Okay, those who have faith, understand it properly, right? I'll just start from the beginning. As you know, these kind of kids irritate you a lot, right? Okay, chalo. See, what is hybridization? It is intermixing of orbitals. You have s orbital, you have p orbital, you have d orbital, you intermix them and you make a new orbital here. For example, you intermix s and p orbital, you make sp. You intermix s and 2p orbitals, it is sp2, then sp3, sp3d, sp3d2. For this chapter, we need only these hybridizations. We don't need any other hybridization. One more hybridization that you can write here that can be useful for you, that is 7, that is sp3d3, and for that you have pentagonal bipyramidal. Pentagonal bipyramidal. Okay, these are the only hybridization. Those who are saying, ma'am, what about dsp2, ma'am? Ma'am, what about sp? Ma'am, what about d2sp3, ma'am? What about these hybridization? These we will discuss in coordination chemistry. It has no use in this chemical bonding. So let's focus on these hybridizations only, right? Okay. no, PDF I'll provide you, okay? ठीक है जी? But a square, planar and all, we will not discuss it here, right? We'll discuss only these hybridizations. That is a part of chemical bonding, right? Okay, understood? Understood everybody? Right? Now, let's see this over here. Once you have this, acha, if you talk about 2, that belongs to sp3, sp2, 4 sp3, 5 sp3d, 6 sp3d2, 7 sp3d3. Corresponding to you have your shapes. Let's say I talk about linear. Now see how we do the shapes, okay? Now let's see how we do the shapes. So if I talk about sp hybridization, that is going to be a linear structure like this, having 180-degree angles here, right? If I talk about trigonal planar structure, it is going to be this. It looks like a triangle. If you see, it is making a triangle here, and it has 360 divided by 3 is 120 now. So it is having 120-degree angles here, right? So you can just write it over here that this has 180-degree angles. This has 120-degree angle, that is trigonal planar, because it is in one plane. That is why it is called as trigonal planar. Now let's talk about the third one, that is if you have 4, that is sp3, that corresponds to tetrahedral shape. So tetrahedral geometry means what? You have this kind of geometry where this is the tetrahedron, and you rotate it, all the angles will be same. This is a tetrahedron. If you see, this is a tetrahedron. This is how it looks like, okay? This is how it looks like. Now it has an angle of 10, what angle it has? 109-degree angle it has. 109-degree angle, 24 minutes is the angle here. Trigonal bipyramidal shape is what? This is trigonal bipyramidal. See, what was trigonal planar? This was trigonal planar. Now in this case, on the upper side you have one bond, on the lower side you have one bond, making 2 pyramids. This is first pyramid, this one is the second pyramid. So that is trigonal bipyramidal, right? Okay. Now next is octahedral. What do you mean by octahedral? This is how octahedral looks like. In octahedral, what you have a square here, right? And here you have one bond, and here also you have at 90-degree another bond. Why it is called as octahedral? Because it has 8 phases. This is first phase, this is second phase, this is third phase, this is fourth phase, and similarly below also you have 4 phases. That is total 8 phases. That's why it is called as octahedral, right? Then the last one is pentagonal bipyramidal shape. So I don't have any atom which has 7 ways to form it, right? That means I don't have any atom that has 7 holes, so that's why I won't be able to do that. But I can teach you that how it will look like. Just like here you have trigonal bipyramidal, now here you have a triangle, right? Then you have a bipyramidal above and below. Similarly, just imagine this is a pentagon, okay? Just imagine here you have 5 atoms, that is a pentagon. So in pentagon, above and below you have atoms, right? That is pentagon bipyramidal. Very rare case that they will ask you pentagon bipyramidal. Mostly are these cases that they ask you 2, 3, 4, 5. Now each example will see how to do that, right? Everybody tell me. Let's do, right? Okay. Let's do this, everybody. Let's do this. Let's do this, right? So steric factor you have here, steric factor you have here. Very simple. Let's understand that. To predict hybridization, following formula to be used. What is the formula? Now I told you this is the steric number. But ma'am, how do I calculate the steric number? Who will tell me steric number is 2 or 3? If you know steric number, you can know the hybridization, you can know the geometry. But who will tell you what is the steric number? For that, this is the formula that you are going to use. The formula is you have half of total number of valence electron in the central metal atom, right? For example, I am calculating the steric number of NH3 lone pair here, okay? Or you can say, chalo, let's calculate NH3 lone pair, right? Let's calculate the steric number here. Steric number is defined by Z, that will be half of, I'll just calculate this here only, so that we can calculate for some other compound as well. This will be half of, this is total number of valence electron in the central metal atom. Now, those who have confusion in that thing, ma'am, but how do I define that? What is the valence electron here? Right? Let's understand how to understand the valence electrons. How to tell that these are the valence electrons. Let's understand that. Okay? Let's understand the valence electrons. So, let's just see very simple thing I'll tell you here. If you talk about the valence number, right, valence, so if you talk about, let's say you have lithium beryllium, you can say, okay, let's say lithium beryllium boron carbon nitrogen oxygen fluorine neon. Okay, so now here what will happen? Lithium, it belongs to group number 1, its valency, it will lose 1 electron, it will be 1. Beryllium, it will be 2. Boron, it will be 3. It will, then this will be, for carbon it is 4, for nitrogen it is 5, for oxygen it is 6, for fluorine it is 7, for neon it is 8, right? Usually neon you will not have. So basically, how do you remember this? From here you can remember this is group number 13, this is group number 14, this is group number 15, this is group number 16, this is group number 17, and this is group number 18, right? So group number 1, 2, this is group number 1 and this is group number 2. Just remember the valencies here, because that is going to be very important while solving the hybridization. And this is a sure short question. I can guarantee you, right, that question will be there. This question based on asking the hybridization and the shape will be there in your exam, will be there. So be prepared for that, right? And very predictable shape will be there, right? So all what I'm going to tell you today, that they will ask you, right? So now if you have group number 1, it is 1 valency, 2 is 2. Any element that belongs to group number 13 will have valency 3, and 14 will have 4, 15 will have 5, 16 will have 6, 17 will have 7, 18 will have 8. So what they are asking you, they are asking a total number of valence electron in the central metal atom. So valence electron in case of nitrogen will be what? As I told you, valence electrons, right? These are the valence electrons. Acha, can you tell me what is the difference in valence electrons and valency? Can you tell me the difference in valence electrons and valency? See, valence electrons, when I talk about valence electrons, I talk about in the outermost shell how many electrons it has. And you will use the valence electrons while calculating this. You will not use the valency here. Valency simply means that lithium wants to gain wants to lose 1 electron. This wants to lose 2 electrons. This wants to lose 3 electrons. This wants to share 1 electron. This wants to gain 3 electrons. This wants to gain 2 electrons. This wants to gain 1 electron. This does not want to. Valency is number of electrons it wants to gain or lose to complete its octet. That is called as valency. But we will only talk about valence electron. In this case, in the formula, we are putting the valence electrons. So just remember that thing. Now, let's see if you can answer this or not. Nitrogen belongs to group number 15. 15 means 5 electrons, so put it 5. Put it 5, right? Total number of monovalent atom. Monovalent atom, you have how many? You have 3 monovalent atom, right? Minus charge on cation plus charge on anion, right? See, a lone pair is regarded as charge only, right? So if you talk about the lone pair, see, lone pair will be added here plus charge on anion. So you have how many electrons? You have 2 electrons here. So what you will do here, 5, 6, 7, 8, right? 3 electrons, so we have done now. Lone pairs, so we will not add, because there is no point of adding that, right? So it will be 5, 6, 7, 8. 8 by 2 is 4. That is nothing but sp2, sp3. This is one of the way of calculating. Another way is just add sigma plus lone pair. Sigma plus lone pair, that is Z. So sigma plus lone pair, you can also add that sigma plus lone pair, that is nothing but sigma is 3 sigma, and you have one lone pair, so that will be 4, that is nothing but sp3. So for hybridization you have two ways of calculating, right? Either you can calculate it from the formula or you can calculate it directly. Now one more question I will ask you for that. Okay, so can you tell me the hybridization, can you calculate the steric factor of, let's say, bf3? What about bf3? What is the steric factor of bf3? So if I directly calculate from z, z is equals to sigma plus lone pair. Boron does not have any lone pair here, right? So it is going to be sigma plus lone pair. Sigma is what? Sigma is 3 and lone pair is 0, so it is overall going to be 3. 3 means it is going to be sp2 hybridization, right? Now see this over here. If I talk about boron here, right? Boron, in case of this formula, that is half of total number of valence electron in center. Boron belongs to group number 13, that means 3 valence electron, right? And here total number of monovalent. Fluorine is a monovalent atom. It has valency 1, as you can see. It is monovalent atom. Its valency is 1. Hydrogen is monovalent. Group number 17 is monovalent, right? Okay. Monovalent, I'll just write monovalent atoms. What are monovalent atoms? Monovalent atoms is hydrogen or group number 17. They are monovalent. They have only valency 1, right? So here fluorine is definitely monovalent. So it will be 6 by 2, that is nothing but 3, that is sp2, right? So anyway, in some cases you will be able to apply this, in some cases you will be able to apply this. Now I'll tell you from the formula. When you have no idea, here to there can be one student who is saying, ma'am, how you know that there is no lone pair here? Ma'am, who told you there is no lone pair? Ma'am, what if I don't know if there is any lone pair or not? Ma'am, then what I will do? Possibility is there, na? You don't know whether there is lone pair. Ma'am, who will tell me, ma'am, here you have lone pair or not? Ma'am, I don't have that much knowledge. That's why I am in this session, right? Ma'am, I don't know how to know that there is lone pair or not. So to understand whether there is lone pair or there is no lone pair, we have to see a lot of examples, right? And trust me, in the end, right, you will be like this in calculating the hybridization, right? But before that, there are some important things before jumping into the examples. If you talk about VSEPR theory states that if there are two lone pairs, lone pair repulsion will be there. If there is one lone pair and one bond pair, lone pair bond pair repulsion will be there. If two bond pairs are there, even then there will be repulsion. But lone pair repulsion is more as compared to lone pair bond pair, as compared to bond pair repulsion. That is why angle change we will see here, right? Okay. And whenever I talk about geometry, I'll talk about lone pair plus bond pair. Whenever I'll talk about shape, I'll only talk about the bond pair, right? These are some pre things that you must know. Now I know that you're still confused, but ma'am, how do I solve the question? Let's start. Okay, let's start solving. Okay, let's start solving, right? Okay, yes. Okay, yes. Tell me. VSEPR theory, VBT, hybridization, all the combination will apply and solve these questions, okay? So they have given you, you know how they ask you the question. Let me just firstly show you how they ask you the question. This is your JEE 2025 question. This is how they ask you. Now these shapes can vary. They can ask you anything here. So that means you don't need to cram the shapes. You can't do that. How many shapes you will cram? Tell me. Are you a computer who will just type the shapes and record it? No, right? You have a brain, right? It has some memory, and use that memory very wisely, right? So that's why we will understand how to calculate these shapes, right? Okay, these are the questions, and this is also the questions that they ask you. Total number of molecules with pyramidal shape, that's how you answer this. right? So to answer these two questions, we'll have to go through these tables, right? Let's understand that. So first is they have given you a molecule, let's say BeCl2 molecule. In this molecule, let's say what you have, one by one I'll draw that. Firstly, see what you will do, right? In BeCl2, firstly what you will have, let's say you have Ab2 kind of molecule which has 0 lone pair and 2 bond pair, right? Okay, here they will tell you, firstly I'll just show you that what is the situation. Okay, what is the situation? Chalo, let's understand that with the help of examples also and with the situation also. First situation is Ab2 kind of molecule. Ab2 kind of molecule means there is some central metal and there is two atoms. Now here they are saying that there is no lone pair. Lone pair is not present here. Don't look at the examples as of now, just look at this thing, right? You have a molecule which has 2B and there is no lone pair here. Now tell me, what is the number of lone pair plus bond pair? That is going to be sigma plus lone pair. Sigma plus lone pair is going to be, sigma is 2, lone pair is this, it is going to be 2, so the hybridization is sp. For sp hybridization, I always say the structure is going to be linear, right? This is the structure, this is A, this is B, this is B, and the geometry is going to be linear, that we talk about. And whenever you have no lone pair, 0 lone pair, so what is the situation here? You have 0 lone pair, shape and geometry is going to be same, right? Because what we have learned that geometry we will define lone pair plus bond pair, and shape we will define lone bond pair only. So when lone pair is 0, then both geometry and shape will defined by the bond pair, that is 2. That is why our geometry and shape is going to remain the same here, that is linear, right? Okay, now ma'am, here also ma'am in the question it was given whether it's lone pair or bond pair. Ma'am, tell me, if I don't know only that what is, for example, this is given to you, this example is given to you, BeCl2. Now how do you answer it? You have no idea that how many lone pair bond pair are there. Let's understand. Okay, this is the same sequence that you will apply. Firstly, this is the step process that you will apply. Firstly, you will say, okay, BeCl2, central metal atom will be beryllium. What you do, firstly calculate the, either you directly calculate the value of Z here. There are two ways to answer this. Calculate the value of Z. Z is what? Z is going to be, beryllium is, till now I have no idea whether there is any lone pair or bond pair, right? Okay, so either you can calculate the value of Z here, that is half. Beryllium is going to be, it belongs to group number 2, that means 2 valence electrons, and monovalent atom is 2, so it is 4 by 2, that is 2, that is sp, right? That is clear to us that it is sp hybridization, right? Okay, I'll tell you one more way to verify this, how I do it. See, you have beryllium. Firstly, write down the valence electron of beryllium, that is 2. Okay? You have written down the valence electron. Now see how many bond pairs are there. How many bond pairs? Bond pairs will define that in beryllium you have 2 valence electron, and those 2 electrons are occupied in forming the bond. So that means 2 minus 2. Bond pair, whether it's sigma, whether it's pi, you will have to add the bond pair, right? So that means when you subtract it, it will define the lone pair. That means there is no lone pair. So understand how to calculate the lone pair. Number of lone pair, how do you calculate? Lone pairs will be simply calculated by, you define the valence electrons of the central metal atom, then you subtract the bond pairs here. How many bond pairs you have? You have 1 bond pair, 2 bond pair, 3, whatsoever. That will tell you the number of lone pairs. So that is going to be, number of lone pair is 2 minus 2, that is 0, right? So here you can calculate the value of Z as, sigma bond is 2 and lone pair is 0, so it will be 2 plus 0, that is 2. So it means sp hybridization. So either though you can calculate it directly from the formula, right? But in the formula na, sometimes we get confused in understanding the lone pairs, right? So that's why I try to calculate it with this method, so that there is no chance of any doubt, like there is no chance of doing it wrong, right? So here number of lone pair is number of valence electrons minus bond pair, and z will be sigma plus lone pair, right? And now you know it's a linear structure without any lone pair. When you have zero lone pair, it is the sp hybridization, means it is going to be a linear structure. So this is be, this is cl, and that's it. It's a linear structure, the hybridization is sp, right? Done. Okay, similarly you will calculate for hgcl2. Now let's understand that, ma'am, what if I have, ma'am, let's take here the example can be hf, right? The example can be hf, right? Okay. No, not hf. Actually, example is very difficult here. Otherwise, so they will not ask you this. But still, just to tell you that what can be the process here. Wait a minute. So, what if you have a structure, right, where you have one lone pair and one bond pair? That means you have AB, and here you have one lone pair. Now, in this case, right, this will be the situation. You can draw it here. This is one AB and this is the lone pair. If you see sigma plus lone pair, sigma is 1 and lone pair is 1. So hybridization is sp only. Hybridization will stay sp only. It is going to be a linear structure only, that will remain the same, right? Okay, done. Acha. Now let's see more things here. That is this BF3 and SO2. This I'll calculate for you directly, right? But firstly, let's understand this pattern, this page here, right? See, if you have AB3 kind of molecule, AB3 matlab tetrahedral it will be. AB3 na, AB2 it will be. AB3 will be 4 na, so it will be AB. No, say. Yes, AB3 only. Yes, this will be the situation. That is trigonal planar. See, when you have lone pair is 0 or bond pair is 3, even then the total Z value is going to be 3. That means it is going to be sp2. Even if this is 1 and this is 2, so 1 plus 2 is also 3. Even then it is going to be sp2. Even if you have 2 lone pair and 1 bond pair, then also it is going to be 2 plus 1, that is 3, that is sp2 hybridization. So we know that sigma plus lone pair is always going to be 3 in all the 3 cases. So always in the 3 cases, it is always going to be like this. This is A, this is B3. Okay, B3. This is B, B, and this is B. In this case, you have AB2. Now you have one lone pair. So what you will have? This is A. You will have one lone pair. You will have this B. You will have this B. In this case, you will have 2 lone pairs. So it will be one lone pair here, one lone pair here, and one B here. Now geometry is going to remain the same. That is trigonal planar. That is not going to change. Geometry will remain the same. But the shape is going to change. Let's see how. देखो बेटा, whenever sigma plus lone pair is 3, whatsoever is the situation, you have 0 this, 3 this, 1 this, 2 this, 2 this, 1 this. If the total number is 3, it is sp2 hybridization, that is final. Geometry is defined by sigma and lone pair, bond pair and lone pair both. So that is the reason geometry will always remain trigonal planar only, but the shape will change. If you have this, all the 3 bond pair, this is trigonal planar. If I remove this, here if you have a bond pair, and we don't calculate bond pair in shapes. Now isn't it bent V shape, right? So that's why we write it here bent V, right? And that is the reason you will write here, what thing you will write here? This is same. This is trigonal planar only. What you will write here, this particular shape is bent V shape. Can you see this over here? This is bent V shape, right? Now what about this one? If you have 2 lone pair, you take out one more here. It is this. Can you see what is this? This is a linear structure because you don't see lone pair. just erase the lone pair here. That is a linear structure, so you can say this is linear. Okay, right? Now, shall we do the examples? Shall we solve the examples here? Right? Because understanding from the examples is very important for you, because in the exam, they will not tell you this has 0 lone pair or 1 lone pair. That thing we'll see, that how we will predict that. Okay? That thing we'll see. First, I'll be solving BF3, which is again a very, very important one, right? Then here I'll be solving SO2, right? Okay. So if you see this here, acha, what was the first thing that we used to do, right? Solve it from how I do it, right? Okay, let's solve it, right? So here, first thing is calculate the lone pair. Lone pair is nothing but whatever is the valence electrons of this sentimental atom, that is, it belongs to group number 13, so it has 3 valence electrons, and sigma 3 bonds it is making, so it will be 3, right? You will subtract 3 here, right? So answer will be 0 lone pair. So Z is equals to sigma plus lone pair. How many sigma bonds it is forming with BF3? Now, if I don't know the shape, at least I know this thing, that it will be forming 3 sigma bonds here. So 3 sigma, lone pair is 0, so overall it is 3. So overall 3 means it is going to be sp2 hybridization. That's how. Now, once you know the hybridization, everything else is simple. You have B, this is F, this is F, there is no lone pair here, right? This is BF3, that is going to be trigonal. Everybody write it in the chat box, trigonal, planar, geometry and shape will remain the same here. It will not change here, right? Okay, let's see this. Now, everybody do it yourself, okay? Tell me, sulfur belongs to which group? Very good, everyone in the chat box. Sulfur belongs to group number 13, 14, 15, 16. Which group? It belongs to oxygen family. Don't worry, if you don't know, ma'am, I don't know how to understand which belongs to which group. I'll teach you that in block chemistry, okay? I'll teach you that today itself, right? So this belongs to group number 16, so it is going to be 6 valence electrons. Now, always remember, that's why I took this example here. Always remember, sulfur, oxygen always form multiple bonds. Fluorine always forms single bonds. Oxygen form multiple bonds. You will always see on all the structures, oxygen is forming 2 bonds here. 1 sigma, 1 pi, right? I right now have no idea what kind of shape it is. I just know it forms multiple bond. So I can see 1, 2, 3, 4. 4 bonds. Don't subtract only the sigma bonds. Subtract the bond pairs. I want to see why I'm doing that. I know 1, 2, 3, 4, 5, 6 valence electron it has. Now I know that 4 valence electrons are used in forming the bond pairs. That's why I subtracted. Then only I'll get to know that I am left with only 1 lone pair, right? So that's why I'm subtracting the bond pairs here. That is 4, it is 2. 2 electrons you are left with. That means 1 lone pair you will have. That means 1 lone pair you have. Now, what is Z? Z is sigma plus lone pair. Sigma is what? Sigma, bacha, tell me how many sigma bonds you have. 2 sigma bonds you have. Okay? 2 sigma plus lone pair is 1, that is 3. That means this is also sp2 hybridization. Ma'am, how sp2 hybridization? That means it is going to show you a structure that is trigonal planar only. Right? It should be trigonal planar only. But 1 lone pair will be there. And you know how I place lone pair? Let's say lone pair is this green atom here. That is the lone pair. This is the lone pair. These are the bond pairs, right? Now, can you see? Geometry looks like trigonal planar only. But if I want to see the shape, I'll just remove this and I'll see, array, this is bent V shape, right? Geometry will be, now what you write? This is S, right? Just simply make the lone pair here, that is this one, and this is double bond O, double bond O. Now geometry is trigonal planar, right? That I will not write, I'll just write the shape here. It is a bent V shape, bent V shape, okay? That's how you solve it, right? Okay, Tell me, tell me, tell me, tell me. Any problem? Now this particular part is clear to you, right? Okay, this part is clear to everybody or not? Right? When you have trigonal planar, then what is the situation? Now let's see if you have hybridization. Here na steric number will be 4 in this case. In all these cases, the 4 cases that we have drawn, it will be sp3 hybridization. Now how it is possible? You can have 0 lone pair, 4 bond pair. Overall it is Z is going to be 4, it is sp3. Okay? Here it is 1 plus 3, that is also 4, right? So I'll just write this thing, right? Okay, it is same only. Here it was 1 plus 3 is 4, 2 plus 2 is 4, 3 plus 1 is 4. That means overall Z is going to be 4 in all these cases. So whenever Z is 4, you always say it is a tetrahedral geometry. So the structure geometry is going to be tetrahedral here. But you know what's the catch? They ask you shape in the exam. They don't ask you they want to ask you a tough question. Why would they ask you structure or geometry? They ask you the shapes, right? So the structure, oh, by mistake I have written it here. Tetrahedral geometry, right? In all the cases, but structure is going to differ here. Let's see how. So when you have all the 4 bond pairs, it looks like this, isn't it? It looks like this, guys. It looks like this. Let me just show you that over here. It looks like this, isn't it? Right? Now what I want to do, I want to say, okay, this looks like this. This is A, 1, 2, 3. This is how we make it in 2D, right? Now I want to say I have a lone pair. Okay, you have a lone pair. Perfect. If you have a lone pair, I'll just draw the lone pair here. When you have a lone pair, geometry is tetrahedral, but I want to just see the shape. So here it will be, is it planar? Is it planar? What kind of situation this is? Tell me. I'll just block, don't worry. What kind of situation this is? What situation this is? Is this planar? Is this putting, can I just put it in my palm and this is, can you see it is getting pressed in my palm? No, it is not this. You can see it is bulging out. So this is not planar. This is actually pyramidal. If you see, this is actually pyramidal structure. So that is called as pyramidal, or you can say trigonal pyramidal, right? So tetrahedral, so here also it is tetrahedral, right? Here you can say pyramidal shape. Very important, pyramidal shape. Now if I say you have 2 lone pairs here, then what you will do? Remove one more here, right? Can you see now it became bent V shape, bent V shape. So I'll just write here bent V shape, bent V shape. There are 3 very important things that we want to discuss here. Last one is, what if last one where I just leave one bond pair, that one you will never see. Very rarely you will see that example, right? So here you will see that is a linear structure. Okay? So now you have linear shape. Okay, structure, pyramidal structure looks like this. One lone pair, rest of them are bond pair, right? In this case you will have, you have 2 lone pair and 2 bond pair. This is like water. And here you have only 1 bond pair, right? And 3 lone pair. Okay? So last one though you will not use. This one you will use, right? Okay, tell me, any problem here? Any problem here? Right? Now shall we answer CH4 and water, and these are 3 very, very important things regarding sp3 hybridization. 3 things we are discussing. What is that? CH4. Okay, so I'll just draw CH4 here, right? Then we are discussing water, then NH4. Sorry, NH3. Okay na beta? Tell me. So what you have, firstly you have CH4, then let's discuss NH3, then let's discuss H2O. Now I am assuming you know nothing. I am assuming that you have no idea that NH3 has how many lone pairs, water has how many, because there is a possibility, right? Now in these cases you have an idea, maybe sometimes you forget that in the exam, right? So how to solve it? Process will be same. Tell me what was the process. Firstly, what we used to do. Tell me, firstly, what we used to do. Nahi, officer, no, not at all. In sp3, only tetrahedral is the case, right? We'll talk about square planar in coordination, that has a different hybridization. We'll talk about that. Application part is also different there, right? How we apply VBT theory, that is entirely different in coordination. So don't get confused, right? But yes, it will help you. But if you start getting confused, it will, and you will end up ruining both the chapters, okay? So that's why what I am telling you, only focus on those things, right? So here, what is the valence electrons? Bond pair and lone pair add. Very good. So firstly, let's calculate the lone pair. Valence electrons of carbon belongs to group number 14. So valence electron is 4. And here, how many bonds it is forming? It is forming 4 bonds. So I'll just draw the 4 bonds like this. I have no idea about the shape. I'll draw it like this, right? So I have 4 bonds. So it is -4. It is 0 lone pair, right? Ammonia, N is forming 3 bonds here. I have no idea about the lone pair. So this lone pair is equals to nitrogen belongs to group number 15. That means 5 valence bond, valence electrons, right? Minus you have 3 bond pairs. This gives you 2 electrons. That means 1 lone pair it will have. That means nitrogen is going to have 1 lone pair here. Similarly, water, you have oxygen, it is forming 2 hydrogens now. Ma'am, but you said oxygen always form double bond. Array, oxygen wants to form 2 bonds. Now, possibility is that oxygen is forming 2 sigma bonds, or possibility is that oxygen is forming 1 double bond. But it wants to make 2 bonds. That is the thing about oxygen. Nitrogen always wants to have 3 bonds. Oxygen always wants to have 2 bonds. That is the possibility, okay? So now if you see here, lone pair is equals to, in this case, this is OHH. Tell me, oxygen belongs to group number 16. 16 means 6 valence electrons. 6 minus how many sigma? Ma'am, 2 bonds it is forming. Ma'am, 4 electrons. That means 2 lone pairs. Tell me, is there any problem in answering the lone pairs, right? Is there any problem? Even if you know, I'm telling you, even if you know that oxygen has 2, even then calculate it like this. Why? Because what if they give you sulfur, right? Otherwise, so you should know that group number 15 has 1 lone pair electron. Group number 16 always has 2 lone pair electron. 17 group will always have 3 lone pair electron. Okay, those who don't want to calculate like this, see, this method you should know, because in some cases it gets, they don't ask you directly. I'll give you the examples of those complicated cases as well. But otherwise, in a neutral state, when it is not a cation, it is not an anion, condition is it should not be a cation, it should not be an ion. Group number 14 does not have lone pair. Group number 15 has 1 lone pair. 16 has 2 lone pair. 17 has 3 lone pair. Okay, right? Done. Now, what is Z here? Z is equals to sigma plus lone pair. Sigma is 4, lone pair is 0, it is 4, that is sp3. Right? Z is equals to sigma is 3 sigma plus 1 lone pair, it is 4, it is sp3. Here Z is equals to sigma is what? 2 sigma you have, and you have 2 lone pair, it is 4, it is sp3. Now the situation is same. We will also apply VBT here. Tetrahedral situation you will have here, tetrahedral geometry and structure you will have here. That is this kind of structure you will have here, right? Okay, tetrahedral structure you will have here. That is this kind of structure it will form, right? Now after that, what I'm going to do now, I'll just change one of them with the lone pair. Okay, one of them I'll just change it with the lone pair. That will form the structure of NH3. Now tell me, what is the angle of NH3? This is a theory. VSEPR theory, which tells us that if you have all of them as bond pair, bond pair attractions, repulsions are least. If you have a lone pair, there will be repulsions. This lone pair will repel this lone pair will repel this lone pair will repel this. Because of this repulsion, the angle that was earlier 109 will even now more, it will create more bulge, and this will be 107. Okay, it will be 107. Here the angle is 109, here the angle is 107 because of this lone pair bond pair repulsions. In case of water, what you will have, in case of water, you have two lone pairs. Lone pair repulsions are maximum, and that is the reason they will repel each other. This will further repel this. And what will happen here, if I place one bond here, if I place one more lone pair here, this is water, right? This is water having two lone pair, two bond pair. Now what will happen, they will create so much repulsion that this will be even lowered, that is 104 degree. Okay, right? ठीक है जी, 104 degree. Understood? Tell me. This is a very, very important case. Right, everybody? Understood? I want you guys to be pro in this particular. I don't want to do like, okay, this is hybridization. This is the question. Okay, I know if I teach you like that, it will be like I am just teaching you because, okay, I have done this topic, right? You will also feel, oh, ma'am has taught it, I have done this topic. When you solve the question, you will end up like, you will be like, I don't know how to solve this. So what's the benefit of that, right? I know you are here because you want to gain marks, right? And this is how I have designed this lecture, right? So that you gain maximum marks out of this, right? And if you see, this is Z is equals to 5 when it is sp3d situation. Now it can be 0, 5, 1, 4, 2, 3, 3, 2. That means always addition of lone pair and bond pair should be 5 here. So that is always going to be sp3d. Hybridization is going to remain the same here, right? The structure also, structure I'll define. Geometry will always be trigonal bipyramidal. What is the geometry always? Trigonal bipyramidal. Now this is very important. We are going to see something really unique here. Geometry will remain the same. That is this geometry. Okay. See, this geometry we are going to see. What is trigonal? This is the trigonal part, right? This is the trigonal part. And here you have two pyramids over here. You have this pyramid and you have this pyramid. What's the big deal? I'll tell you what's the big deal. Big deal will be when you solve it, right? Chalo, first let's understand what will happen here. Bacha, if you have all the sigma bonds, there is no problem in that. It means this is also trigonal bipyramidal. No problem in that. No problem. Right? But ma'am, what if I have one lone pair and 4 bond pair? If you have one, ma'am, should I have the lone pair here? That is the big problem. Ma'am, should lone pair be over here or should lone pair be here? So remember, this is a very important point. This they can ask you directly, assertion reasoning question. This they can ask you in the form of shape. This is a very, very, very important point. That lone pair will be over here. Ma'am, should I put lone pair here, ma'am? Ma'am, or should I put, ma'am, lone pair over here? So these are two positions. Okay, these are two different positions. Okay, if you put lone pair here and you see the shape, it is this kind of shape. Okay, it is this kind of shape, right? If you put lone pair here, first you need to understand that difference it will create. If you put lone pair here, it will have an entirely different shape. Okay? Now when you remove the lone pair and see the shape, this is the shape. So where you should put the lone pair? So always remember, lone pair, these three positions that are in the trigonal planar phase, that I can rotate here, that I can rotate here, these three, okay, if you see, wait a minute, let me just show you that. This is upwards, right? This is downwards, and these are the three equatorial shapes that you have. Okay, wait a minute. Okay, these are the three equatorial shapes that you have. This is 1, 2 and 3, which I can rotate like this, which I can rotate like this. These are equatorial positions, the above and the below. Or I'll just show you this. When you form a trigonal planar, these three positions are called as equatorial. Okay, and when you form one above and one below to form two pyramids, that is axial position. And you know why always lone pair is on the equatorial position, not on the axial position? Reason being, because when, let's say, it is on the equatorial position, so what it will create? It will create less repulsion. Here the angle is 120, here the angle is 120, and here the angle is, it has two 120 angles and one 290. With this it has an angle of 90, with this it has an angle of 90. Okay, so repulsion will be maximum through 290-degree angle, because 90-degree angle is more. If I put lone pair here, it will have three bonds that are at 90 degree with this. One 90 degree, second 90 degree, third 90 degree. So it will cause more repulsions, and that is the reason always. And this now, if they ask you assertion reasoning question, they will give you assertion reason like that. Reason is because at equatorial position repulsions are less, because it has only 290-degree angles. And in case of if you put it in an axial position, it will have 390-degree angles, right, where it is repelling. So it will be more repulsions here, right? So answer will be, you will have it over here. And the shape, if you see, isn't it like seesaw? Isn't it like seesaw? Hai na? This is like seesaw, na? Seesaw, right? Seesaw, right? Right? So answer is seesaw shape. Now, when you have two lone pairs, equatorial position also, only you will put one lone pair here, one lone pair here. Okay, one lone pair here and one lone pair here. This will be the situation. Now, if you see, when you remove the lone pairs, it will be a T shape. Okay, that is T. So answer will be, this is going to be T shape. T shape, right? Then this one is going to be, when you have, even this is the lone pair, that is the linear only, then that thing only happens, that is linear. Okay, but important are this one, this one, this one, right? Okay, now let's see this with the help of examples. We have PCl5, SF6 and Cl. Chalo, let's see this. Okay, let's see this. Let's see this. Let's put it here. Three examples. Will you do it yourself as well, everybody? Will you do it yourself? Now let's move little fast. You have PCl5, you have SF4, then you have ClF3. Very important shapes these are, okay? They see it in your PYQs. You'll get the PDF of the, it is in the description box, you'll get the PDF, okay? Right? Acha, see, phosphorus has, tell me, bacha, everybody in the chat box, tell me, if you see how to calculate lone pair. Lone pair is number of valence electron, that is 5 for group number 15, minus sigma bonds, minus bond pairs, that is 5, so it is 0 lone pair. So Z is equals to sigma plus lone pair. Sigma is 5 plus lone pair is 0, it is going to be 5, that is sp3d, right? Then if you have here to calculate lone pair, it belongs to group number 16, that means 6, minus 4 bond pairs, it is 2 electron, that means 1 lone pair. Z is equals to sigma plus lone pair. Sigma is 4, lone pair is 1, so it is going to be 5, that is sp3d, right? This lone pair is, this belongs to group number 17, that means 7 valence electrons, minus 3 bonds. This 7 minus 3 is what? 4. 4 electrons means 2 lone pairs. So sigma plus lone pair, that is Z. Sigma is 3, lone pair is 2, it is going to be 5, that is sp3d. So now you can write the shapes here. This is PCl5. This is, as I have written, trigonal bipyramidal. This is S, but here in this case you will have a lone pair here. This is F, 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 F here, right? Okay. Some students, one student also asked me one question, ma'am. What if, ma'am, wait a minute. Ma'am, what if I have a lone pair not here but here? Wait a minute. In 2D, when you see it, you will find it tough. Ma'am, what if I don't want to have my lone pair here? Ma'am, I want to have it here. Okay, have it here. Isn't it same? Okay? So in 2D, you might feel like some student like, ma'am, why? What if, ma'am, lone pair is, ma'am, here and this is F here? It is same only. It is not looking like a seesaw shape, but even now it is a seesaw shape. Okay, even if they draw it like this, now in the exam they draw it like this. This is also seesaw only. Okay, this is also seesaw. This question they can easily ask, they can give you this kind of shape and students will mark it incorrect. Ma'am, this is not correct. Arey, why it is not correct? It is on the equatorial position. You put it here, you put it here, you put it here. It will be symmetrical only because it is 120-degree angle. Okay, so just for our convenience, we draw it like this. It's like we know that here it looks more beautiful and more symmetrical and it looks like seesaw in 2D as well. That's why we draw it like this. CLF will be 2 lone pair here. Now you can also draw it like this, okay? Even if it is written like this, it is not wrong. It is not wrong, right? But just to make it look like a T, we make it like this. Otherwise, you have 2 lone pair anywhere. Okay, you have it here, right? Or you want to have it here, right? That is same only. This all is symmetrical only, right? Okay. Ma'am needs, definitely you can watch Sudha, definitely you can watch. Acha, tell me, is there any problem in this? Is there any problem in this? Last one we are doing now. Here what you have Z is equals to 6. It always defines for sp3d2, that is octahedral, right? Now here octahedral means this thing, that is octahedral. Now in octahedral, either it can be 0 lone pair or 6 bond pair, 1 lone pair or 5 bond pair, or 2 lone pair or 4 bond pair. All of them will mean the same thing, that is Z is equals to 5 here, that it is sp3d2, right? That is the same thing here, right? And the structure, definitely we'll see, geometry is always going to be octahedral geometry, that is not going to change. Let's talk about the shapes here, right? You have all the sigma bonds, that is octahedral. You have one lone pair. You put one lone pair here, what it is going to look like? Tell me what it is going to look like. Anyone of you? Anyone of you? This will be the lone pair. Green, I am drawing the lone pair. Now for shape, just erase the lone pair from here. Just take it out. What is this? This is a square and over there you have one pyramid. So that is square pyramidal. Simple, right? So write it here. See, if all of them are same, so it is going to be octahedral. If there is one lone pair, it is going to be square pyramidal, right? If you have two lone pairs, even here you will have the lone pair. Take it out because in shape you don't consider the lone pair. That is a square planar shape. So just write square planar, right? Okay. How it will look like here, I'm just drawing, this is A, 1, 2, 3, 4, 5, 6. Here it will be A, 1 lone pair, 1, 2, 3, 4, 5. This will be A, 2 lone pairs, and this will be 1, 2, 3, 4. Right? Okay? Tell me. Now let's do SF6, BRF5 and XCF4, right? On the next page, let's do these three, right? Ready for this, everybody? Let's do these three. 1, 2 and 3. Okay, let's do this. Three shapes I am going to discuss now: SF6, BRF5, SF6, BRF5, and then what one was the last? XCF4. I think till now, so you are pro in this. Do you have confidence now? Everybody spam it in the chat box. Right? Lone pair should be on equatorial position. Definitely, yes, Harshini, lone pair always will be on the equatorial to cause least repulsions. Okay? Right? Okay? Where I have drawn it on the axial. In octahedral, there is no axial or equatorial. Equatorial or axial is only in case of trigonal bipyramidal. This is equatorial and this one is axial. In case of octahedral, there is no equatorial axial. Okay? Right? Octahedral, everything is symmetrical. Right? There is no axial equatorial there. Right? Okay? Yes. Confidence you are getting, very good. Now just solve this along with me. Solve this along with me. This is group number 16. So it has 6 valence electron minus 6 bond pairs that you are having here. It will be 0 lone pairs. So Z is equals to sigma plus lone pair. Sigma is 6 and lone pair is 0. So it is 6. That is sp3d2. Right? Here it will be, this belongs to group number 17. So it is 7 valence electron minus 5 sigma bonds. It is 2 electrons. That means 1 lone pair here. Okay? So now Z is equals to sigma plus lone pair. Sigma is what? Tell me. Sigma is 5. Lone pair is how many lone pairs you have? 1 lone pair now. So it is 6. It is sp3d2. Right? Again 6. Here it belongs to group number 18. So it is 8. Minus what you will do? Tell me. Minus 4. 4 bond pairs you have. It has 4 electrons left. That means 2 lone pairs. So Z is equals to sigma plus lone pair. Sigma is 4. Lone pair is 2. So it is 6. That is sp3d2. Isn't it? Tell me. Any problem? Now we know that this means it's octahedral. So just draw octahedral here. This is SF6, right? Okay. Now what about this one? This is bromine, right? In this case, you have a lone pair here. Rest of them are your fluorine that you have drawn over here, right? Okay. Yes. Now here you have xenon. Xenon, you have 2 lone pairs and you draw it like this. Okay? Tell me, beta, it is actually a very scoring thing, right? Because you don't have to remember this. In inorganic chemistry, now, block chemistry, you have to memorize a lot of things. Why you want to memorize the shapes? There is nothing to memorize here. You can't do that. How many shapes you will memorize, right? Okay? Understood? Let's see now questions. Okay, how they, most of the shapes so we have already done in the question part, in the example part. But still the ones that we have not done, I'll do that as well. Okay. See. If you talk about SF4, if you remember, SF4 I told you already, it will have this kind of situation. It will have a seesaw shape. Do you remember that? It will have a seesaw shape. Okay. So I'm just directly writing it seesaw because I have already done that in examples. I'll not repeat the same thing that I have done it in example. BRF3, we have done it already if you remember. BRF3 also we have done. BRF3, अच्छा, we have not done BRF3. Okay. कोई बात नहीं, we'll do that. We'll do that. If we have not done, we'll do that. Right? Okay. I think rest 3, let's see how to do. Right? So, BRF3, tell me, now this is your final countdown. Okay, let's see if you can answer this or not. BRF3, BRO3 negative, BRO3 negative, then you have NH4 positive. right? Then you have NH4 positive, right? Okay, let's do this. Everybody, tell me, tell me, tell me, tell me, tell me, tell me, right? Okay. Yes, elements and their groups will remember this in block chemistry, right? We'll do that. Don't worry, today itself we'll do that. BRF3, if I would have started with block chemistry first, you would have exhausted yourself, right? So it's better to understand theories and all in the first go. Then we will move towards, after a good break of half an hour, we'll move towards block chemistry, because that is too much memorizing things to do. But I have already made a very beautiful notes for you. Handwritten notes are there, right? Some very important conclusion from your NCRT is there, right? So if you watch that block chemistry that I have done, that I'll do today, you don't have to watch anything else, right? Okay, now see this thing here. You have bromine. Bromine belongs to group number 17, that means 7 valence electron minus 3 bond pairs. 7 minus 3 is 4 electrons, that means 2 lone pairs, right? So Z is equals to sigma plus lone pairs. Sigma is what? Till now I have no idea what it will come out to be, okay? So sigma is 3, lone pair is 2, it is 5. So I can say it is sp3d. Okay? Now that means it is trigonal bipyramidal geometry. Bipyramidal geometry, right? What about lone pair? One lone pair, you have 2 lone pairs. So it is Br. This is 1, 2, 3. This is geometry. 2 lone pairs you have to put here, right? That I'll put here. And this is a T shape. Okay. So this is a T shape. So you can write it here. It is coming out to be T shape. Bent T shape. Okay. Why, ma'am, bent T shape? Because lone pair will repel each other, right? Then lone pair bond pair will repel this. So it will slightly move here. It will slightly move here. Okay? Understood? Now, what about this one? Bromine again belongs to 7 valence electrons. It has, acha, always remember, oxygen wants to form 2 bonds, okay? It will be like this. How many bond pair? 1, 2, 3, 4, 5, 6. 6 bond pair. Okay? You have also added one negative charge here. So that also you will add here. Okay? One negative charge is also there. Negative charge is always added in this case. Positive charge will always be subtracted in this case. Okay? So you'll add 1 electron here. 8 minus 6, it is going to be 2. 2 electrons means 1 lone pair, right? Okay. So what situation you will have here? This is 6, 7 minus 6 plus 1. See, in this case, you will have sigma plus lone pair. Sigma is what? Sigma is 3. Lone pair is 1. So it will be 4. Why sigma is 3? Because it is forming double bonds. Okay, 1 sigma, 2 sigma, 3. 3 sigma you have. So it is sp3 here. Right? So what you will have here, if I draw the shape here, this is Br. Okay, it will have a lone pair, double bond. It will have 1 O negative here, and you will have one this thing. ठीक है ना? That's how it will be, na? Because see, if I say there is one oxygen which is negative, a simple concept about chemistry is, if you have a neutral oxygen, it will be 2 bonds. If you have an oxygen which is negatively charged, it will be 1 bond always. Okay? That's why if I calculate this, you can also calculate it like this. You can also calculate it like this, that 7 minus 5 is equals to 2 electrons, that means 1 lone pair. Okay? Or you can calculate it like that as well. But always remember, whenever you have 1 O negative, that means 1 oxygen is having 1 single bond. Okay? Always when oxygen has a negative, it always have a single bond, and it will always have, now if you see, it is a pyramidal structure, because lone pair pyramidal shape it has. Okay? Tetrahedral geometry, pyramidal shape it has. This is a very important one. Okay? Then you have, this is belonging to group number 15, so 5 valence electrons. And here you have 4 sigma bonds, it has bonded 4 sigma bonds, right? And here you will subtract one more minus here because of the positive charge. So it will be 5 minus 5, that is 0 lone pair. No lone pair will be there. Okay. So Z is equals to what? Z is equals to sigma plus lone pair. How many sigma bonds it will have? See, 1, 2, 3 and 4. 4 sigma bonds. Lone pair is 0, it is 4, that is sp3. Now see, this is nitrogen. It has 4 sigma, 1, 2, 3 and 4. Lone pair it does not have. Why then it will have a positive charge here? Because nitrogen always wants to have 3 bonds if it is having more than 3. I'm giving you one simple thing to remember for your chemistry section, right? This will be useful anywhere in chemistry, organic, inorganic, it will be useful. Oxygen wants to form 2 bonds. Okay? If it is having 1 bond, if by chance instead of 2 it is forming 1 bond, it will be negative. Whenever you have less than what you want, you always feel negative, na? If you were expecting really good marks in something, you don't get, you feel negative. If you get more than what you want, then you will be very positive, right? Similarly, in case of nitrogen always wants to form 3 bonds. Okay, but if it forms let's say 2 bonds, it will be negative. If let's say it forms 4 bonds, it will be positive. Okay, tell me everybody, is that clear? So here it is, this one is pyramidal and this one is tetrahedral. As you can see this over here, that will be tetrahedral shape. Okay, accordingly you will have your answer, right? Okay, tell me everybody, is that clear? Okay, now last question on this, and after that we'll start with the next topic, right? Okay, yes everybody, tell me, will you answer this? Most of it we have done, right? Isn't it? This we know, this I have taught you there as well. This NH3, do you remember? Most of it though we have already done. This was tetrahedral shape. Do you remember? ClF3 was, I think so, it was, I think so, maybe it was T shape, I think. Hello? ClF3 was T shape, right? Okay, ClF3 was T shape, right? I'll just see what all I have not done, right? That I'll do. This we have done, this we have done, this also we have done. SO3, Achha, SO3 we have not done, I'll just do that. PCl3 also we have not done, I'll just do that. XCO3 also we have not done. This we have done. BCl3 same like BF3, it is trigonal planar. Okay, then you have ClO3 negative, SO3 2 negative, right? Let's do it one by one. Let's divide. How many you want to solve? 1 2 3 4 5 now. Let's divide this into 3 parts, right? 5 you want to solve. Okay, 2 3 are the very simple. SO3 PCl5. Firstly let's solve PCl3, then you have SO3, then you have XCO3. SO3, then you have XCO3. Okay, let's see that. Same funda, same everywhere, same thing, right? Same funda. This is group number 15, 5. I am the bored of doing this now. Last time I am doing this. Same funda everywhere. 5 minus 3, that is 2 electrons. That means 1 lone pair. Wait a minute. 5 minus 3, that is 1 lone pair, na? 5 valence electrons minus 3, 1 lone pair. ठीक है, 1 lone pair, right? This is how many valence electrons? This is 6 valence electrons. Now SO means it will have 6 sigma. 6, this is 0 low. I think this we have done. I think this we have done. We have done this. We have done this, yaar. We have done this. This was trigonal planar. We have done this today itself. SO3 was trigonal planar only, right? I'll just write this here, trigonal planar, right? Okay. I think rest of it will be pyramidal. Chalo, let's see, right? Now you have fourth 1, 2, 3, 4 I have written here. Now you have PCl3. PCl3, everybody. Now PCl3, if you talk about PCl3, what kind of shape it will have? Okay, wait a minute. What kind of shape it will have? It will be Z is equals to sigma plus lone pair. Sigma is what? 3. Lone pair is 1. It is 4. It is sp3. It is going to be tetrahedral with 1 lone pair, and that means it is going to be pyramidal. It is going to be pyramidal, right? Okay, done. What about this one, XCO3? This Xc belongs to group number what? Tell me. Xenon belongs to group number which? Noble gas, na? Group number 18. 8 valence electron minus. Always it will have a double bond. So it will have 1, 2, 3, 4, 5, 6 bond pairs. That means 2 electrons. That means 1 lone pair, right? Now sigma plus lone pair is what? Z is equals to sigma plus lone pair. Sigma is 3 because 3 sigma, na? Here you will have 1, 2, 3. Only 3 sigma. Okay? 3 sigma plus lone pair is what, everybody? 1 lone pair, that is 4. It is also sp3. And here what you will have is double bond, double bond, double bond. And here, S nahi, this was xenon. Xenon, and here it will have a lone pair. So again, this is also pyramidal, right? Okay, acha. Can you tell me about this one? These two we have done, they were pyramidal, this was pyramidal. What about ClO3 negative and SO3 2 negative? This is going to be interesting for those students who are still getting confused in how to take negative and positive, right? This will help you in understanding that. Okay, right? Okay, you have ClO3 negative and SO3 negative, right? Let's draw that. ClO3 negative and SO3 2 negative. Is it? Was it SO3 2 negative? Haan. Okay, let's see that. So you have ClO3 negative. देखो बेटा, here you have chlorine. Chlorine belongs to group number 17. 17, ma'am, 7 minus Cl double bond, double bond. Whenever you have oxygen, you have one negative. That means there is one oxygen that is negative. It will be like this, right? Because you have one negative, that means be one single bond where oxygen is having negative charge, right? Okay, so 7 minus 1, 2, 3, 4, 5 bond pair, that is going to be 2 electrons. That means 1 lone pair. Okay, now in this case, what you have sulfur, which belongs to group number 16. That means 6 minus. It also has, it has 2 negative, that means 2 oxygen which are having O negative with a single bond. So now 1, 2, 3, 4, 4 bond pair, that means 2 electrons, that means 1 lone pair. Tell me if this thing is clear to all of you or not, right? Oh, हाँ, such NH3 is pyramidal. My bad, my bad, my bad. हाँ यार, shade, geometry is this. My bad, my bad. Yes, you're absolutely right. It is pyramidal. Yes, ma'am. Very good, very good. Right? Yes? Okay. So tell me if this thing is clear. If this thing is clear, how I did it. Now everything else is simple only, right? What you do, Z is equals to sigma. Sigma will be 3, lone pair will be 1, it is 4, it is sp3. Same here, Z is equals to sigma. Sigma is 3, 1, lone pair, it is 4, that is sp3. So it is going to be same as what we have done before. This is Cl, double bond O, one is O negative, there is one lone pair, this is also pyramidal, right? Okay, what about this one? This is S, this is double bond O, one O negative, other O negative, this is one lone pair, this is also pyramidal. Okay, beta, more than this they will not ask you, right? More, trust me, more than this they will not ask you, right? Okay, if you're able to do this, now we know what all are the shapes of pyramidal. This is pyramidal, this is pyramidal, this is pyramidal, this is pyramidal, this is pyramidal. So total is 5 is the correct answer. Okay, understood, right? Okay, tell me, is that clear? This topic we have done. Do you promise me, all of you now, okay, in inorganic chemistry one shot, I don't care whether it is this one shot will go up to 12 p.m. or 1 a.m. I'll wake up for you. I it's okay, I'll wake up for you if you are ready for that. But I want to do things in detail. You want, if you promise me that in this now you will not do mistakes. More than this detail, I can't teach you. Okay? This is the same detail, same depth that I have taught you in detailed manner when I taught you hybridization for the first time. Right? Okay? Understood? Now you promise me, ma'am, we will not do any mistake here. Do you promise me that? Do you promise me that? MOT, so it's MOT is free number. 2 tricks and you are sorted. MOT is that easy, right? Okay, now spam the chat box with green hearts if you promise that, ma'am. Hybridization, ma'am, no one can beat us in hybridization, ma'am. We will score full marks if there is a question, and 100% there will be question. 4 marks is final, right? 4 marks plus add 4 marks. Add 4 marks in your mark sheet, right? That is done, right? Santa promise, yes. Today though it will be Santa promise, right? Okay. So now let's start with molecular orbital theory, another important topic of coordination chemistry. Coordination chemistry, I'm saying chemical bonding. So in MOT, molecular orbital theory, let's understand how we are going to do it, right? See, bacha, MOT, so many things are there. First thing is molecular, they say that actually 2 atomic orbitals, they will make 2 molecular orbitals. One will be bonding molecular orbital, one will be bonding molecular orbital, other will be anti-bonding molecular orbital. This is represented by a star. And in bonding molecular orbital, what you have the addition of 2 atomic orbitals. Here you have the subtraction of 2 atomic orbitals, right? So in this case, let's say sigma 1 minus sigma 2, this will be sigma 1 plus sigma 2, right? So here you have the addition of orbitals, here you have the subtraction of orbitals, right? Now, next thing that is very, very important for you, that is this electronic configuration that you have to remember, right? Okay, this electronic configuration that you have to remember. Now, if you see this here, if you have, let's say, less than or equals to 14 electrons, right? That is this category. This category, I'll just mark it here. This category is for less than or equals to 14 electrons, right? Simple, I'll just mark it here. Less than or equals to 14 electron here, right? In this case, what you have, what about this one? In this case, what you will write? In this case, it will be, just write it here, more than 14 electrons. Ma'am, but how do I remember all of this, ma'am? Ma'am, some trick, ma'am, please, ma'am, some trick. Okay, right? See, I'll tell you how I remember this, right? See, first thing is sigma 1 है, sigma 1 है, sigma star 1 है, sigma star 1 है, sigma 2 है, sigma 2 है, sigma star 2 है, sigma star 2 है. So that means first 4 orbitals, right? They are same in both the cases. Sigma 1 है, sigma star 1 है, sigma 2 है, sigma star 2 है. So you don't have to remember that. So always remember this part, we tell it by kk star, right, or kk dash. That is having always 8 electrons. Remember, whether it's this or it's this, it will always have 8 electrons and 4 orbitals. It will have no differentiation here. But now here you have the differentiation, right? Here it is different and here it is different. So how do you remember this? Just remember one thing: less than or equal to 14 or equal to 14. Here write it more than 14. More than 14. Just remember one thing, that is, in this case you will have less than 2 1 2 1. How do you remember 2 1 2 1? Here it is 1 2 2 1, right? It is 1 2 2 1. Ma'am, what do you mean this by this 1 and 2? 1 means only one orbital will be there. See, if I write 2 1 2 1, it will be like 2 1 2 1. If I write 1 2 2 1, I will write 1 2 2 1. Okay, I'll just make it here as well, right? Okay, see what I told you: less than 14, less than or equal to 14 if all the electrons are. This is if it is more than 14, right? Okay, here it is if it is more than 14. This is just a way that I am telling you how to write it. Don't remember the full thing here, more than 14. Just remember one thing: this is 2 1 2 1, right? 2 1 2 1. This is 1 2 2 1. How do you write it? See, first 4 orbitals will be same, so you don't have to write it again and again. How I do it: simply do this: 1 2 2 1. Here write it 1 2 1 2 1 2 2 1. Now what is the difference? This is 1 2 2 1. The one that are above, last 2 will always be your star, so it will be the one that are equal will always be, see, equal ones will always be what? X and Y, and they are always pi to px. This is pi to py. Equal ones will always be pi to px. This is pi to py. Equal ones here also, this is pi to px. This is pi to py. This is always pi to px, pi to py. Okay, now the one that is not having two things, so that is one, that is 2pz. This is 2pz. Now here also it is 2pz, here also it is 2pz. Now when you fill the electrons here, can you see that? How do you fill the electrons? Tell me. Acha. Also remember, this one will always be star. Last 2 orbitals will be in the anti-bonding. This is also anti-bonding. First 2 orbitals are in the bonding. Okay? Just remember this. You don't have to remember this like fully. You don't have to cram the electronic configuration. See, first 4 will be sigma 1 is sigma star 1 is sigma 2 is sigma star 2 is. It's okay. Then just remember 2 1 2 1 1 2 2 1. 2 means x and y, 1 means z. Right? In x and y you always have pi, in z you always have sigma, right? Then last 2 will be anti-bonding, first 2 will be bonding. That's it. Done. Okay? Tell me. Done? Yes? Acha. Yes, it is applicable to heteroatoms. Yes, it is applicable. We'll see some heteroatoms as well. Right? Okay? Now see how to, for we have two tricks here. Firstly, though, I'll give you a formula of bond order. This is the formula of bond order. This is the trick of bond order. This is the way to calculate paramagnetic, diamagnetic. Okay. So the formula of bond order is half into number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals. Okay. Let's say you have taken, let's say I have filled the electronic configuration of 14 electrons. It will be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it will be 2 to 13, 14. Right now, see how many anti-bonding you have. Anti-bonding is only 2, 3, 4. Okay, anti-bonding is 4. Bonding is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 minus 4 divided by 2. That is 6 by 2. That is 3. N2 has 14 electron, and that's why N2 has 3 bonds, because its bond order is 3. Right? Okay. Done. Okay. If I get 1000 plus likes on this video, then I'll definitely do organic one shot. Right? Okay. But for that, I need 1000 plus likes on this video. Right? I'll see if you can make it or not. If you can make it, then definitely we'll do it. Right? Now, so you have not even made 120 plus. Right? So let's see if you can do that. Right? Acha, now one more thing. Right? Either you calculate it like this, or you always, this to always will be cancelled, this always will be cancelled, or directly don't ever include this, just directly include this part here, that is anti-bonding is 0, bonding is 1, 2, 3, 4, 5, 6. It is even easier, isn't it? It is even easier, right? Now, ma'am, but still, ma'am, what about the trick, ma'am? Ma'am, I want to save time in chemistry, ma'am. So this is the trick, okay? If you have 14 electron, bond order is 3. 15 electron, now bond order, just remember the bond order for 14 electron is 3. You go 1 less, it will be decreased by 0.5. That means for 13 it is 2.5. This is 2, 1.5, 1. When you go down here, you increase the atomic, you increase the number of electron by 1. It will also be increased by 0.5. So it is this will also be decreased by 0.5, 2.5, 2, 1.51. Okay. Now, for example, they ask you N2. N2 has 14 electrons, so bond order is 3. Easy, like really, right? So that's why MOT, to you will see free ke number, you have it in the exam, right? Because yes, when you apply the theory, it's lengthy, but otherwise from the tricks, so it's just 1 second work, right? So you have, let's say O2. This is how many electrons you have. 68 into 2 electrons, 16 electron. For 16 electron, it is going to be 2 here. Or even if you don't see this, 14 it is 3, 15 it will be 2.5, 16 it will be 2. That's why you have double bond. O2 positive, this is 16 minus 1, that is 15 electron, that means 2.5. Then O2 negative, it will be 16 plus 1, that is 17, that will be 1.5. Isn't it? Whatsoever, down you talk about CN. Ma'am, what about CN? Carbon is 6, nitrogen is 7, 6 to 14, that is 15. 15 is nothing but that is 15 is 2.5. Okay, got it? Tell me, any problem here? Any problem here, bachcho? Any problem? Any problem, everybody? Do let me know in the chat box if there is any problem here. Right? I can't see your chats. Here it is. Yes, everybody? Any problem over here? Right? Yes? How many marks expecting if we listen? Yeah, you can easily expect around 40 plus marks easily you can expect from this lecture, right? Okay, done. Matlab inorganic chemistry complete I'll do na, so you can easily expect 40 plus marks least, right? Okay. Now then, ma'am, what about, ma'am, if I want to calculate the paramagnetic, diamagnetic? See, paramagnetic means you should have an unpaired electron. So for example, let's see, ma'am, if I want to have, I'll just put it here, when you will calculate paramagnetic, diamagnetic with proper method, let's say you have O2. Let's say you have O2 that has 16 electrons, that is having 16 electrons, right? Now 16 electrons mean 2 1 2 1. Now 16 minus 8, because 8 electrons will belong to sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. So I'll just directly subtract it here. It will give you 8 electrons here. So 8 electrons will be 1 2 3 4 5 6 7 8. Okay, you can say this is paramagnetic. Why? Because it has unpaired electrons. Let's say, ma'am, I have, acha, it was, wait a minute. It was less than 14, na? Huh. More than 14, I should have written it here. Ulta, I have done. What to do? I'll just go back. Okay. Okay. This we will not put here. We'll put this here. Okay. O2 is 16 electrons. 16 electrons means you will have 16 minus 8, that is 8 electrons. So it will be 1, 2, 3, 4, 5, 6, 7, 8. So this is paramagnetic, right? This is paramagnetic, that you will know. And where it is paramagnetic? This is paramagnetic in these two orbitals. It is paramagnetic. Okay, this is the first thing that you must know, right, everybody? This is the first thing. Ma'am, didn't understand. See, very simple. If you have, when you calculate the number of electrons, if the number of electrons are less than or equal to 14, it will be 2 1 2 1 2 1 2 1. If it is more than 14, it will be 1 2 1 2. Okay, before this 2 1 2 1 1 2 2 2, what is this? Okay, there is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Here it is sigma 1s, sigma star. That's why I'm not including it, because it is same. It will always have 8 electron. Always it will have 8 electron. That's why I'm only focusing on this thing. 1 2 2 1 is for more than 14. 2 1 2 1 is for less than 14. Tell me, is that clear? Right? Okay. Okay, definitely I'll tell you after the class what you need to do. Right? I have that thing already prepared for you. Right? Okay, tell me. Okay? Tell me. Is that clear? Acha, what about N2? N2 has, let's say, 14 electrons. 14 minus 8. Ma'am, why you are subtracting 8 electron always? Because I want to subtract the sigma 1s, sigma star 1s, sigma 2s, sigma star 2s from here. So it will be 14 minus 8, that is 6 electrons. So it will be 1 2 3 4 5 6. So definitely it is diamagnetic, no unpaired electron. Do you get it? How do we solve it properly from the method? Okay, I just don't want to give you the trick, because sometimes they ask you in what orbitals you have unpaired electrons. For that though, you have to apply this method. But if they simply ask you whether this is para or di, for that we have a trick. Okay, right? Okay. Chalo. Now let's see this. Ma'am, what if, ma'am, I want to know it directly from the trick? Then what I have to do? Very simple. Odd number of electrons, para, right? Odd, even odd, so you know na what is even odd, right? Odd number of electrons, para, even number of electrons, di. So simple. But in this case, if you have 10 electrons like boron, or you have 16 electrons, even though they are even, but still they will have para. That's it. That's the exception. Okay, what exception? It's actually not a rule that I'm saying exception. That means whenever you apply this trick, you have to remember this thing, right? Okay. Example is, let's say O2 2 negative, it has 18 electron. 18 electron means what? Tell me. 18 electron, ma'am. Even, ma'am. Even will be diamagnetic. Right? Even means diamagnetic. You don't have to do anything else. Boron, boron, boron. Hydrogen, helium, lithium, beryllium, boron. Boron is 5. 5 into 2, 10. 10 electrons. But boron is the exception. Even though it is even, but it will be para. It will be para. Right? Nitrogen has 14 electron. Nitrogen positive will have 1 minus electron, that is 13. 13 means odd, it will be para. 13 means odd, it will be para. Oxygen has 16 electron, it is even. Even should be diamagnetic. Even should be diamagnetic, but because it is 16, that is why it is para. Tell me, any problem? N2 is 1221. N2 is 1221. 1221 nahi beta, it is equal na when you have N2. Wait a minute. See, if you talk about less than or equal to 14, it is 2121. See, N2 is in 2121. Okay, equal to 14 is also under the category of 2121. Okay, equal to 14 is also under this category. Okay, tell me beta. I am going to cover all the chapters. Okay, okay. Tell me, is there any problem in what we have done? I see some of you asking, ma'am, oxygen group is exceptions. Oxygen group is the exception. Which case you're asking oxygen? This one, yes. This one here, 10 and 16 electron, even though they are even, that will be para. Right? Okay. Santosh, what do you want me to do today? Hana? Should I give you some kind of magic powder? Like I'll throw it at you. Completed inorganic, guys, in 1 hour. Inorganic completed, guys. You'll be like, ma'am, really, ma'am? Yes, I'll complete inorganic in just 1 hour. Yes, ma'am. Yes, ma'am. It's done, ma'am. And after that, in the exam, you will, oh, ma'am to said inorganic can be done in 1 hour, but I can't do it. Oh, ma'am lied to me. And then you will literally, I don't know what all you will how you will remember me after that. I don't want you to remember me like that, no? That, oh, ma'am completed inorganic in just 2 hours. And how ma'am completed? Chak, 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 chak. Right? So if you want to do things in detail, don't ask me when the session will end. Just be thankful that ma'am is here. Even my Christmas is there, but I am not celebrating Christmas. I am here with you, na? So you should be thankful for that. Right? Done? Yes. Chalo. Done, done. Yes. Now let's see what is the number of unpaired electron in the highest occupied molecular orbital of the species. Now in this case, they are asking you number of unpaired electron. That you can't answer by tricks. Okay. So for this, you have to answer it with the help of MOT only. See how do I answer that. Pehle to, let's say N2. Let's say N2 negative it is it? No, it is N2 positive. This is O2. This is O2 positive. N2 you have 14 electrons. N2 positive you have 14 minus 1, 13. O2 you have 16 electrons. This you have 16 minus 1, 15 electrons. Right? Now, in case of when you have 14 or less than 14 electrons, it is 2121, right? And here it will be 1221. More than 14 will be 1221. Okay? Now let's see how do you write it. 2121, 21. Wait a minute. 2121, 1, 2, 2, 1, 1, 2, 2, 1. Now just fill the electrons. 14 minus 8 electron is in kk. So that means sigma 1 is sigma star 1 is sigma 2 is sigma star 2 is. So it will be 6 electrons, 1, 2, 3, 4, 5, 6. Here it is 13 minus 8, that is 5. Still 1, 2, 3, 4, 5. This is definitely paramagnetic, right? So here it is 16 minus 8, that means how many electrons? It is 8 electrons. So it is 1, 2, 3, 4, 5, 6, 7, 8. Here it is 15 minus 8, that is 7 electrons, that is 1, 2, 3, 4, 5, 6 and 7. Can you see now where you have unpaired electrons? You have unpaired electron here. So first one is number of unpaired electron is 0. Here number of unpaired electron is 1. Here number of unpaired electron is 2, right? Here number of unpaired electron is 1, like this. Okay, so you can directly write it here. N2 has 0, N2 positive has 1, 0, 1. O2 has 2, this has 1, so answer will be first is the correct answer here. Is that clear? Okay, tell me, is that clear? Have you liked the session, everybody? Let's see how many likes you have made. I think it should be 200 plus likes by now. That's really sad you're not doing that, huh? Very sad, very ungrateful. Very ungrateful. Beta, I have given you one target, huh? Chalo, done? Okay. Perfect, perfect. Chalo, this all we have done, right? Okay. Next is this one where you have consider the given species Cn positive, Cn negative, NO, Cn. Which one of these will have highest bond order? Bond order to directly you calculate, na? See, here only I'll calculate. NO means 7 plus 8, that is 7 to 14, 15 electron. This means 6 plus 7 plus 1, that means 14 electrons. This means 6 plus 7, that is 13 electrons. This means 6 plus 7 minus 1, that is 12 electrons. So this will have 3 bond order. This will have 2.5. When you increase one, that is also decreased by 0.5. When you decrease one, it is also decreased by 0.5. Right? 12 means for, see, 14 you will have 3. 13 you will have 2.5, 12 you will have 2. So answer will be 2. Okay, so answer will be 2. Right, everybody? So answer will be maximum bond order. Which one of these will have highest bond order? It will be Cn, that is 3. Right? Okay, perfect. Already you have answered. Lunch you have not done. I thought you will come before, like after doing the lunch only. You have not done the lunch. Beta, now to I'll give you break after completing chemical bonding. 2-3 topics we are left with. Right? After that, I'll give you the break. Right? Okay? Tell me. Now let's see bond angle. That is, first thing is how do you calculate the bond angle? 2 topics done. Most repeated 2 topics we have done, right? Okay, now let's see bond angle. Firstly, though, we will, this is the conclusion part. Okay, this is all what you have to do for that. Okay, see, hybridization states that if you have, let's say, these are the formulas. Mostly if you have the hybridization, how the angle is going to decrease. If you have sp hybridization, it is going to be 180, sp2 is 120, sp3 is 109, sp3d has 120 and 90 degree angle. Now why ma'am sp3 had 120 and 90 degree angle? It's a simple thing that we do here. 90 degree angle means this bond will have 90 degree, 90 degree, 90 degree with each other. But these three if you see, 1, 2 and this third, they will have 120 degree angle with each other, right? Then octahedral will always have 90° with each other. Okay, if you see 90° will always be there, right? In octahedral too, you always see 90° angle. If you see 90° with this one also 90, this one also 90. Everything has, each atom has 90° angle with each other, right? Then if you have sp2, acha, this is the shapes, na, different shapes. So basically, if you talk about hybridization, that is how angle varies. Usually, you can define for sp, sp2, sp3 that sp has maximum, then sp2, then sp3. Based on this, you can answer. If hybridization is same, let's say hybridization, then it will be defined by bond angle is inversely proportional to number of lone pairs. For example, you have NH3 and you have H2O. Okay? Both have the same hybridization, that is sp3. Now, the one that has more number of lone pair will cause more repulsion. So, its angle will be less. That is why it is like this. Okay? Let's say you have CH4 will have maximum, then you have NH3, then you have H2O which has 2 lone pairs. Right? Okay? Done? If both hybridizations, right, and number of lone pair, now hybridization is also same, lone pair is also same, then what you will do? Then how bond angle will vary? In that case, if both hybridization and number of lone pair are same, for example, you have which example you can take? See, you can take BRF3 and CLF3. Okay? Now, in this case, what is the difference? In this case, both are T shape, both are, we have already calculated it, both are sp3d. We have already done that, right? So, hybridization is same, surrounding atom is same, lone pair are same. That means they belong to the same group. If the lone pair are same, everything is same. Now you will see the electronegativity of the central metal atom. If your central metal atom is more electronegative, that will be having more bond angle. So fluorine, chlorine, bromine. Chlorine has more electronegativity, so it will have more bond angle. Simple, okay? Done, simple. Next is, now hybridization is also same, lone pair is also same, central metal atom are also same. Now the surrounding atom can be different here, right? So you will say bond angle is directly proportional to the size of surrounding atoms. The size of surrounding atoms, more is the size of surrounding atom, more will be the bond angle, right? Because repulsions will be more. Bond angle is directly inversely proportional to electronegativity of the surrounding atoms, right? Is that clear? Tell me everybody if that is clear to all of you or not, right? Okay, done. I'll just give you one example. For example, you have BF3 and BCl3. Now, which will have more bond angle? If you talk about BF3, see, hybridization is same, that is sp2. They have lone pair is same, no lone pair they have, central metal atom is same, surrounding atom is different. So more is the electronegativity of surrounding atom, less will be the bond angle, or more will be the size, more will be the bond angle. Clear everybody? Tell me, is that okay? Okay, that's a very small topic. Okay, some topics are very small yet very important, right everybody? Okay, done. Now let's see this question over here, that is 2024 question, right? So again, this can be answered within seconds. Now who will answer this? Will you try to answer this, any one of you? Will you try to answer this? Cn is more electronegative now, so it will be less, right? Okay, wait a minute. The size is more fluorine, chlorine. Beta nahi. Cl is more electronegative than fluorine. When Cm, acha, here, wait a minute. This is fluorine, chlorine, bromine, right? Bromine is less electronegative. Chlorine is more. Here chlorine is more electronegative. Out of fluorine and chlorine, the fluorine is more electronegative, right? So chlorine is less electronegative. That means here the bond angle will be more. Okay? Chalo. Now let's see correct option. You have BF3, PF3 and CLF3. It looks like same, but they are not same. Okay, we have already done it. BF3 is actually sp2 hybridization. We have done PF3 as well, where it was coming out to be sp3 hybridization. If you remember, here it was lone pair as well, 3, 4, 5, it was like this. CLF3, if you see, 3, chlorine has total 7 electrons na, in the valence, 3 are occupied. So 7 minus 3, you have 2 lone pairs here. Okay, it was sp3d, right? So answer was, this is having 120-degree angle. This is having 109, right? This is having 90 and 120 both. So angle is also decreased here when it is 90, right? So you can see this over here. This is not 109, this will be 107 because it has one lone pair now. Then we know that when there is one lone pair, angle is slightly decreased. 2 lone pair, it is further decreased, right? So you can see this over here. I have to just given you the proper answer here. So BF3 has maximum, then it is PF3, then this. So answer will be C is the correct answer here. Okay? Understood? Just from the hybridization part, you can answer this. This is actually, they are asking you hybridization only, but with the twist of bond angle. Okay? So these kind of question also they ask. Then bacha, there is Drago's rule. Let's understand that. What is Drago's rule? This also they can ask you. You should know what is a Drago's rule. So applied when center metal atom is from third period or below, right? When it is from the third period, actually I'll tell you Drago's rule. Vesto totally I'll be able to explain it once you have done P block, right? But still, chalo, let's see a little bit here. Central metal atom must have at least one lone pair. Surrounding atom has electronegativity. What I'll do now, I'll explain you this in P block only. Okay, when we will do P block, just remember that I have to teach you this. Okay, because this third period, why it is so, all those things, so I'll be able to teach you once we have done a bit of P block as well, right? That means in the starting of P block, I'll teach you this. Okay, okay, I'll just shift, in fact, I'll shift this slide to P block, right? Okay, I'll just shift this slide to P block. Wait a minute. Oh my God. So much, huh? So much to teach you today. Yes, I'll teach you this here, right? Okay, done, right? That we will know, but I want you to understand the proper depth of Drago's rule and how to apply that rule, right? Okay, see. Now let's talk about dipole moment. Again, a very simple question for dipole moment is asked. So for that, just remember, lone pair has no contribution in dipole moment in pure s or p orbital. This is very, very important. Lone pair will have no contribution in the s or p if they are pure s or p orbitals, right? Then lone pair only contributes to dipole moment if placed in hybrid orbitals. If they are like sp or sp3, these kind of hybrid orbitals are there, only then lone pair will participate. Value of lone pair moment is directly proportional to S character. Generally, lone pair moment is greater than the bond pair. And what is dipole moment? That is charge multiplied by distance, right? For a symmetrical molecule, right? When lone pair is 0 and all same terminal atoms are there, then mu net is equals to 0, like you have BF3. ठीक है, for example BF3, in which you have 0 lone pair and all the atoms are symmetrical at 120 degrees. So in this case mu net is going to be 0, right? Okay, now if you see, okay, if you see this particular part here, always remember dipole moment will always go from positive to negative, okay, or atom to lone pair. It will always move like that. Chalo, let's see. This is carbon is positive, this is chlorine is negative, positive, negative. They will make a resultant here, right? And that resultant will be here. That will add on. So mu will not be equals to 0. In this case, you have this mu, right? This mu, and here you have the resultant. Now again mu is not equals to 0 here. Again here from positive to negative, this is also positive to negative, but in this case it is cancelling out, so mu is equals to 0. In this case mu is not equals to 0. In this case mu is not equals to 0. And always remember, in such cases when you have same atom, in such cases firstly you have ortho, then there is meta, then para is 0. Okay, para, which is 0, okay, ortho, meta, and then para. Remember this thing. And here also, if you know how to calculate the hybridization, you'll be able to answer the questions, okay, right? Let's see this, right? Let's see this. Let's see the question over here. Question is, given below are two statements, the dipole moment of this is greater than this. C1, C2 bond lengths. Let's see this question over here, right? Okay. How many slides, ma'am? Are you getting like really scared of that? Don't worry, guys. Don't worry, you don't need to be scared of that. We'll easily be able to do that. Okay? See, given below are two statements, right? Two statements, dipole moment of this is greater than this. So in this case, what is the difference? Here you have conjugation as well. Here this will be double bond, single bond, double bond, and here you only have double bond. So here you have conjugation as well, and because of this conjugation, what will happen, right? If you can see this over here, in this structure, right, you have CH3, CH, 1, 2, 3, wait a minute, 1, CH2, this should be a double bond, right? Okay, so here what can happen? This bond will shift here, this bond will shift here, you will have O negative, this is double bond, this is single bond, this is a positive charge. Here what you have is, you have partial double bond, right? So that is the reason what is happening, more charges and more distance between charges than other compounds, so more dipole moment. If you see this compound over here, in this case this is partially negative, this is partially positive, that's it. But in this case what you will see, there are so many partially negative positive. Here this develops partial positive charge, this is partially negative charge, this is also developing partial positive charge. So you can see this over here. After resonance, the distance is more, 1, 2, 3. The distance is 3 atoms. And here the partial positive and negative charge, if you see this here, the distance is only this much. So distance is less here. Distance here, it will have partial negative. Here it will have partial positive. Distance is more. More the distance, more is the dipole moment. So that is the correct statement here. Right? Okay, that was a very interesting question that they asked in JEE 2025. That's why I have taken this question. Okay, otherwise baki questions are very simple, right? Okay, but this question is very interesting. Then C1 C2 bond length of this is greater than C1 C2 bond length of this. Now what about bond length? See, simple thing is C1 C2, this bond length, this will have partial double bond, right? This will not have any, this will be single bond. So partial double bond will be less. C1C2 bond length is greater, that is false here, right? Because what happens, okay, because C1C2 whenever it has partial double bond, and we know that single bond, then you have partial double bond, then you have double bond, okay, then you have triple bond. So that means definitely partial double bond has less length, so statement second is false. So you can say statement 1 is true and B is false, right everybody? Done. Chalo, last part let's see for chemical bonding, that is hydrogen bonding. Intramolecular hydrogen bonding you have here. See, in intramolecular hydrogen bonding, what you will see here, right? Intramolecular means within the molecule you have. Okay, so in orthonitrophenol, within the molecule you have hydrogen bonding, that is intramolecular. And in intermolecular, between two molecules you have hydrogen bonding. Hydrogen bonding means you have hydrogen that is connected to an electronegative element, and here it is also making a hydrogen bond with the electronegative element, and that electronegative element will be FO on N, fluorine, oxygen or nitrogen. Okay, right everybody, tell me. Understood? Oh. Orthonitrophenol is steam volatile, whereas paranitrophenol is no. Okay? Steam volatile. Orthonitrophenol is steam volatile. Why? Because see, orthonitrophenol, see, it's the same situation when you're so much busy in talking to your best friend that you don't care about anyone else, right? So your bond with other people are not strong, right? So easily with other people you can easily disassociate, right? So here this bond, this molecule does not have good bonds with any other molecule, right? That is why you give it steam, it will volatile, because its hydrogen bond with itself is so strong that it has no interest in making bonds with others. So that is why, because of intramolecular hydrogen bonding present in orthonitrophenol, right, this happens, right? Okay, and that's it for coordination. That's it for chemical bonding. Next will be coordination chemistry, right? Okay everybody, tell. 10 minutes break shall we take? Wow, what a rhyme. 10 minutes break shall we take? Okay, now because there is no dinner time, so I don't want to give you really a very big break, right? But I'll give you very big break. 10 or 15 minutes is fine, but after coordination chemistry, that will be your dinner time, then I will give you a big break, right? Okay, tell me. 10 minutes or 5 minutes? Chalo, before I join back, Arey Baba, tell me. Energy, 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 energy. Energy. 10 p.m. for dinner. Chalo, I'll give you dinner break after completing coordination chemistry. Okay? Reason being, because I do once I start block chemistry, then I can't give you a very big break. Okay? Because chemical and coordination chemistry are little interconnected, right? Then you have the connection of block chemistry throughout. So there, if I give you half an hour break, na, the flow will break. Okay? Chalo. Now, really increasing our hope for getting into IIT, NIT or IIT, etc. Ma'am, thank you. Thank you, Gokul. Thank you so much. Right? So, yes, everybody. Now you have, ma'am, is P block done in this session? Beta, everything will be done. P block, DNF block, periodic classification, everything will be done. Okay? Understood? Chalo. Done, everybody? Yes. Okay, done, done. Great. So I'll now see you all after 10 minutes. Now what's the time? It's 26. I'll see you at 5:40. 5:40 works for everyone. 5:40 p.m. I'll see you all at 5:40 p.m. 5:40 p.m. Right? Class will be resumed. Right? Okay. Where is the timer? Here you have the timer, and hell, I'll start. Right? Okay, so see you all at 5:40 p.m. for the next part. Oh, what happened, ma'am? 5:45. Oh my god, oh my god. 45. How much big breaks you want to take? Chalo, theek hai. I'll give you break. Chalo, 5:45. But 20 minutes break you want to have. Are you sure? Just more 5 minutes. I'll give you break till 9 p.m. Okay, till 9 p.m. you sleep. Okay, I'll give you break till 20th of Jan. You sleep till 20th of Jan. Right? Acha, tell me. चलो ठीक है 30-40 यार देखो enough is यार 45 I'll give you then ठीक है 45 now not more than that now I want to see you all at 45 okay not more than that I'll give you right don't take advantage of my sweetness huh chalo okay so I'll see you all at 45 right sharp 45 I'll be here Hello, 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 hello. Yes, everybody, do let me know if I am clearly visible and audible to all of you or not. And let me just inform the students as well that, wait a minute. Okay, you know what I was watching? Dhurandhar movie review. So, wait a minute. I was actually thinking that I'll watch that, but because of so many sessions, I'm not able to go only. Right? I'm just thinking and thinking and thinking only. So, now, wait a minute. Let me just inform the students. Break over. Let's start coordination chemistry. Okay? Let's start it, everybody. Acha, before going now, I just realized we forgot to do Fajans rule, okay? Even I forgot to write it on my PPT. That is also an important thing. And that is also a very simple thing, okay? So I'll just write it here. Fajans rule. Fajans rule. So what is Fajans rule? Simple thing. Here, Fajans rule says that you have a cation, you have an anion, right? What will happen? This is cation, this is an ion. This will cause interaction, right? And that is the reason, because of that interaction, this anion, the electrons will start distorting here. Distorting means it will be like this, right? Negative, 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 negative charge will start distorting here, right? So that is called as polarization. That will happen in the Fajans rule. Now then, yes, about ionic and covalent. So one thing, polarization and all is there, right? But one thing you need to remember is this thing, covalent character. If they ask you covalent character, right, that depends upon charge on anion or cation. More is the charge, more will be the covalent character, right? Okay, then it is directly proportional to the size of anion and inversely to the size of cation. Okay, just remember this thing. Just remember this thing, right? Just remember this thing. If they ask you any 2 3 comparisons, they do, like NiCl or NiCl, I'm saying NaCl MgCl2, right? If they ask you this becomes Na positive, this is Mg2 positive. So more is the charge on the cation, more will be the covalent character. This will be more covalent, right? Okay, so that's how you answer this. Right? That was a very simple thing that you must remember. It is also very simple, and chances are that they will ask you this, right? Okay, but I am again telling you, bond angle, Fajans rule. Fajans rule is very least. Hydrogen bonding, Fajans rule, like, it's not a very high priority topic, right? But it's very simple. So if they ask, it's not like they have never asked this. They ask you questions from here, but it's not definitely they will ask. Definitely ones are hybridization, MOT. They are definite questions that will be there in your exam, right? So that though you can't even afford to skip. The rest of the topics you yourself saw, very small topics you have. Now in coordination chemistry, who will tell me what are the important topics according to you, right? According to you, what are the important topics that you have in coordination chemistry? First is VBT theory, then there is CFT. Most important, these are super duper important topics, two super duper important topics. Then here are some very small topics that you have. First is IUPAC naming, they can ask you. Then type of ligand, you should know the distribution of type of ligands, what are different types of ligands that you have. Then you should know about, then super duper important topic here is also isomerism. So these three are super duper important topics, right? VBT, CFT and isomerism are super duper hit important topics. IUPAC, type of ligand, or Werner theory. Okay? These are very small topics, and I would not advise you to skip it, right? So I will do these topics in 10 minutes. and this I will do like in 20-25 minutes. I'll devote to each topic, right? Okay, do you understand the distribution? So our target is to complete this chapter by 8:15, right? Okay, ready for the target? Yes, everybody ready for it? Very good. Metal carbonyls, yes, how I can forget that, right? So metal carbonyls, that also we are going to do today, right? Okay, so our target is, bacha, if we are able to complete it by, let's say 8:15, or I would say 8:30 p.m. will also work. If we are able to do this by 8:30 p.m., like a lot of things will be done, right? Okay, then we will be only left with block chemistry, right? Okay, tell me. My idea is we should complete it by 8 p.m., but maximum it can go up to 8:30, right? So let's do that. First is Werner theory. See, Werner theory states that you have two kind of valencies. One is primary, one is secondary valency. Primary valency is nothing, it is oxidation number only. And secondary valency is nothing, it is coordination number. Now, what is oxidation number? What is coordination number? Let's see. Oxidation number is when you take metal as X, when you take this, the charge on the ligand, that is in amine it is 0. And here, always remember, how do you calculate the overall charge? Okay, one more thing I'll tell you. Those who are totally blank in coordination chemistry, let me tell you some important things here. This is called as central metal atom that accepts the electron. This is called as ligand that donates the electron. And this is the one that is outside that square bracket that you have, that is counter ion, right? Achha, one more thing. Take this bracket like this here. Now see this thing. If you have 3 here, then this is going to be plus 3. Always first will be cation, then there will be an ion, whatever, because do you remember we have done this in earlier classes as well. If you have Al3 positive and you have SO4 2 negative, just cross multiply. It will be Al2 SO4 and this will be 3. So when you dissociate it, you write Al, whatever is written here, 3 positive, SO4, whatever is written here, 2 negative. Same thing I am doing here, right? This is 3, so it will be 3 positive. Over here it is 1, so it will be minus 1, right? Okay, this is how you see the charge. Now, how do you calculate the oxidation number? That will be X plus 0. Now, amine is a neutral ligand, plus 0 is equals to plus 3. So, coordination number, oxidation number will be plus 3. That means here the oxidation number is going to be plus 3 here, right? That means primary valency is plus 3 here. And if you talk about the coordination number is the number of donating sites. Okay, coordination number is the number of donating sites. And amine has only one donating site, that is this nitrogen. So one amine has one donating site, 6 amines will have 6 donating sites. So coordination number will be 6 here, right? Okay. Now, how many of you, right? How many of you find it difficult to understand, ma'am, what is oxidation number? Ma'am, how will I get to know amine has only one donating site? Ma'am, who will tell me? Ma'am, who will tell me that amine is having 0 charge? So do you want a chart for that? Everybody spam it in the chat box. Do you want a simple chart? Ma'am, just tell us to remember that. Ma'am, we will do that. Will you tell me? Otherwise, I'll delete that slide if you don't do that. Okay? If you're like, ma'am, we will not do, you show us the chart, we will still not do it. Then there is, if you don't do that chart now, there is no benefit of learning coordination chemistry. Then skip coordination chemistry, right? Okay? If you want to remember coordination chemistry, then this chart you have to remember anyhow. Let's see what is this chart. Okay, what is this chart? Denticity means how many number of donating sites it has, that is denticity. So firstly, I have monodentate ligands. Monodentate means only one donating site, right? So this has nitrogen, this has oxygen is the donating site. Here oxygen is the donating site, right? Here pyridine, nitrogen is the donating site here, right? And here you have nitrogen donating site, bromine, chlorine, fluorine. This is here, and nitrogen is here, fluorine. So all of them has only one donating site. That is why they are called as monodentate. One donor atom, only one donating site, right? You talk about these are also monodentate, these are bidentate. Bidentate means they have two donating sites. Bidentate means two donor atoms. How, ma'am, two donor atoms? Let me just show you this thing here. Two donor atoms of like this, you have ethylene diamine, that is called as En, right? Here this is ethylene, that is why it is CH2 234 hai na. So diamines means NH2 NH2. Now this is the ethylene diamine. It has two donating sites. First is this nitrogen, other is this nitrogen. These are the two donating sites to the metal. In case of oxalato also, you have two donating sites. First is this O negative, other is this O negative. That donates it to the metal, right? Okay, that is bidentate ligand. Is that clear? Is that clear, everybody? Do let me know in the chat box. That is bidentate ligands. So all the ligands that are written over here, this, they are bidentate ligands, right? Okay. I'll just mention some of the very repeated ligands that you have. First is this one. It's like too much. You have to do all of them, but these are repeated ligands, okay? Then all the halogens that you have, these are quite repeated. This is also repeated. Then here you have SCN is also repeated. EN is so highly repeated. Carbonato is also repeated. Oxalato is also highly repeated. So these are some of the very repeated ligands that you have, right? So denticity, you will get to know about whether it's monodentate, bidentate, tridentate, tetradentate, pentadentate, hexadentate, right? That you will get to know from here. And you know, there is one more thing, that is you have EDTA. Acha, tell me one thing. If you have ethylene diamine, ethylene means CH2CH2, diamine means NH2NH2, tetraacetate means replace all the hydrogen with acetate groups. That is ethylene diamine tetraacetate. Now let's say you don't have acetate, you have COH here. Now how many? This is EDTA with zero charge. Tell me how many donating sites it has. This is itself a question, okay? How many donating sites it has? Donating sites are two, this nitrogen and this nitrogen. If I say this is -1 charge, let's replace one hydrogen with -1. It has 1, 2, 3 donating sites. Then let's say you replace it with -2 charge. So let's say this hydrogen is also converted to acetate group. So it has 1, 2, 3, 4 donating sites. Let's say you replace this also with -3, then you have 1, 2, 3, 4, and this will be -3 means this is also O negative. 3, 4, 5. Let's say you have EDTA -4, right? Then it will be 1, 2, 3, 4, 5, and this is also 6. So EDTA, the charge will define whether it's bidentate, tridentate, tetradentate, pentadentate, or hexadentate. Okay, understood now? Shall I write it here? EDTA, when it is simple, it has bidentate. EDTA -1 is tridentate. EDTA -2 is tetradentate. EDTA -3 is, I just told you, pentadentate. EDTA -4 is hexadentate. Acha, if they have not given you the charge, they just directly give you ethylene diamine tetraacetate. Acetate matlab they are talking about iron only. Okay, they are talking about all of them are acetate ions. So that means they are talking about EDTA -4, right? Okay, got it? Understood now? These many examples are sufficient for you. And then you must know the charge, okay? Neutral ligands. For oxidation state, you must know the charge. Which of them, which are like ammonia, water, carbon monoxide, pyridine, they are neutral. These all have -1 charge, right? Then they are -1, these all have -1 charge. Then bidentate neutral ligands are these, -2 charge are these. Okay, so this list you must know. Right, everybody? Tell me, is that clear? Is that clear? That's how you will find the oxidation state and that. Now, another thing that is very simple thing based on what they ask you the question is they will give you that this is the molecule and this gives you 3 mole of AgCl. This 3 mole of AgCl simply means that in this case, what you have 3 Cl outside. 3 Cl outside. That means how many ammonia are inside? 6. So this is cobalt, 6 ammonia inside and 3 Cl outside. 2 mole of AgCl means 2 mole of Cl are outside. 2 Cl are outside. 5 ammonia are inside. 5 ammonia are inside and 1 Cl is also there. So out of 3 Cl, 2 Cl are outside, 1 Cl is inside. Okay. Then beta, you have this thing. In this case, what you have? 1 mole Cl outside. Others are CO, this is NH3, right? How many of them? 4 and 2 Cl. So this is the compound. 1 AgCl again, this is also 1 AgCl outside, this is the same thing. Acha, can you tell me why the color is different? Who will tell me? This we will learn in the concept of isomerism, right? You don't need to write the notes, that we will do, right? I will provide you with the notes, just go through them. See, both of them has same molecular formula, but the color is different. That means they both are isomer of each other. Okay, so this we will understand in isomerism. How can two same molecular formula have different colors? How they can have different properties, right? Because simply because that they are isomers of each other, right? Okay, then that is done. Okay, same thing, this is also the same thing. Here you have no mole outside, right? In that case, that will be 0 mole outside. This is CO, no Cl outside. It will be NH3 thrice, Cl thrice. Okay, so that is how you answer it. Now let's see a question based on that. What kind of question they ask you from here? This is JEE 2025 question. Okay, based on this very simple concept, right? How they ask you the question here. Let's see that, right? Let's see that. So if you see this over here, 1 mole of octahedral complex compound, that is, this gives 3 moles of ions on dissociation in water. 3 moles of ions they are giving. That means 3 moles means some 2 are outside, 1 is this. It's the situation is like this. That's how it can give you 3 moles. 1 mole of the same complex react with excess of this to yield 2 mole of AgCl. That means 2 Cl are outside. So this is the formula. This is cobalt, NH3, this is 5 and 1 Cl outside. Such a simple question, right? The structure of the complex is what? What? I mean, such a simple question, right? In 2025, they have asked you this, right? So answer is, first is the correct answer here. Is there any problem here? Everybody tell me in the chat box if there is any problem over here. Right? Denticity and all I have told you already. Then guys, there are ambidentate ligands and flexidentate ligands. Let's talk about that. What are ambidentate ligands? See, bidentate ligands have 2 donating sites. So they will be donating from both the donating site at one point. Ambidentate ligands are, beta, inorganic is going on, asking me organic in between. I'll teach that, don't worry. So, ambidentate ligands have 2 donating sites but at one point only one donating site they are using, right? That is ambidentate. For example, you have let's say NO2, yeah, NO you can have nitrogen donating, here oxygen is donating. For example, you have this thing, sulfur can donate or carbon can also donate. Sorry, nitrogen can also donate, right? So two donating side, they are using only one out of it, right? Flexidentate ligands are ligands having two or more donor atoms. This is less used, this is more used. Two or more donor atoms coordinate with metal atom either through one donor atom forming non-chelate complex or through two donor atom forming chelate complex. So basically flexidentate, they are flexible. Ligands having two or more donor atoms, they should have coordinate with metal atom either through one donor atom forming non-chelate complex or through two donor atoms forming a chelate complex. For example, you have a metal, right? There are some ligands here. Okay, that ligand, if it is having two donor atoms, either it can make non-chelate complex like this, it can donate from one side, then also it can delete from one side, or it can form a chelate complex by donating from both the sides. That means it can, this ligand that has more than one donor sites, it can either donate from one side or it can donate from both the sides. In ambidentate, it is final that it has two donor sides and it will use only one. In flexidentate, it's like today I'll use two sides, today I'll use one side. It is flexible, right? That today I'm lazy, so I'll use one side. Okay, so it is flexidentate ligands, right? Usually ambidentate ligands are asked, but I told you flexidentate also, you know, they can ask you the definition and all. Chelation is when you have a ligand which forms a ring, like you have oxalato ligand that is forming a ring. Can you see it is forming 1 2 3 4 5 1 2 3 4 5 5 membered ring it is forming, right? So that is called as chelation, when it is forming a chelate complex. Similarly, you have metal, you have ethylene diamine, you have carbon carbon, here you have nitrogen nitrogen, that also forms a chelate ring. Okay, so bidentate ligands and like the one that have more than two donating sites or two donating sites can form chelates that are more stable. A chelate is a type of complex compound where a central atom is bonded to large organic molecules and a ligand forming a ring-like structure. Ring-like structure is formed that gives it more stability, right? Okay, done? Done, everybody? They have done it. Yes, they are doing it. Acha. Tell me now, IUPAC naming, let's talk about that. Okay, let's talk about IUPAC naming, right? Okay. So if I talk about IUPAC naming, there are some rules that I'll teach you. After that, I'll give you 3-4 examples for that. Okay, so each rule, please see it very carefully. The cation is named first, both positively and negatively charged coordination entities. So even if you have coordination entity like this, and here you have the counter ion, this is positive, this is negative, or you have firstly the counter ion and here is the coordination entity, this is positive, this is negative. Always the cation part will be named as first, right? Because we always name sodium chloride. We don't write chloride sodium, we write sodium chloride. So it is by convention we write cation first and then anions, right? Then second is the ligands are named in alphabetical order before the name of the central atom, right? Ligands are named in alphabetical order. For example, now those who are asking, ma'am, how do I know the names? Beta, names are also written here. NH3 amine, this is aqua, water is aqua, this is carbonyl, bromido, chlorido, this all is written here. Okay, all the names I have already written here, right? That is useful for you, right? Okay, so what you will see, for example, you have a compound which has amine and that also has aqua. Okay, that metal you have. Now amine starts from Am, AMMINE. Aqua is AQUA. Both are starting from AA. Don't write tri and tri. Don't include TT here. Okay, when I am doing alphabetical, I'll just see which one is before. A will cancel. This is M and this is Q. So M is before Q. So you will write amine first and then you will write aqua. Okay. Now you will write that here you have 3 amines. So you will write triamine. Right. Here you have 3 aqua. So you will write tri-aqua. Okay, that's how you're going to write it. Next is names of ionic ligands always end with O, right? You can see this over here. Names of ionic ligands here are always ending with O. Azido, bromido, chlorido, cyanido, fluorido, right? All are ending with O, right? You see this here. Hydroxido, nitrito, thiocyanato. So all of them are ending with O, right? Okay, so that you must know. Names of anionic ligands end with O, right? Those neutral and cationic ligand as such, they don't have any name. Aqua for water, simple. Amine for NH3, carbonyl from CO, nitrosyl for NO, right? Simple, right? These are, right? Then let's see. Prefixes, we write mono we don't write, we write tri, tetra, then you have penta, hexa, number of ligands to represent number of ligands, right? But if you have a name like you have ethylene, diamine, ethylene 1, 2, diamine. In this diamine, M will be single. In simple ammonia, amine will be double M, right? Now, can you see in the name of the ligand itself, you have di. So if you put di here as well, or you put tri here as well, that will not work here. So in those ligands which already has di and tri, you will write bis, tris. So answer will be bis, tris, tetrakis, pentakis. So that will be, that is the one name that you will use, right? Tris, tetrakis, pentakis, bis and tris you will use maximum, right? Okay. Then oxidation state of metal in the cation, if you talk about metal in the cation, that you will represent, for example, oxidation state is coming out to be 3. So that is how you will represent it, 4, 5, 2. So it will be represented in Roman language, okay? Roman numerals. Then you have, very important, if the complex means this complex, the one that is written in the bracket form. If this particular entity is positive, the name of the metal will be simple. Like for cobalt, it is cobalt, chromium, it is chromium, iron, it is iron, silver, it is silver, same, simple. But if you have negative here, if you have this particular entity is negative, then the metal name will be changed and you will have 8 as the suffix here. How, ma'am? How the name will change? For example, in this case, I'll just write it here. For example, Fe will be ferrate. Okay. Ag will be argentate. These are some important, right? Because if you have a cation as a coordination entity, this is written as iron, this is written as silver, right? Then other two things simple, like chromium, you write simply it is as chromium. If it is in the negative entity, then it will be written as chromate, right? Cobaltate. For cobalt, it will be cobaltate. For nickel, it will be nickelate. Nickelate. Okay, tell me. Any problem? Right? Okay. Tell me guys, any problem? Let's see how many likes you have made. Let's see how many. I think it should be 250 plus by now. Let's see. Let's see, let's see, let's see. Oh, still not completed with the target. Let's do that, guys. Let's do that. Okay, let's make the likes 300 plus by the end of this, not end of this session, by the end of coordination chemistry. Understood? Now the neutral complex molecule is named similar to that of complex cation. Let's see how to apply these things, right? How do I apply these things? Simple examples I'll be giving you here. Simple examples, how I will apply this. This is, see, first thing is, this is 3. So here it will be minus 3. This is 1. So here it will be plus 1, right? Cation is named, my bad. This is 3 now, so the cation is firstly, then this is an ion. This will be minus 1. Similarly here, there we will do after this. Here, cation you have, whenever you name the cation first, right? So I'll name this coordination bracket first. In coordination bracket, I'll name the ligands first. Ligand I have amine Am, aqua Aq. So obviously amine will be written first. So I'll write triamine, triaqua, triamine, triaqua, right? Then chromium will not be written as chromate. Why? Because the coordination entity where the metal ion is, it's a cation. So that is why it will be directly written as what? Everybody tell me. It will be directly, wait a minute. Yes, it will be directly written as chromium. How do you answer the oxidation state, ma'am? See, this is x plus 0 plus 0. This is equals to plus 3, right? So it is equals to, x is equals to plus 3. So that is going to be the answer here, isn't it? Yes, everybody, x is equals to plus 3 is going to be the answer, right? Okay, so oxidation state is plus 3 here, that is 3. And then you write the counter ion, that is simple chloride, sulfate. Simply like an anion, you will write chloride. Okay, now let's talk about this one. Here you have this thing. Here it is 3, so it will be written as plus 3. Here it is 2, so it will be written as minus 2, right? Now, when you write the coordination entity, firstly write the ligands here. Ligand is, what is this? Can you guess what is this? CH2, CH2, NH2. Ethylene diamine. And ethylene diamine itself has di. So you will write tris here. So that's why it is written as tris. 3, it is 3 times ethylene diamine. So it is tris ethane 1,2 diamine. That will be written in brackets. Why? Because you have written tris. You want to separate this thing, so that's why these ligands which already have tris, di or tri, they are written in brackets. Okay, so here it is tris ethylene diamine or ethane 1,2 diamine. Cobalt, simple. Oxidation state here will be x plus 0 for ethylene diamine is equals to plus 3. So 3 is the oxidation state and this is sulfate. So simply it is written as sulfate. What about this one? See, what about this one? See, what about this one? Simple thing is, here if this is plus 1, because now silver wait a minute. Good evening, very good evening, very good evening. See, if you have this thing, if I say this is plus 1, so this is plus 1 plus 0 is equals to plus 1, so overall charge is plus 1. So overall write it plus 1 here. Here it is plus 1 minus 2, that is minus 1, overall it is minus 1. That means the silver here is plus 1, the silver here is also plus 1, that is the oxidation state. Firstly, I will write the cationic coordination entity. Ligand is NH3, it is diamine. Diamine, because the silver is in the cationic entity. It is simple silver and then the oxidation state. Here it is anionic entity. It is dicyanide. For CN it is cyano or cyanido you can write. This Ag is not written as silver. It is written as argentate. Why? Because again I told you just here, again I wrote all the very important and famous metals here. I have already written. Whenever they are in the negative coordination entity, you have to write it this way. Okay? Tell me if any problem you have over here. IUPAC naming, like, it was very difficult to select few examples, right? But I have selected those examples where, you know, all the things we can learn. So that's why I taught you firstly the rules and then the examples, right? Okay, tell me, clear everybody? Any problem here? Any problem? Now we are going to start VBT theory. VBT, valence bond theory, right? Okay, right? Tell me, tell me, tell me, tell me, tell me. Let's start with VBT theory. What is VBT theory? Three main important topics now we are left with. Four actually. VBT, CFT, isomerism, and then metal carbonyls. Right? Okay, let's see that. I'll also teach you EN, effective atomic number, because that is also simple only. It's not a big deal to calculate EN. That is in your syllabus. Okay, वैसे तो EN is a very big topic, right? But in your syllabus, you don't have that much advanced, right? In JEE advanced, definitely it is advanced thing, right? But till JEE means you don't, if they ask you EN also, right? That they will ask very simple question on that. Okay? See, valence bond theory. Ma'am, we have done it. See, now all those students who were getting confused in chemical bonding, ma'am, square planar, ma'am, DSP2. Relax, we are going to do it here, right? So square planar, everything will do it here. This theory is basically will talk about the hybridization. What are the steps to follow? What are the steps to follow? Steps will be, firstly you will write the firstly you will calculate the oxidation number, right? That you know how to calculate. Then you will write the electronic configuration, that I'll tell you. Electronic configuration, this you must know. Okay? Then I'll teach you the two things. One is whether there will be pairing or no pairing. Pairing or no pairing. From that you will identify the, from this you will identify the hybridization. Okay? Now firstly tell me, do you know how to calculate the oxidation number? Yes, everybody. Do you know how to calculate the oxidation number? Yes, everybody. अरे बिल्कुल बिल्कुल will do that, don't worry. Advance के लिए भी will do that, बिल्कुल कराएंगे, right? Okay? But right now focus on JEE, means you're just 20-25 days left, right? Try, see, I'll give you a simple thing. You are already preparing for advance by preparing for JEE means now. Ma'am, how, what is the logic? Simple logic is, if you guys are thinking, I want to crack attempt 1, you're already ahead of so many students out there. They have given up. They are like, attempt 2 is there, I'll do that. Acha, attempt 2, if you are already like attempt 1, I will not give, or I will not give it wholeheartedly. You will give attempt 2 with full dedication, right? Now you don't have any, you know, gap between these two. So either to you prepare for JEE Advanced now, or right now crack attempt 1 with 99.9 percentile and then prepare for JEE Advanced. That is the best thing that you can do. Because in JEE means you're already boards, so already it is getting completed, while this all is boards only. Now pre-board, board, everything is covered in this session, right? So JEE means prepare for that, attempt 1, right? Now see, I'll teach you electronic configuration. Okay? How many of you get confused in electronic configuration? Here I'm teaching you electronic configuration of 3D elements. Electronic configuration of 3D elements. Of 3D elements, right? 3D elements. Let's see here, how do you answer that? Yes, everybody. So for 3D elements, how do you write it? It is Sakti Karman Fiko. Oh, so I'll just start from here. Tiv Karman Fiko Niku Jan. Okay, this is what you have. This is what you have, right? Okay, now you will just write it this thing here. You will just write it this way here. Just write it this way here. Write 4s 3D 3D here, simple way. Write 4s 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 4s. Write 3D 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 3D. Ma'am, what you're doing? I'll tell you what I'm doing. Right? Achha, do you know what is atomic number here? Atomic number is from 21 to 30. This is a 3D. We'll see this in block chemistry. Beta, if you know this electronic configuration, your questions of wait a minute. Your questions of organic, your questions of VBT, your questions of magnetic moment, your questions of CFT are already your questions based on this electrode potential, ionization enthalpy of 3D, all are already sorted. Wait a minute. I think I should not. I will take little bit rest in between. See, 27, 28, 29 and 30, right? So just write 2, 1, 2, 2, 23, just skip 24. Instead of 24, write, because here what happens now, you write 4s to 24, but to have half filled d orbital, it becomes 4s1 and 3d5. Okay? This is the exception. This is the exception. So I'll write the exception with a different pen. That is 4s1 3d5, or I'll just write it with the red pen. This is 4s1 3d5. Okay, then again it is 25, 26, 27, 28. Now copper is also the exception, so instead of 210 29, you write it 110, because you want fully filled d orbitals, right? Then in the end, so you have 30, that is zinc, you have 2 here and 10 electrons here. That is the electronic configuration. Okay, this you must know, right? Okay, yes. Like option NTG is there. This option that is ask with any doubt, you click on that, you will get the option for the PDF, right? Or the doubt as well as the quizzes, right? Okay, understood? So this is what you will have here, right? Now I'll just tell you, this is the proper chart and all. This you don't have to remember as such, because that they will not, but still I have just given you this. But what you have to remember is this thing. Coordination number 4 and 6 are in your syllabus. This is what they ask you. If coordination number is 4, either it can be sp3 or it can be dsp2. If coordination number is 6, it can be sp3d2 or it can be d2sp3. See, if it is sp3, it is going to be tetrahedral. dsp2, it is going to be square planar. Both of them has octahedral geometry, right? Okay, now one by one, let's see how to find that which one will be what, right? Which one will be what. But before that, just see if you have magnetic moment. If you have magnetic moment, for the magnetic moment, you will simply say, if you have all paired electron, that is diamagnetic. If you have unpaired electron, even one unpaired electron, that will be paramagnetic. The official magnetic moment formula is mu is equals to under root n plus 2, but we are not going to use that, right? You must know the formula, right? But we are not going to use that. If your number of unpaired electron is 1, it is going to be 1.7. If it is 2, it is 2.8. If it is 3, it is 3.8. If it is 4, it is 4.9. If it is 5, it is 5.9. Okay, so that's how you're going to write the magnetic moment, which directly you can know from the number of unpaired electrons. You don't need to calculate it this way. 1 1.7, 2 2.8, 3 3.8, 4 4.9, 5 5.9 directly. Okay, it will like ease a lot of things for you. Now let's see this nickel cobalt 4, cobalt I'm saying nickel carbonyl 4. How do you answer this? See, firstly calculate the oxidation number. X carbonyl is 0. This is going to be overall, it is 0. So X is going to be 0. It is nickel. Write down the oxidation electronic configuration. It is 28. It is 4s2 3d8. Right. So outermost electrons are 10 electrons. Right. And here what you will have, always write down firstly D. Right. 1, 2, 3, 4. This is 5. Okay. This is S and this is P. Now always remember, in this case, all you need to have is empty d orbitals. Ligands will donate to the empty orbital, not d orbitals, empty orbitals you need, right? Now here you have 10 electrons, and see, you also need to understand which one will be strong field, which one will be weak field. Abhi to na, I'll just tell you the strong field and weak field here. But in the end, after doing CFT, you know, I'll tell you a fun fact here. In reality, VBT theory was not given for this purpose. In reality, what happened in the experiment? Firstly, they experimented that this is para, this is di. Based on that, they understood if it is diamagnetic, that means all electrons are paired. That means pairing is happening. For paramagnetic means pairing is not happening, right? That's how they told you this, right? Wait a minute. Let me just see if exceptions are written here or not. I think exceptions are not written here. I'll have to take that over here. By that time, can you please, Vita, just give me a second. I think I'll have to take out the exceptions from my another PPT. I think I skipped it by mistake. Okay, just give me a second. Just give me a second. By the time, just tell me, will there be any pairing here or not? Will there be any pairing here or not? Right? Tell me, everybody. Oh. Yes. So this is the page that I want to take a snip. Wait a minute. And this is another page that I want to take a snip. Okay. Right, wait a minute. So I'll just take 2 snips here, right, that are very important for you, right? Very important 2 things, right? Made with a lot of love and hard work. See, wait a minute. Okay, so wait a minute. I'll just import that. This is the first thing, right? Like which one will be paired and not paired, and then you have this thing, right? Okay, this will make it very easy for you to remember the exceptions as well, right? This is the exceptions case, right? See, so I'll tell you what is the interesting part here. The interesting part is VBT theory didn't give us any strong field, weak field ligand. VBT theory never gave us strong field and weak field. Why this is red, red? Achha. Okay. So VBT theory never gave you weak field or strong field. This is from the CFT. We applied it here in VBT. Actual VBT theory didn't give you the answer why this is paramagnetic, why this is diamagnetic, how many unpaired electron. This VBT theory never gave us. But we solve it in such a manner that we answer paramagnetic, diamagnetic as well. In reality, they gave us para, they firstly experimented, oh, this is para, this is di. According to they decided whether pairing will happen or not. But after the discovery of CFT, we know that strong field ligand cause pairing and weak field does not cause pairing, and we apply it here and then we answer whether it will be para or di, which was originally from the experiment that was calculated. Okay, so that thing is important for you. So strong field ligands are like ammonia, NH3, En, Cn negative, CO. NH3 na, it is always in that confusion state only. Ammonia is, I'll tell you where it behaves as strong field, right? So they always behave as weak field, and here are some exceptions for that. If you talk about cobalt 3 positive bonded with H2O and oxalate, then it is acting as strong. Usually it is weak field, but with but if it is bonded with cobalt 3 positive, it is strong field ligand. Similarly, water is a weak field ligand, but with Cu2 positive, it is strong field ligand. Similarly, nickel 4 positive, it makes fluoride ion also a strong field ligand, which is originally a weak field ligand. So ammonia with cobalt 3 and iron 3, it is strong field ligand, but with iron 2 positive and Mn 2 positive, it is a weak field ligand. Here it is a strong field ligand, right? Then always remember 4D and 5D elements, no matter you have strong field, weak field, they will always behave as strong only. Okay, always, any ligand you have, they will always behave as strong field. Okay, so that is very, very important thing. Right, everybody, tell me. Okay, I'm not able to see your chats. Is there any lag or anything, guys? हाँ, ठीक है. Kota factory, yes, I have watched it, right? We'll discuss about that after your exams, right? I know what you are actually trying to say, ma'am. Exceptions. Yes, I do remember that. Kota factory, huh? Chalo. Now 10 electrons you have here, okay? CO will behave as a strong field ligand here, right? So that is the reason pairing will happen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now you need, for coordination number 4, you need 4 orbitals that are empty. So that is why it is sp3 hybridization. That is the reason it is tetrahedral in structure, right? And whenever there is no paired electron, no unpaired electron, that is diamagnetic, right? That means n is equals to 0, mu is equals to 0. That means it is spin paired complex. All the spins are paired. You can also say it is spin paired. You can also say it is inner outer. Wait a minute. If you have dsp2, that will be inner na. sp3 complexes are also called as outer complexes. Okay, so this is outer orbital complex. Because see guys, if you have here dsp2 include, for this you need this also empty, that will be inner, right? So that's why dsp2 is inner and this is outer. You can also write it over here that this one is inner, right? This one is outer, sp3 is outer, this is inner, this you're using outer d orbital, this is outer, and here you're using inner d orbital, so that is inner. Okay, that you must also know. Now after this, what you need to do, once you have done it, then outer orbital complex, this all you have, Then you can also write it as it has very low spin. Low spin means when the number of unpaired electrons are very less or zero, that is low spin complex. Okay, everybody, tell me. Now, next one is NiCl4 2 negative. In this case, x minus 4 is equals to minus 2, x is equals to plus 2. So, nickel, its oxidation state is plus 2, its electronic configuration is this. In nickel 2 positive, it is 4s0 3d8, right? So, you have 3d8. What do you write here? You have these orbitals 1, 2, 3, 4. This is S and this is P, right? Now, when you write it here, what it is going to be, this is 8 electrons. So, here it will not cause any pairing. Cl is a weak field ligand. Okay, it will not cause any pairing. So, it is, firstly, you will fill all the degenerate orbitals 1, 2, 3, 4, 5 and 6, 7, 8, right? Tell me what is the hybridization here. Again, it is sp3, right? So you will write it here sp3. That means it is tetrahedral. Tetrahedral, right? Okay. Tell me, everybody. Is that clear? Is that clear? It is tetrahedral. OMG. Guys, oh my God, what just happened? Oh God, blunder. Guys, I am little clumsy. I do these things, right? Okay. No issues. I'll just complete this. After that, I'll just give you 2 minutes break to, wash this off. Right? So it is sp3 and this is tetrahedral. Now tell me, do you find any unpaired electrons here? You have 2 unpaired electrons. That means here mu will be equals to 2.9. Here it is going to be paramagnetic in nature, right? And here it is high spin, because whenever you have unpaired electron, that is called as high spin complex, right? And then after this, what you need to do, high spin, and here it is spin free complex, because all the spins are not paired. You have spin free complex, and this is also inner orbital complex. Okay, so these are all the things that you need to know, every single point here, right? Tell me, guys, if that is clear to all of you. Ma'am, are you okay? No, I am okay. Water bottle, the whole water is now on the floor, right? So that is the problem. I spilled the whole water on the floor. So that's why I don't have space to walk now, right? So, yes. Tell me. Next is this one. Again, x minus 4 is equals to minus 2, x is equals to plus 2. Nickel, which is 4s2 3d8, in its nickel 2 positive state, it will be 3d8, isn't it? Now what you need to do, you just need to fill the electrons here, 1, 2, 3, 4, 5. This is S and this is P. Always remember, in coordination number 4, either it can be dsp2 or it can be sp3. There is no other possibility here, right? So you need to fill 8 electrons, and this is a strong field ligand. So it will be 1, 2, 3, 4, 5, 6, 7, 8. Now who will tell what is the answer? What is the answer? dsp2. It is going to be square planar, right? Now guys, can I say here number of unpaired electron are 0, mu is equals to 0. So this is going to be diamagnetic. Can I say here it is low spin complex? Can I say it is spin paired? All the spins are paired. Spin paired complex. Here, wait a minute. This I have written inner kya? It will be outer here, yaar. Outer here. sp3 is outer. By mistake, I have written inner. Okay? Outer. Inner will be only dsp2. That is inner. Okay? That is inner. Right? Tell me. Any problem? Any problem, guys? Any problem? Done? Now next is you have FeCN6. Again same thing, same funda. X minus 6 is equals to minus 3, so x is equals to plus 3. Iron, that is 4s2 3d6. It Fe3 positive will become 3 electrons you take out. Firstly take out the electrons from 4s and then 3d. So 4s and 3d, it will become 3d5. Okay, this will become 3d5. Now see one thing, when you have 3d5 electrons, so what you have here, this is 1 2 3 4 5, right? This is S and this is P. I'll just do one thing, I'll also write, because I need to have for 6 orbit. Tell me what is the possibility in case of coordination number 6. Either it can be sp2 or it can be sp3d2, or it can be d2sp3. Okay? So if I see here, it is Cn. Cn is a strong field ligand, so it will cause the pairing. So it will be 1 2 3 4 5. Now can you see the answer is d2sp3? After this d2sp3, empty orbitals are these only, so answer will be d2sp3. So it is a inner octahedral complex, right? Number of unpaired electrons are 1. Mu is equals to 1.8, 1.7 here, right? You can say this is paramagnetic. You can say it is spin free complex, because your spin is free as well. You can also write that it is high spin complex, because you have unpaired electron, so it is also called as high spin complex. Tell me guys if that is clear to all of you or not, right? Okay, now last one. Okay, let's see if you can do this or not. Will you do this yourself, everybody? Will you do this yourself, right? By the time I'm just setting whatever I've just done here, right? Okay, will you do this yourself, or do you want me to do this? Tell me. I'll just give you the hint. X minus 6 is equals to minus 3. X is equals to plus 3. So iron, which is 4s2 3d6 oxidation state, in plus 3, it will be 3 electrons you take out, it will be 3d5. Now this is a weak field ligand, there will be no pairing here. What will be the answer, right? Okay, what will be the answer? So you have here, this is D. Tell me everybody, what will be the answer here? Tell me everyone, what will be the answer here? D, 1 2 3 4 5, S, and this is P. This is again drawn D, 1 2 3 4 5. Okay? Now weak field means no pairing. 1 2 3 4 5. So N is equals to 5, mu is equals to 5.9, right? Here it is sp3d2. sp3d2. So that means it is outer octahedral complex. That means you can say it is definitely paramagnetic. It is definitely paramagnetic. You can say it is spin free complex. It is high spin complex. So many spins are there. High, this is so definitely high spin complex. Okay, right everybody? Okay, done. Now it's very difficult to stand here at this point, right? Acha, this is a question. By the time we do the question, let me just handle this part. Okay, this is getting quite irritating for me to stand here. Okay, so do this question, I'll just back in a minute. Hi guys, let me just clean this up because it's really messy over here. The floor is like a swimming pool right now. So I'm just cleaning that up. Just give me a second and solve this question, okay? Whew. Oh god, that was a task, guys. That was really a task. So now you all have seen me uh, doing ghar ke kaam as well. You have seen my jugadu mic as well. So you know, ma'am is full on desi Indian, right? So actually, it was all like water, water everywhere. Even now, after one more break, I'll have to do one more. I have to do mopping again, right? Oh my god, that was crazy. I never expected I'll do that on YouTube. I hope so you didn't see me. Okay, let's see this. So CO, Ni, CO4, we already discussed three of them. These three though we have already discussed, right? NiCO though we have already discussed this. NiCO is sp3, that is tetrahedral, and you can write this over here. NiCO4 is tetrahedral with mu is equals to 0. So it is tetrahedral with mu is equals to 0. This is tetrahedral with mu is equals to what? NiCN4 is tetrahedral with mu is equals, it is DsP2 with mu is equals to 0. This is DsP2 with mu is equals to 0. That is this thing. This is tetrahedral with mu is equals to 2. So this will be what? Manganese. See, manganese, this is x minus 4 is equals to minus 2. So x is equals to plus 2. Manganese is nothing. It is 4s2 3d5. Okay. Now that means manganese 2 positive will be 3d5. So you have 4 orbitals, now 1, 2, 3, 4, 5, and this is S and this is P. If you see this over here, you need to fill 5, and Br is a weak field ligand. So it is 1, 2, 3, 4, 5. So that is why N is equals to 5, mu is equals to 5.9. So that will be this. And here it is going to be sp3. That is, this is going to be 4. So answer is going to be A is 3, A is 3, B is 2, C is 1, and D is 4. So answer is C. And I could see this over here that so many of you did C as the correct answer. Right? Okay. Yes, everybody, tell me. Is that clear? Tell me, everybody, is that clear or not? So that we have done. Let's move ahead here. Let's move ahead here. Now we have, and I'm again telling, don't see the slides. In block chemistry, there will be more slides, right? Because there are so many things I want to teach you. But every slide will take hardly 1 minute, right? So that's why I'm saying don't create that kind of panic here. Focus here. If you don't want to do that, you can go. Okay, I am not forcefully saying to be here. If you want marks, you can be here, right? But don't create panic among other students as well. So many this, so many that, है ना? This is not a movie, right? Okay, that will be finished by like 1 or 2 hours. It's a syllabus that we are doing, right? So first thing, for starting CFT, you must have a knowledge about d orbitals. So dxy, dyz, and dzx, right? dxy, dyz, dzx, they are between the x's. They are between the x's. If you talk about dz square, dx square minus y square, that is along the axis. That is along the axis. And what we will see, that in case of tetrahedral, the energy of this will increase. In case of octahedral, this is in case of tetrahedral, energy of dxy, dyz, and dzx will increase. In case of octahedral, the energy of dx square minus y square and dz square will increase. What is the reason, right? What is the reason behind that? See, if you have octahedral orbitals that are like this, right? These octahedral orbitals are along the axis. That is why any orbital that is along the axis, that will have repulsions, and that is why there will be increase in energy. But in case of tetrahedral, you will not see that. There will be no increase in energy in case of along the axis, but between the axis will have increase in energy, right? Okay, so you can see the octahedral diagram like this. Firstly, all the degenerate orbitals, all the d orbitals are degenerate. Then when the ligand is approaching, they will have high energy. Then once the ligand has approached, there will be splitting of the d orbital, right? Okay, and what you will see, this is Eg, this is called as Eg, and this is called as T2G. T2G means, simply I'll just write here as well, this is a set of T2 and this is a set of E. Whenever we talk about octahedral, we write G for gerate, that means symmetry, right? So here, if you see, what you will see here, from the berry center, you will see the distance will be plus of 3 by 5, and from the berry center till this, the distance will be minus of 2 by 5, right? Okay, now let's see other things related to this. What we have seen, the energy of 2 Eg orbital is increased by 3 by 5, as you can see this here. It is increased by 3 by 5, and 3 T2G orbital is decreased by 2 by 5, right? Now let's see the CFSE here, how to calculate the CFSE here. Okay, that I'll teach you from here. Firstly, so let's see weak field and strong field ligand. Weak field ligand, he says that where this gap is very low, that is weak field. When this gap is very large, that is strong field. Now understand this with the help of a concept. If the gap is very low, right, in that case, if I ask you to go to second floor, you can easily go. But if I ask you to go to 24th floor, you will find it difficult. So you will be like, I don't want to go, I will pair here. So what will happen here, when the CFSE is low, that is weak field, and in that case, no pairing will be there. No pairing will be there, right? In this case, it will have pairing. When CFSE is strong field, CFSE is very high, gap is very high, instead of going up, it will cause pairing only. For example, you have this orbitals now. So instead of going up, it will start 1, 2, 3. Instead of this fourth electron going here, it will pair here, right? That is a case of strong field ligand. So when there is no pairing, if you're not able to purchase something because its price is too high, that's why you're not able to purchase it. Similarly, no pairing. Why you're not able to do any pairing? Because the pairing energy is very high. Too much money you need for pairing, so that's why you don't want to do that, right? Electron will enter Eg orbital and it is high spin, right? It is high spin because no pairing is there, spins will be there, so that is why it is high spin. CFSE is high, pairing is there. Pairing is there means the money for pairing is very less. So P is less than delta, electron will enter T2G, means here this is T2 and this is 1, 2, 3, fourth electron will enter T2G only, right? That is pairing, okay? So it's a low spin complex because pairing is there, so spins will be less, right? Okay, now I'll teach you how to calculate CFSE. Before CFSE, now let's understand this part. I'll just copy paste this 10 times because I want to teach you something very, very, very important. Very, very, very important. How to fill octahedral complexes, high spin and low spin. Okay? Understood everybody? Let's do that. How to fill octahedral complexes, high spin and low spin. So if I talk about D1, whether it's strong field or weak field, you will fill it like this, right? Okay. When it is D2, whether it's strong field or weak field, you will fill it like this. If it is D3, whether it's strong field or weak field, you will fill it like this. There is no difference in that. But if you want to fill D4, for strong field, you will cause the pairing 1, 2, 3, fourth electron will fill here. And for D4 weak field, it will be 1, 2, 3 and 4. Here it will be T2G3 and EG1. Here it was T2G4 and EG0. Can you see with the strong field and weak field how the difference is there, right, in filling the orbitals? In case of D5 strong field, it will be 1, 2, 3, 4, 5 and here it is T2G5 and EG0, right? In case of D5 weak field, it will be 1, 2, 3, 4, 5. It is T2G5, T2G3 and EG2. Next is D6 strong field. So it is going to be 1, 2, 3, 4, 5, 6, right? So that is going to be T2G6 and EG0, right? Okay. Then you have D6 weak field. That is going to be 1, 2, 3, 4, 5 and 6. That is T2G4 and EG2. Then you have D7 strong field. So it is 1, 2, 3, 4, 5, 6 and 7. That means T2G6 and EG1, right? Then you have D7 weak field ho gaya na? D7 weak field. D7 weak field. So it is 1, 2, 3, 4, 5, 6, 7. Can you see this is T2G5 and EG2? Can you see the difference here? Right? But in case of D8, if I talk about D8, whether it's strong field or weak field, it will be 1, 2, 3. If I draw it strong field, it will be, yes, everybody. If I fill it here, 1, 2, 3, 4, 5, 4, 5, 6, 7, 8. It is like this. It is T2G, 6 and EG2. Now let's do it for weak field. It will be 1, 2, 3, 4, 5, 6, 7, 8, right? If you will it for strong field, 1, 2, 3, 4, 5, 6, 7, 8. It is same only, right? It is coming out to be same. Then you have, wait a minute, two more we are left with. That is this and this. ठीक है? नहीं. Wait a minute. Oh. Wait a minute. Okay, D9 and D10 will do, right? D9 and D10. Tell me everybody, what about D9 and D10? How do you fill it? What about D9 and D10? Any one of you? D9 will also have same. Strong field or weak field, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? D10 will also be, whether it's strong field or weak field, it will be same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So all you need to remember in the end is that D1, D2, D3, D8, D9, D10. Whether it's strong field or weak field, they will always have same electronic configuration. Others, it will vary, right? Then let's talk about tetrahedral. In case of tetrahedral, what you have? In this case, dx square minus y square, that means E will be lower in energy and T2 will be higher in energy. Right? Okay. Now, let's see one more thing here, that is, now let's talk about this thing. Okay, I'll give you some examples here, right? Two examples I'll give you. Chalo, two examples I'll give you, right? How to answer this, right? How do I answer this? This is D4, let's say weak field, right? Now what you will do? D4 octahedral, it is 1, 2. D4 means you will have 1, 2, 3, 4. This is T2G, this is EG. T2G is multiplied by minus 0.4, so CFSE, that is delta O, will be 0.4 minus 0.4 multiplied by number of electron in T2G, that is 3, plus 0.6 multiplied by number of electron in EG. Ma'am, what is this N star? Ma'am, what is this N star P? देखो, N star means if you directly write it 1, 2, 3, 4, 5, number of 1, 2, 3, 4. Here you have no unpaired electron, no paired electron. Here also you don't have any paired. N star defines the extra pairing energy that you give. Here also there is no paired here also there is no pairing pair that you have. Here also you don't have any pairing pair, right? So that is why it will be 0. So answer is going to be, you can solve this. This is minus 1.2 plus 0.6, that is minus 0.6 is the correct answer here. Let's talk about if you have D4 strong field. When you write it without any, in the degenerate orbital, when you write it, it will be 1, 2, 3, 4. But when you write it this way, 1, 2, 3, 4, 5, here the number of electrons 1, 2, 3 and 4. Here you have 1 paired, here you have 0 pair. So that means extra N star is going to be 1. Extra 1 pair you are forming, right? Okay, understood now? What is N star, right? So delta O is going to be minus 0.4 into T2G, that is 4, plus EG, how many electrons you have? 0 electrons in EG, 0.4, plus N star is 1, so it is P. So it is minus 1.6 plus P, right? So that is going to be the answer. Tell me. Tell me. It's okay. Ariva, koi baat nahi. Be here just, okay? Tell me. Done na? Understood how to calculate the CFSE? How to calculate the CFSE? Tell me everybody, if there is any problem in that, do let me know. How to calculate CFSE, and that's the same case. Dekho beta, what we have done here, when, see, this so I told you, this so I have taught you how to write, how to fill with strong fill and weak fill. That's why I taught you that, right? Now always this part will be multiplied by 0.4. This part will be multiplied by 0.4, and this part will be multiplied by 0.6. Here it will be 0.6. Okay. This part will be T2 always is multiplied by 0.4, E always is multiplied by 0.6, N star is the extra pair that you have. Here you have 0 pair, here also you have 0 pair. So there is no extra pair. Here you have 0 pair in the simple degenerate d orbitals when you fill D4. But here you have 1 extra pair, and that is because of that 1 pair you have N star is equals to 1, right? Okay. How do you get D4? D4 is the example I have given you. This will be given in the question. Do it for D4, do it for D5. This is just an example. I have solved 2 questions in front of you. Okay? Understood? Tell me everybody. Is that clear? Is there any problem in that? If there is any problem in that, do let me know in the chat box. Now let's see factors affecting. Now as the charge increases, like M3 positive have more than M2 positive, then M positive, as the charge on metal ion increases, the CFSE will increase. Now next thing is, remember that 5D series have more than 4D, then you have 3D series, right? And you know 5D and 4D have that much more, then they always cause pairing, and they usually form low spin complexes. Low spin complexes they form, right? That's why I told you now, 4D and 5D, every ligand will behave like a strong field ligand. Every ligand. Why? Because their CFSA is very high. It doesn't matter whether it's weak field or strong field, it is so high, right? It doesn't matter only whether it's weak field or strong field. Then the nature of the ligand, for this you must remember this spectrochemical series. This is so important. I have also given you an order to remember this particular series, right? This is very important, guys. Very important. Just remember this order as it is, right? Okay, this is the mnemonic. I broke Samantha's clock. She found out, called Harsha. Nobody ever noticed any cracked clock. Okay, that's how you remember this, right? Then as I told you, CFSE order, 5D is greater than 4D, then 3D. Square planar is greater than octahedral, then tetrahedral. It is so that delta T is almost half of octahedral, as you can see this over here, right? Then tetrahedral, the d orbital splitting is smaller than octahedral. It is almost half of octahedral. That is the reason in tetrahedral you will see high spin complexes, because the splitting is so small that generally they form high spin complexes. Splitting is very small, so they will jump, they will not cause pairing, right? Okay, ठीक है जी, understood? Yes. Tell me. You will find that over here, right? Organic chemistry, I'm thinking to do it. If you give, let's say, 1000 plus likes here, then I'll think to do it. So 500 plus likes you give, then I'll do it. Okay? Done? Chalo. Now let's see next thing. Right? Remember that E is equals to hc by lambda is equals to h mu. So that's why energy is inversely proportional to the wavelength, right? Okay, so that's why now this order that you have written over here for spectrochemical series, they can ask you the order of lambda, that will be inverse of spectrochemical series, right? Okay, then let's talk about DD transition. See, simple thing is that DD transition takes place because here you have T2, here you have EG. So it will transit from this to this, then it will come back and it will give you complementary color that you see, that is called as DD transition. So colorless complexes will be D0 or D10, right? Others will be colored here. Colorless complexes will either have D0 or D10. They will not show any color. Also, exception is that KMnO4, which has Mn7 positive, has D0 configuration, but and K2Cr2O7, we will study this in DNF block as well. This has chromium plus 6, that is D0. Both of them has D electron 0, but both of them has D electron 0. The D electron is 0 here, but both of them shows color. This has purple color, this has orange color. Why? Ma'am, D0 should have colorless. They show color by charge transfer, and that too LMCT. They show color by LMCT. Okay, it's just a simple thing that you should remember, right? Everybody, tell me, right? Okay, please do it. Chalo, I'll do it. I'll think. Okay, make it 500 plus likes and make it, no, by 2 days, make it 500 plus likes. I'll do that, right? Now see what are the complementary colors. Like if you have violet, just remember this is the chart, just write V B Gyur. Wait a minute. I'll just, instead of this na, write it this way. Okay, I'll just give you this thing. Vybergyur. Just write Vybergyur. Okay, so the colors will be complementary to each other. Violet and yellow are complementary, blue and orange are complementary, red and green are complementary. These are all complementary colors, right? See, as such, so you don't have to remember these colors, right? Okay, but still I have written it for those students who don't want to take any risk, because see, I would not advise you to remember these colors, but still I have just put it here, okay, so that you have an idea that which has which color. Okay, but I'll tell you how do you remember these colors. You don't have to remember this color. I have already prepared a chart for you that I have done in DNF block. There is a chart of ions and its colors that you must remember, that I have already made for you, right? Now let's see this question J 2025, that is which one of the following complexes will have delta O and mu is equals to 5. See, if mu is equals to 5, that means it will have 5 unpaired electrons. 5 unpaired electrons you need to have, right? Delta O, which of the following will have delta O what? Delta O, I think there is some misprinting or what. Chalo, 5 electrons I'll find, right? 5 electrons, 5 unpaired electrons. See, in strong field, so it is not possible. Cobalt with, do you remember with cobalt 3 positive, NH3 start behaving as a strong field ligand. So here also, this is not possible. Here it is weak field. Here also it is possible. Let's see this thing. This is x minus 6 is equals to minus 4. So x is, this so we have done na, Fe F6 4 negative. I have told you it is weak field ligand. It is having 5 unpaired electrons. So it is plus 2. Iron plus 2 is nothing but 3D. This is 6 maths, 3D6. Okay. So you have how many unpaired electrons? This is, RU x minus 6 is equals to minus 4. This is plus 2. I think this should be plus 3. Is it? Wait a minute. This though is definitely not there. I don't know what question they have asked. Delta naught is 0. Wait a minute. They have written delta naught 0. Is it? I think so. Delta naught they have asked 0. Right? Okay, only then to it is possible. Because if you see, wait a minute, if you see FeCN6, FeCN6, FeCONH3, Fe this, so delta naught also has to be 0, huh? Wait a minute, huh? Wait a minute. Let me just see it from the answer. They are asking what? I think they are asking delta naught also to be 0. Huh. That's what the answer is, na? So this they are asking that this has to be 0 and this has to be 5. So if you see this here, this is not coming out to be 5. Here though it is not possible only because strong field ligand, how it can have 5 unpaired electron? It will cause pairing. This has unpaired electron, but here you have how many unpaired electrons? No. So here you have 4 unpaired electrons. 1, 2, 3, 4, 5 and this is 6. So you have 4 unpaired electrons here. So again, this is not the possibility. The only possibility left is this one. I'll tell you how. So you have manganese and SCN is under very low spin complex. If you see this here, SCN is a weak field. SCN is weak field. If you see this over here, let me just show you that. SCN is under the category of weak field only. Can you see this? It is weak field, even weaker than chlorine and fluorine. So it is under weak field only, right? So how do we calculate this? Let's understand that. Let's understand that. Wait a minute. Let's see. Now I'll just calculate this manganese here. Manganese. See, manganese has oxidation state. This is x minus 6 is equals to minus 4. X is equals to plus 2. So manganese plus 2 is nothing but 3d5. Because it's a weak field ligand, so it will not cause any pairing. So it will be 1, 2, 3. Even if I make it 1, 2, 3, 4, 5, 6, it will be 5 only. 1, 2, 3, 4, 5. This is octahedral. You make it 5 unpaired electrons. 1, 2, 3. For weak field, it is 5. So number of unpaired electron is 5. What is delta O? Delta O is here, this is multiplied by 0.4 minus 0.4 into 3 plus it is 2 into 0.6. So it is minus 1.2 plus 1.2, that is 0. So that is coming out to be 0. So answer will be D is the correct answer here. Right? Okay. Yes, I'll definitely give you break. Don't worry. After coordination chemistry, I'm going to give you dinner break. Don't worry about that. Chill. Take a rest. Okay, no tension on that. Right? Okay. Chalo. Next is the correct order of complexes. Now, can you see such a simple question? JEE 2025 they have asked. They have given you H2O and this, NH3. They have given you CN. They have given you Cl and this. See, strongest, they are asking the correct order of wavelength. See, energy order will be what? Energy order will be, firstly, so it will be C, because this has Cn. After Cn, you will have NH3. NH3 maximum is there, so it is B. Then you have 5 NH3 here, so it is D. Then it is, here also it is 5 NH3, here also it is 5 NH3. But water is, chlorine is a weaker ligand, right, as compared to water. So it will be B and then it will be A and then it will be D. Okay, based on spectrochemical series. Lambda will be opposite. So it is C, B, A, D. D, A, B, C. D is maximum. D, A, B, C. So answer is first is the correct answer. Okay, so that's how you answer this. Okay. Okay. Chalo ji, next question. Let's see that. Next question. In which of the following complexes CFSE delta O will be equals to 0? Where delta O will be equals to 0? Let's understand that, everybody. Where delta O will be equals to 0? Will you find that? Ma'am, we have just done that. Acha, see. Delta O 0. If there is pairing, I'll tell you simple thing. If I say all these are octa only, this has 6, this has 6, En is multiplied by 2 because it is bidentate, this is also 6, this is also 6. So it is T2G only. If I have pairing, let's say 1, 2, 3, 4, 5, 6, 7, 8. Chalo, why to do shortcut? वैसे weak field ligand has more chances of that, but let's do that. Okay. So I'll just divide it into 4 parts, right? Okay. This kind of thing, na, you should know. Trust me, when they give you pages to solve the question, na, they don't give you like full-fledged pages, right? So you have to, sometimes students, what they do, they don't make the marginalized, they confuse between this question is going here, this question is going here, this is going here. That's why they, even after solving, they end up writing the wrong answer. Okay, so that's why I make this a habit of doing these margin lines that I'm doing. I have this habit, right? This is 3, this will be minus 3. This is 3, this will be plus 3. This is 2, this will be plus 2. This is 4, this will be minus 4, right? So if I see this over here, this part, A part will be x minus 6 is equals to minus 3. So x is equals to plus 3. Here it is iron plus 3 is nothing but it is 3d5. You take out, see, iron plus 3 beta. Now, to how many times I have written it? Okay? Now, so you should be able to write it bahut jaldi, right? So it is basically 4s2 3d6. You take out 3 electrons, it will be 3d5, right? So here, though, it is possible. Easily, I can see the answer over here, right? So here it is 1, 2, 3, 4, 5. You multiply this by 0.6, multiply this by minus 0.4. So answer we know. Answer we got, that A is the answer. Right? Answer we got. Still I'll solve it for others. This is x minus, this is x minus mean, this is 0 is equals to plus 3 again. So iron will be in the state of 3d5, but En is a strong field ligand. So here what will happen, pairing will happen. So it is 1 2 3 4 5. So definitely nowhere it is going to be 0 delta O. This will be multiplied by minus 0.4, this is 0.6. So how they can be 0? Not possible, na? So for that, this situation should be there if you want to make it 0, right? This is again Fe, this beta x plus 0 is equals to plus 2. So iron is what, 3d6, right? So this is 1 2 3 4 5. 3d6 means here you have NH3, right? Then again what you have, 1 2 3 4 5 6, right? Again it is not happening, same is in this case. So last two to beta you don't even have to solve, right? Okay, directly it is showing that this is not going to happen, right? Because plus 2 to how it is possible, right? Okay, but still if you want to solve this you can, but we got the answer directly, right? So A is the correct answer here, right? Acha, now let's do metal carbonyls and then isomerism, right? Okay, everybody, tell me. Now we will do metal carbonyls, right? Okay, we'll do things that are important for you for metal carbonyls, right? So if you talk about metal carbonyls, guys, in metal carbonyls, what you will have? First thing is homoleptic ligands. Will talk about homoleptic means same, only one type of ligand is there. Heteroleptic means more than one type of ligand is there. Homoleptic carbonyls containing only carbonyl ligands are there. Now देखो, usually the work of metal is to accept the electron by the sigma bond. This is usually because ligand has a work of donating, metal has a work of accepting. Like I have a work of teaching you, you have a work of learning, studying, that is your work, right? But sometimes you also teach me, right? So ma'am, we don't teach you, no, we learn a lot of things from you, right? Teachers also learn a lot of things from you. Like sometimes I see so many dedicated students out there, uh, they are so passionate about this thing. Ma'am, I want to go there. Ma'am, I also want to work. Ma'am, I also want to earn. Ma'am, so I see those students, I learn, right? Isn't it? So sometimes students also teach the students, teachers, some good lessons about life, right? About behavior, right? So here metal is donating to the ligand opposite behavior. And remember this thing, that thing is called as synergic or back bonding. Metal was not supposed to give, but metal is like, you are donating to me, I will also donate to you. So that is synergic bonding, that is back bonding, right? So that is called as synergic or the back bonding. So I'll just write it here, back bonding or synergic bonding, right? And you know where it accepts the electrons? It always accepts the electrons. Ligand accepts the electron in its pi star orbital, right? You don't have to learn this diagram. Nobody is asking you. That is not in your syllabus. Just see that this is the orbital where they accept electron from metal. Because this is empty now, you don't have to learn this diagram. This is just to tell you that this is empty. Okay, this is just to tell you that, right? Okay, tell me. Is that clear? Is that clear? Now let's see extent of back bonding, right? What is the extent of back bonding? If you talk about, if there is more negative charge on the central metal atom, that means it has the power to donate, right? So it will donate. If it has a more positive charge, then it does not have the power to donate, right? Then important thing is, very important, that strength of MC bond will increase. As you can see, if MC bond strength increases, right, then CO bond strength will decrease, right? And always remember, bond strength is directly proportional to bond length, bond order, right? And it is inversely proportional to bond length, right? Okay, this you must know. So if I say MC bond strength is increasing, its bond order is increasing, its bond length is decreasing. And if this is increasing, its bond strength is decreasing, its bond order is decreasing, its bond length is increasing, right? Okay, can you see here? Tell me guys, can you see this simple thing here or not? Right? Okay, understood? Now from here they can ask you question, or they can ask you the one that is most probable question will be this one. Like they can ask you question from here that the shapes, like NiCO4 has tetrahedral shape, FeCO5 has bipyramidal, trigonal bipyramidal shape, this CrCO6 has octahedral. These two shapes are very important, right? They are directly from your NCRT. Now in this case you have one manganese bond as well, and two octahedrons are connected together, and all the ligands are terminal. All are terminal. In fact, in all the cases you have terminal ligands only. But in case of cobalt carbonyl complex, you have these bridged ligands. These are bridged. They are forming a bridge. They are bridged ligands. Others are terminal, and it also has one CO-CO metal-metal bond. Right? Okay. So there is a question on this that they have asked you in 2024. Let's talk about that question over here, everybody. That is, in which of the following metal carbonyls CO forms a bridge between metal atoms, right? So you should know all the compounds here, and that's why all the compounds I have already drawn it here. In case of cobalt, one cobalt and two carbonyls are there. Here you have no bridge carbonyls, all are your terminal carbonyls. Here in osmium, they are connected together making a square planar, and after that all of these or ligands are connected that are in terminal position. Same with ruthenium, right? Okay, tell me. Yes. Definitely, tell me. Okay, so that's how you answer this, and this is just a cramming part here. This I have given you the crux here, that these are the structures that you must remember. Now you, after the class now, one student was asking, ma'am, after the class what is the task? After this class, all the things of block chemistry and these kind of things you have to revise and note down yourself. Note down yourself means you have to PPT, PDF will be provided to you like in the morning, right? Because I think the class will end by 12 a.m. or so, right? So it will take us time, right? So that's the reason I think PDF will be provided tomorrow in the morning, right? Okay, understood? So if you have this here, in the cobalt carbonyl complex, number of CO-CO bonds is X, and terminal CO bonds, CO ligands are this. CO-CO bonds, number of CO-CO bond is X. So X is 1. Terminal ligand is what? How many terminal ligands you have? You have 1, 2, 3, 4, 5, 6, and 6 terminal ligands. So this is 6, that is 7. So answer will be 7 is the correct answer here, right? Okay, done. Acha, before moving towards structural isomerism, let me just tell you one important thing about EAN, right? Very simple concept, that is very simple concept, very simple, very easy. In your syllabus, so at least it is simple, but otherwise, so that complex, that topic is very vast. Okay. See, if you talk about this thing here, if I tell you En, effective atomic number, let's see you have FeCO5. Okay, one example I'll give you. Let's see you have FeCO5. In this, what is X? X is equals to 0. So your oxidation state will be 4s2 3d6. Okay? Now see one thing. Number of electrons in the central metal atom, you have 26. How many electrons this ligand is giving you? 5 ligands you have, and 2 electron are given by 1 carbonyl, so it is going to be 36. This is noble gas configuration. Okay, this is noble, this is the atomic number of proton. So you can definitely say that yes, this follows En. That's why this compound is existing, because it is following En. En rule means simply it states that your number of electrons from central metal atom in its oxidation state, plus number of electrons from ligand is equal to any noble gas atomic number. If it is so, then it follows En. If it is so, then En is followed. Right? Okay? Tell me. Okay? So just this much, if you remember, that is good enough for you. Right? Now let's see isomerism. Right? So isomerism itself is a, like, if you want to see it in detail, you can watch my lecture. Just type Stereoisomer by Diksha ma'am, in coordination chemistry. It's a 3-hour lecture. I have just taken it, I think, 3 months back. But the conclusion part I'll tell you, because otherwise it's a very lengthy lecture, right? If you want to see it in like full detail, because things are complicated here. But instead of just not doing it, I have written the conclusion part, that this shows, this does not show. Because in the end, all you have to remember is which one shows and which does not show. And I can guarantee you that if you see this, the things that I am giving you here to remember, and also I'll teach you here as well why it is so, you will be able to do the questions. But if you want to do like full detail, then watch that lecture. But if you don't have time, this is also good enough, right? Okay, tell me. Write down isomerism in the chat box, everybody. Let's see how many likes you have made by now. How many likes? Let's see. Oh, still 245. It should cross 300 by now. Let's see if you will be able to do it or not. I am doing my part. Let's see if you can also do your part. Right? Okay? Chalo. Now, let's see that. Right, everybody? So, if you see this over here, structural isomerism, you have here, देखो, 2 type of isomerism you have. One is structural, other is stereo. In structural, the bond has changed. Okay, like A is connected to B or A is connected to C, the linkage of that atom has changed. Okay, so that's why we'll see that 1, 2, 3, 4, 5, 6 type of isomerisms we'll see here. First is ionization isomerism, in which the counter ion and the ligand, they are interchanged, right? That means here you will have counter ion as SO4. Here the counter ion will be Br. So that is interchange, that is ionization. The ion is different, that is you are giving after dissociation. In case of hydrate or solvate isomerism, the number of water molecule acting as ligand are different. Remember, always formula is going to same in isomerism, right? So formula will be same. Here 6 water molecule as ligand, here 5 water molecule as ligand. In linkage isomerism, you will have ambidentate ligand. That means two donor sites, but at one point only one is donating, right? So here it is donating by nitrogen, this is donating by oxygen. So the linkage is different. That's why this is called as linkage isomerism. Then there is coordination isomerism. In coordination isomerism, what you have, right? Yes, I am covering it, Sanjana, from the past. है ना? How many times you asked me the same thing? ठीक है? Yes, I am covering, beta. Coordination isomerism, you have two coordination entities. Cation is also coordination entity. Anion is also coordination entity. But cobalt is with NH3 in first. Here cobalt is with Cn in second. Here chromium is with Cn, here chromium is with NH3. So they are interchanging the ligands with each other, right? Otherwise, both will have the coordination entity, that is called as coordination isomerism, right? Then next is you have ligand isomerism, when the ligand itself is different. Ligand is the isomer of each other, that is called as ligand isomerism. Okay, tell. So the ligand is different, that is called as ligand isomerism, right? Okay, last is coordination position isomerism. This you will not find it in your NCERT. This one you will not find in NCERT. This one also you will not find in NCERT, right? So this one is coordination position isomer, means you have two metal ions. These two metals will exchange their ligands. Like here you have 4NH3 here and 2NH3 and 2Cl. Here you will have on one side you will have 3NH3 and 1Cl, and here you will have 3NH3 and 1Cl. That means the distribution of ligands in the two metals in that one coordination entity will be different. That is called as coordination position isomerism, right? Okay, tell me. Is that clear? Is there any problem in structural isomerism? Because then we will be moving towards stereoisomerism, right? Okay. Tell me. Understood? Tell. Till now we have done structural isomerism. Now we will be moving towards stereoisomerism, right? Okay, everybody? Okay, everybody? Let's see stereoisomerism. Ma'am, will you give the PDF of this session? Yes, I'll definitely give. Don't worry, right? So let's see stereoisomerism. Beta, wake up, wake up, wake up, wake up, everybody. Spam the chat box with green hearts who are there, who are active in the chat box. Spam the chat box with green hearts. Let me see. How many of you are awake? Because this now next thing is going to take a lot of energy of mine, right? So I want you guys to be completely ready. Fill the chat box with green hearts. Fill the chat box. Have you also shared this session on your Instagram? Have you also tagged me at you can say Diksha Kaushal _ Vasudev, or you can say Chem Catalyst Diksha. You can tag any of this. Have you done that? Right? If you're making any notes, write the notes and do tag me on the Instagram, right? And also share this on your WhatsApp story so that we can spread more knowledge, right? Okay? Those who use. Very good. Good. This page you are saying, you have two metals, okay, in one coordination entity. the distribution of ligands have changed, right? Distribution of ligands have changed. Like here you have, with this metal you have 4 ammonia, with this metal you have 3 ammonia, 1 Cl, with this metal you have 2 ammonia, 2 Cl, 2 ammonia, 3 ammonia and 1 Cl. So that distribution has changed, right? Okay. Beta, definitely there will be p block. Okay, after stereoisomerism we are going to start this block chemistry only, right? We'll start with p block only after this, right? But I'll give you break for that, right? Chalo, let's understand. I think by 8:30 it will be done, and for then I'll give you break of 30 minutes. 9 p.m. we'll start block chemistry, right? Now we'll do stereoisomerism. Let's do that. Okay. Chalo. So stereoisomerism you have, first is geometrical isomerism, then there is optical isomerism. Geometrical isomerism, we talk about cis and trans here, right? And in optical isomerism, we talk about POS, plane of symmetry, should not be present, only then optical isomerism will exist, right? Now always remember that tetrahedral will not show geometrical isomerism. Can you tell me why? And square planar will not show optical isomerism. Can you tell me why? This itself is a very important question. If you see tetrahedral, I'll just show you this with the help of structures only, right? If you see this over here, if you talk about tetrahedral, right? If you see this here, I can't tell that this one is next to, because cis means what? Cis means simple thing. Cis is this thing. Cis means when two things are next to each other, two same things are next to each other, that is cis. When two same atoms are opposite to each other, that is called as trans. So in case of tetrahedral, I can't define whether these two atoms are opposite or they are next to each other. They are next only. You can't define whether they are opposite or next to each other. That's why you won't be able to show tetrahedral isomerism. Tetrahedral will not show geometrical isomerism. Why square planar cannot show this optical isomerism? Yes. Why square planar cannot show? Guys, please don't spam. I'm going to cover. Last time I'm saying yes, block chemistry will be done. Now don't ask. Okay? Please focus. Right? Focus. Why your essay doing? Right? So square planar you have here. Right? See, optical isomerism is POS should not be present. So here though there will always be one POS that is cutting it like this. Okay, this POS will always be present here. That's why square planar will never show optical isomerism, because POS is always present here. Now let's talk about geometrical isomerism in case of cis and in case of square planar with coordination number 4. Okay, so if you talk about coordination number 4, right? If you talk about coordination number 4, what it will give you, this is coordinate, wait a minute, let me see, coordination number 6 is also there. Yes, perfect. Okay, see, now let us see which one will give, which one will not give. Bacha, please focus. I need full focus from your side, right? Okay, right? Please have focus here. So in case of square planar, right, cis and trans, can I define cis and trans here? What cis and trans? Same atoms are also next to each other, same atoms are also opposite, no cis trans here. If I change one atom here, let's see if I change one atom, A3B or B3A. So here, these two atoms are next to each other, same atoms next to each other, same atoms opposite to each other. So no cis and trans here, right? So this also will not show, this also will not show, this also will not show. AA2 and AB. Now what is this AA and AB? For that, let's see this. Okay, for this AA and AB, let's see this. See, if you have bidentate ligand that is symmetrical, right? Like En or oxalato, that will be shown by AA, BB, CC, right? If you have unsymmetrical ligand that is like this, that will be shown by AB. Now, you have here if you have, let's say AA, let's say AA, okay? So you have here, this is A and this is also A, right? Wait a minute. This is also A, right? And this is AA now. Now I'll just make this, I'm defining as symmetrical ligand, okay? This I'm defining as symmetrical ligand C. This is also AA. See this thing very carefully. If you see, you can't define which is next to each other, which is opposite to each other. So this will also not show. If you see AA and BB, let's see, you have AA and BB. Now in this case, for example, you have something different here, like AA is a different ligand, BB is a different ligand. So let's see if it can show or not. If you see this here, even now it is the same ligand. Even now if I reverse this, it will also be the same compound. There is no change in that compound. Even now it is the same compound. If you see this, even now it is the same compound. There is no, if I rotate, if I change this as well, it will remain the same. So you can't define which is cis and which is trans, so that will also not show. If you have AB here, let's say you have here AB, right? Let's say you have here AB. Now in this case, if you see, if I say this is one ligand, chalo, this is one compound, right? If I make this opposite, if I interchange it like this, that is the same thing. I rotated, that is the same thing. So you can't define cis and trans here. For cis and trans should be two different ligands, I am saying two different compounds. You can't make it for this one. So all these that I have written here, they are under the category, they will never show any GI. So mark it here, they will never show any GI, right? These complexes will show GI. For example, you have Ma2B2. Right? In this case, when two same are next to each other, it is cis. Two same are opposite to each other, that is trans. It is easily showing GI. Then you have Ma2BC. Now, two same are next to each other, that is cis. Two same are opposite to each other, that is trans. It is easily showing it, right? Then you have MABCD type of ligand. Let's see that. How to define this, right? In this case, now always there will be two cis and one trans. Always. You must remember this, right? Let me tell you how. ABCD. ABCD. Now see, I am fixing one of them, right? I have fixed this. This is fix, okay? I have fixed this. Now what I'll do, I'll interchange these two. This will become C and B. Then I'll interchange these two. This will become B and D, okay? Now, what you will do, take any two as same. Let's say C and D as same. Let's take C and D as same. Like in this compound, you will have bromine and chlorine as same because they belong to halogen family. Okay. So D and C are same. That means this is cis. D and C are same. That means this is trans. Two same are opposite. D and C are same. That means this is cis. They are next to each other. So two cis and one trans always. Right? Okay. Chal. Then you have Ma2 AB2. Okay, this I'll teach you how, basically why I am saying this. This, with the help of this 3D structure, you will be able to understand it more easily. Wait a minute. See, you have this thing, right? Now can I say this is a different molecule, right? Okay, two same are next to each other. If I draw it like this, that will be a different molecule. You rotate it, nowhere you are getting the same molecule that you have drawn before. So they are opposite to each other. So I can clearly see it is defining cis and trans, right? When they are opposite, it is defining trans. When they are same, it is defining cis, right? Okay, tell me. Now let's talk about coordination number 6. Let's see everybody, coordination number 6. Coordination number 6. देखो, in coordination number 6, basically we talk about octahedral complexes, right? So see, I'll just tell you where it is showing GI. देखो, A6, AB5, in this all, they will not show any GI, right? Because there is no cis and trans that you can tell here, right? So they will not show GI. This will not show GI, not show, they all are not showing GI, right? Okay, understood? Then you have this one will show GI. This one is very important, and this they have asked you so many times, right? So it is A4B2. This is A4B2. Two same are next to each other, it is cis. Two same are opposite to each other, that is trans. It is showing GI, right? Then A3B3, very, very important. Here I'll also tell you this with the help of the structure here. Basically, you know what will happen? 3 will be same, 3 will be opposite here. I'll tell you very interesting thing here. See, octa means 8 phases, right? If on one phase, this is a triangular phase. This is a triangular phase if you see. It's a triangular phase. If on one triangular phase you have same atom, that is facial isomer. That's why it is called as facial. Then it is making a meridinium, right? Oh, one unsymmetrical ligand was there, right? So if they are making a semicircle, can you see this? They are making a semicircle, a C, that is called as meridonial isomer, right? But ma'am, what about 2D? How do I write it in 2D? So simply see A, when they are written next to each other, that is facial. Then you write 2A, then you leave a blank, then you write, then again A, that is meridonial. Very, very important, right? They give not cis trans, but facial meridonial, right? Then you have A4BC. In this case, BC will define whether it's cis or trans. So when B and C are next to each other, that is cis. When B and C are opposite to each other, that is trans. Okay, this is the case, a different case. Right? Basically, we want to have a different thing, na? So see, if I say this, when B and C are next to each other, let's say this is C. Okay, that's a different structure, right? If they are opposite to each other, that's a different structure. So all we want to see is two different structure. That means they are showing two different structure, right? Okay. No, there is no formula for that, but I have made a table for you. Okay, AA2B2, right? Now again, B will define when B is next to each other, that is cis. When B are opposite to each other, that is trans. This is also very important, right? They are very important. Okay, this is also important, right? This to pata nahi how many PYQs I have seen this. Even this one, so many PYQs you will see this, right? It's very important, right? Now, this table you will see. This table has all the GIs that you have for coordination number 6 that you need to remember. And this says yes. Okay. All the GIs that you need to remember, that is in this table. Right. Now, let's talk about optical isomerism. Shall we? Everybody tell me about it. Shall we talk about optical isomerism? Let's talk about optical isomerism. Yes, students? Okay. So, optical isomerism basically means enantiomers, right? So, when you have non-superimposable mirror images, that is called as enantiomers, and they are called as optical isomers. So, you don't need to see any POS should not be present, and then they are also non-super. These are the two ways to define this. Non-superimposable mirror image, right? Those two optical isomerism can be dextro or levo. Dextro means that rotates the plane polarized light towards right. Levo means it rotates the plane polarized light towards the left. Okay, understood? Tell me, is that clear? Is that clear, everybody? Is there any problem in that? Done? Tell me. Done, everybody? Done, done. So, now let's see this thing here. Let's see coordination number 4. With 1 and 1, see, first thing though it is though, I'll tell you, doing all of this now, if you want to see it in detail, which one will show POS and not show PS, go and watch my 3-hour detailed video, right? In that you will find it in detail. But now I'll be showing you only those cases where POS is not present, which shows optical isomerism, okay? Right? I'll be showing you this part and this part. If you want to just cram this, then you have the notes. Because in the end, now, you have to just stick in the exam, because this is very like little understanding is important here, right? Wait a minute. Tetrahedral we'll see now, not octahedral. Tetrahedral, right? So in case of A, B, C, D, when all of them are different, so you have A different, you have B different. Chalo, let's make this. If all of them are same, definitely there will be POS. If one of them is different, definitely there will be POS. Let's say if two are different, here also there will be POS. As you can see, POS is present here as well. Then if I say, similarly, in this case as well, you will have the POS. If you want me to draw essay, I see your faces and I'm like, okay, let's do this. Okay? Too much dedicated I am for you. Are you also dedicated for me or not? Or it's a one-sided love? Okay, see. It's a one-sided love, ma'am. Ma'am, you are in situationship, ma'am. Ma'am, you are in situationship with YouTube kids. Eh? Do you also care? Are you also with me? Will you also stay here till the end? Or I'm the only one who will be celebrating Christmas with you here? I'll be celebrating Christmas with you while teaching, right? So, this is AA2. Can you see there is POS present directly? Can you see? Yes, it is there directly, it is present, right? So, if you have AA and BB, here also you have POS present. Can you see that over here? Yes, it is present. Yes, it is present. See, it is present here. How amazingly. Yes. See, POS is present here. Arre, wow, ma'am. Right? So, POS is present here. Right? Then AAAB. Okay. That also I'll show you. It is again present here. Right? It is again present here. It's not that difficult. I know you find it difficult because you have never seen the structures, so you will find it difficult. Na? Imagination, if I tell you imagination, then you will find difficult. You see this place now, can you see the plane of symmetry? This will be divided into half, this will be divided into half. And you can easily cut it into half, right? POS is present here. So now let's see ABCD. When all of the atom are different, there is no POS that is present here. I have one green atom. I have, let's say, one yellow atom. I have one brown atom. Let's say I have one, which one? This some mercury silver color atom. Now, what you can see, if I divide this, if I pass a plane, not equal half. 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 So no POS is present here, so it definitely shows POS. It definitely is an optical isomer. Then you have AB2. AB2 means both are different unsymmetrical ligands you have here. Okay? Both are different unsymmetrical ligands you have here. When two unsymmetrical ligands you have here, you will always find the optical isomerism because there is no POS that is there. You can see this over here as well. You divided into equal half, not equal halves. Okay, you see it is not cut into equal half. You see this here, it is not cut into equal half, right? Can you see this? It is, we can't divide it into equal half only, right? So no POS is there. It's simple, right? But ma'am, in the exam so we will not have these structures, so I have given you to remember na. Just remember this, these two will show will show optical isomerism. That's it, right? In coordination 6 as well, this one will show you POS, right? Then sorry, this one will show you optical isomerism, and this one will show you. Rest of them does not show any optical isomerism, right? Okay, you find it. This cis or trans, they will also not show any of this. You see, they will not show any optical isomerism. Facial meridional also will not show any optical isomerism. So this also M3B2, see, this will also know. MABCDEF, remember this, learn this. GI, they will show 15. How and how, don't get into that, right? It is not even required, right? GI, it will show 15. Optical isomerism, it will show 30. Total stereoisomer will be 30 because GI and its GI is 15. Its mirror image will be 15. So total optical isomer is 30 and these are the GI. So total stereoisomer is also 30. Okay. So that is the thing. And remember A2, B2, C2 will also show you optical isomerism, right? Okay, tell me everybody. Now let's see some important things here. Why this shows AA3? Why this shows? Okay. Ek to these two you have done, they will show optical isomer. Now I'm going to show you some things that they ask you very, very frequently, okay? So MA3, this is a very frequent question that they ask you, very important, very important. Okay? Here students na, who have not done this, who had not done this, they answer it wrong. Ma'am, this is, okay, ma'am, this is the mirror image. Ma'am, you rotate it, you can, ma'am, fall it here. Array, see, this is x-axis, let's see, this is y, and this is z. Mirror image says, this will be y, this will be z, and that will be x. Okay, that will be x. You rotate it, this is cobalt, 1, 2, 3, 4, 5, 6. Now you rotate it, this will be x, this will be z, and this will be y. Right? Can you, x is overlapping x, y is not overlapping y, y is overlapping z, z is overlapping y. So how can they be superimposable? They are non-superimposable. So that means they show optical isomerism, right? Similarly here, you have x, this is y. You take the mirror image, this x will become x here, this y will become y here. Then you rotate it to 180 degree, right? To see if after rotation this is same. So this x will go, this y will go here, this x will go here, right? And the CL will go here. Now if you see, y is overlapping x, this y is also overlapping x. So they are non-superimposable, okay? They are non-superimposable. right? So they also shows optical isomerism, right, everybody? This too you can delete. Okay? See. Now you have MAA2, B2C2. Dekho, I'll just show you this. Basically, what they are saying here, MAA2. Let's say you have this AA2. If I draw cis here, B2C2, na? B2 and C2. If I draw cis here, where they are all next to each other, can you see when this is next to each other? This is, wait a minute, they all should be next to each other, na? So here it should be like this. They all should be, wait a minute, next to each other. See, next to each other, next to each other, next to each other. That is cis. Cis, I am saying that does not possess POS. Can you see here any POS? There is no POS that is possible. No POS that is possible here. Possible ही नहीं है. No POS possible. But if I draw trans here, then what will happen? Tell me. If I draw trans here, then what will happen? If I draw trans here, that means I connect green opposite to green. Okay? Wait a minute. Green opposite to green. White opposite to white. Okay? Right? And this part opposite to this part. Okay? Right? Now, can you see this is showing POS? Can you see? It is, when it can hide and you can see na ki easily you pass the POS there easily, you can see POS is present. So it will not show optical isomerism. Okay? Right? Okay. Santosh, optical isomerism, so that's why I'm telling you, if you're doing this in the revision purpose, optical isomerism, right, then to you can understand. And trust me, if you're not able to understand, just learn which one shows optical, which one does not show optical, or watch my 3-hour long lecture, right? Okay, this is for revision. First time if you see this, you won't be able to understand this. Okay, that's why I showed you with the structure, at least something you can understand. If I don't show you the structure, then it will go from your head, right? So, yes. Tell me, guys, is that clear? So now this is the chart for optical isomerism. Acha, tell me if that is clear. If there is any problem, then do let me know in the chat box. JEE 2025 question. A homoleptic octahedral complex formed using monodentate ligand will not show stereoisomerism. Homoleptic octahedral complex, that is MA6, will not show optical isomerism. See, it will not show any GI, it will not show any optical isomerism as well. So that is true. Okay. Cis and trans platin are heteroleptic complexes of PD. They are of platinum, not PD. They are of PT. So this is also wrong. So answer will be both the statements. First is true, second is false. Because what is cisplatin? Cisplatin is this particular compound that is a complex of PT, not PD, right? And cisplatin is anti-cancer drug, right? Okay, chalo, let's see. The correct statement on the isomerism associated with following complex ion is what? Tell me, everybody. What is the answer for that? The correct statement on the isomerism associated with the following statement is what? So in this case, statement also you should know, na? A and B show geometrical isomerism. See, this does not show any GI. This does not show any optical isomerism as well, because POS will be present. This will show you GI. Okay? It will show you GI like this. Okay? This will be AA, and it can also be like this. AA next to each other. Here POS will be present. Trans will not show any optical isomerism. Cis will show optical isomerism. So optical isomerism also they will show. This is facial and meridional. They only show GI. Only GI, no optical isomerism. Okay? This na you can only answer if you know all of them on your tips. If that is on your tips, like which one shows, that's why I'm telling you, even if you're not able to remember that, just understand a bit and remember things, right? Okay, even if you're not able to understand it fully, just remember, like, you know, some very very important, very frequently used isomerism that I have pointed out there, right? Okay, so here answer will be A and B show geometrical isomerism. That is true. We are saying true or false. ठीक है. A and B show optical, geometrical no. B and C show geometric. Optical isomerism तो only B is showing. ठीक है. So these two statements are तो not valid. B and C show only geometrical isomerism. That is also correct. A does not show geometrical as well. ठीक है. So B and C shows only geometrical isomerism. B and C only are showing geometrical isomerism, but B is also showing optical isomerism. Okay, so answer will be D is the correct answer. Okay, understood? See, next question. This is a simple question from structural isomerism that you have, right? So like here, if you see, here you have ambidentate ligand, so it will show you linkage isomerism. Here you can see this, they can exchange the counter ion and the ligand, so that will be ionization isomerism. Here you can see two coordination spheres are there, so this is coordination isomerism. Here you can see water as a ligand, so this will be solvate isomerism. Okay, so that's how you can answer this part here. Okay, okay. Let's see the next one here. Achha, so many questions we have for this one. Chalo, two more questions. Okay, chalo, good that you will have practice of this thing. Type of isomerism exhibited by compounds. Value of coordination centimeter atom is what? Wait a minute. Type of isomerism exhibited by this. See, can you see all of them have this as 4 water as ligand, this has 5 water as ligand, this has 6 water as ligands. So that means they are showing solvate isomerism. So answer will be solvate isomerism where coordination number will be 6, right? Okay. Next. Type of isomerism shown by this complex. Can you see this is what complex? Ma2, or you can say Mb2, AA2. This M1, 2, 3, 4, 5, 6, A2, this is BB. This can also show you 1, 2, 3, 4, 5, 6. This is 1, 2, this is B and B. Alright, okay. So that is, they show geometrical isomerism. So answer is A is the correct answer. This is trans and this is cis. Okay, tell me. Is that clear? Is that clear? So they are showing geometrical isomerism. Now, last question, guys, of coordination. After that, I'll give you the break and we'll start with this block chemistry. Okay. So, number of possible isomers of complex this will be what? Alright, we have seen. I have just shown you this thing here that they will show you cis and trans. Trans will have POS, so no optical isomer. This will no POS, so it will show you optical isomer. So, one cis, one trans, plus the mirror image of this cis mirror image, that total corresponds to 3 isomers, right? Mirror image of this. So as you can see this over here, cis and its mirror image plus trans, right? So that is going to be 3 is the correct answer here, right? Okay, tell me. Done? Done, everybody? ठीक है? Okay. Isomerism part, I know you might have, you might find it little confusing. So I would advise you after the class as well, no break. Let's continue, ma'am. Sasi Kumar, I am not on any drugs. Trust me, right? I am on simple dinner, right? So I have to take dinner, right? I'm literally not taking any drugs that I'll just come here and I'll just start da 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 from the past 5 hours I'm teaching. I need rest. My body also needs rest, right? Your brain also needs rest. Tell me. Okay? Done, everyone? OMG. You know, such a big thing we have completed. Pata, I'm so scared that I'll lose this PPT. So I don't know. I'm so scared that uh, I'll just save this. I just want to save this so that I don't lose my annotated notes here, right? Okay. So what we will do now, we'll take a break and let's see how many likes you have made it. Will you all comment as well? All the 48 students sitting here. Will you all comment as well? Do you feel that I am doing any hard work for you? I see you guys watch the lecture, but you don't comment, right? And that's very weird. One day na, I'll stop teaching, right? Trust me. One day I'll stop teaching and then you will look that where is Diksha ma'am, right? So, I think what you give to others will come to you, right? If I am teaching you without any personal motive, then it's your duty as well to appreciate me, right? So after this, abhi to I am not ending the class. We are still left with block chemistry. It will take us 3 hours to complete block chemistry, right? So after block chemistry, the session will end right by 12 a.m. Right, and I want just one thing from you. Write down all the 48 students that are here, 52 students now. You need to comment, right? I will be waiting for that. Otherwise, I will not be taking organic or physical chemistry marathon. Right? And trust me, I'll not be taking that. Nobody is asking me. Nobody in Vedantu is asking me to say that, ma'am, take 10 hours marathon. Right? We are doing it ourselves because we are passionate about you. Right? So if you don't want to comment or anything, then we will also feel like, okay, it's okay. In batch, so we are teaching this. In Sigma batch, it is already going on. Right? So, yes. No, S block is not there in mains, right? Okay, chalo. Now I will just, I think that will be completed. So once it is completed, I'll just write it here. Nearly completion it is. I don't know how to say anything in IIT level. Sumitha? Chalo. Okay. Now I'll see you all at 9 p.m. Works. Okay. Have your dinner, right? And 9 p.m. I'll resume the class. We'll do like full on block chemistry, P block. And let me just show you, right? Like, why so many slides we have for block chemistry, because I'll be giving you mnemonics. I'll be giving you directly acidic, basic, neutral oxides, direct thing. Then important lines of NCRT I have picked up. Tables of NCRT I'll be teaching you. Do you get it? That level of content, right? Yesterday whole day, right? Like was invested in doing this for you, like whole day. ठीक है? Chalo. Block chemistry. Are you scared of that block chemistry? Chalo, I think that is too much of time this is taking. I want to write 9 p.m. As to 5 minutes it will only take. Yes, everybody. Chalo. चलो डन. ठीक है, अभी I'll just write here. I'll teach you block chemistry. The class will resume at 9 p.m. So freshen up your mind. I will also freshen up my mind, and after that we'll learn block chemistry. Okay? Done? Chalo, see you all at 9 p.m. Bye bye. Hello. Yes, everyone, I am back. I am back, everybody. Do let me know if I am clearly visible and audible to all of you so that we can start with. So that we can start. Ma'am, had your dinner? Definitely, I had my dinner. I hope so. You also, all of you also had your dinner. So now we are going to start with block chemistry. Firstly, I'll be starting with P block, right? Okay, then DNF block. See, P block to na compounds and all we will not do. We'll do the trends, important trends. We'll do oxides, right? These all we will do, and some important lines we will do. In DNF block, we'll do a lot of important lines, right? Okay, so. Beta S block is not in JEE means, and this is for JEE means, right? Okay, chalo, let's see. Let's start that. Let's start that, everybody. Let's start. Lakhane Bhagya Lakshmi. When you have Lakshmi in your name, na, you don't disrespect a Lakshmi, right? When you have Lakshmi in the end of your name, it's a Devi, then you don't disrespect a girl, you don't disrespect a Devi, right? Okay, so your parents have given you some name, at least give respect to your parents little bit, right? I hope so. You also don't call your mom like that, right? Is it? You also call your mom like that, is it? Maybe person like you can do that. I can expect. Chalo. Now, first thing is, bacha, take the screenshot of this one. This is a very important table. That is all the neutral oxides, amphoteric oxides I have already written over here. Right? Okay, so we'll also do this in the class as well, but some of them I have already written here. All you have to do is remember this thing, right? Okay? Done? This is what you have to remember, right? This is after a lot of hard work, right, that I have written all these oxides. Done? Yes, everybody, tell me. Chalo. Take a screenshot of, take a screenshot, right? Yes, very good, very good. Thank you, thank you, thank you. Let's start. Have you taken the screenshot of this one? This is very important. You know why this is so important? They have asked you a question in JEE 2025 only, where they have asked you vanadium 3 positive. It has an oxide, that is this oxide. Vanadium 3 positive, yes. Then they asked you whether that oxide is acidic or basic or what kind of oxide that is. Okay, so those kind of question is what they ask you, so don't forget to do it, right? Okay. uh yes. Now next is, let's start with block chemistry. This is P block, right? Now this is your periodic table, right? This is your periodic table. This is S block, that is not in your syllabus. This is D block, right? This is D block. This is P block, right? This is P block. And when you talk about F block, this is lanthanum, this is actinium. And after lanthanum, right, you have lanthanoids. Like lanthanum, you have all these lanthanoids. And after lutetium, you have hafnium here, right? After actinium, you have all the actinoids here. And then in the end of this, you will start with again these, right? Okay. Now, one thing to remember here, that firstly we'll start with P block here, right? Firstly we'll start with P block, but before that I need to teach you two things, okay, that we will use a lot, right? First is lanthanoid contraction, and then there is inert pair effect. For that you must know what is screening, right? Okay, these are some basic things about block chemistry that you must know, which will help you understand why the patterns are like that. Okay, firstly you must know the screening effect. if I talk about the screening effect now, in screening effect, remember that screening effect of S is maximum, then P, then D, then F. So what is exactly screening effect? Let's talk about that. What is exactly screening effect? So, but if you see one thing here in screening effect, if you see one thing here, you have a positive nucleus, right? Let's say you have some orbitals, and here you have one outermost orbital that you are focusing on, right? So the inner core orbitals that you have here, the inner core orbitals that you have here, they will define the screening. These inner core orbitals will define the screening for you. These inner core electrons will define the screening for you. Can you see that over here? These are the inner core electrons that will define the screening for you, right? Okay. So if what is exactly screening? Screening means you have inner core electrons. If they have very good screening effect, they are like bodyguards, because what will happen, this proton and this electron will attract each other. Because of this attraction, they will come closer to each other, they will shrink. If there is good screening effect, like you have s orbitals here, right, p orbitals here, if the screening effect is good, right, then they will protect this electron from coming closer to this nucleus here, right? It's like this is the girl, this is the boy, and this is girl's brothers, right? So brothers will make sure, right, that the girl is not getting attracted to this boy, right? Then if the screening is not good, right, the brothers are like, okay, we don't care, then the girl will get attracted, and here what will happen, as a consequence the size will decrease, it will contract. Okay, that is called as inert pair effect, right? This is happening because of d electrons. Now when this will happen because of d electrons, if you see this here, in the d electrons, let's say before gallium, indium, thallium, can you see before aluminium you don't have any d orbitals, right? You don't have filling of d electrons, but before gallium you have d electrons. So that's why all the exceptions that you will see in 13, 14, 15, 16, that will be firstly because of inert pair effect, because of poor shielding effect of these 3d orbitals. Because in this gallium you will fill d10 electrons, all of this will be filled before coming to this gallium. So that is the reason that here, because of this inert pair effect, there will be so many exceptions that you will see, because the size is eventually going to decrease, and so many exceptions you will see in ionization, enthalpy, and size because of inert pair effect. And the second reason will be that in this case you will start adding 4f or electrons as well. Here you will start adding 5f electrons as well. So you will add these electrons, you will add 4f electrons, you will add 5f electrons. So they have even poor shielding effect as compared to D. They have even poor shielding effect. If you see this over here, they have really bad shielding effect, and because of that reason, they have, because of these 4f electrons here, before this you will have lengthenoid contraction, before this you will have actinoid contraction, and that is the reason you will feel some abnormalities over here as well. Do you get it? Tell me. Got it, everybody? That's why in group number 13 you will feel the maximum abnormalities in the size and ionization, because there is sudden addition of d and sudden addition of f orbitals here, right? Is that clear? Because every reason, ma'am, why this is the exception, why that is the exception, the reason is going to be inert pair effect and lengthenoid contraction. Throughout p block you will see this. Okay, that's why in the starting only I told you the reason. Reason is this only, right? Okay, tell me. Okay, tell me, guys, is that clear? Right? Chalo. Done. Now let's start with this. Let's start with the Drago's rule. Will do when we'll do hydrides. Okay, that is a part of that thing. Chalo, I'll just whenever I'll start with the hydrides of group number 15, just remember that I'll have to teach you Drago's rule as well. Okay, all of you remember this, okay, even if I forget. Now, guys, these are the mnemonics, right? You can learn mnemonics in your own regional language as well. You learned it in English, totally your choice, right? How I learn it is, I could learn it directly only hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. So directly you can remember this, right? Okay, this is S block, right? Okay, then you have period 2, period 3, right? Then you have period 4, period 5, period wise this is, right? Okay, done. Now for period wise, these were the mnemonics, and you can totally your choice, howsoever you want to remember this. I have just added this here so that you know, if you don't have any mnemonic, you can remember it from here, right? Okay, now let's see this thing, trends. Now these are some of the important things. See, whenever we talk about along the period or along the group, what will happen to the oxides, right? So along the period, what happens? Along the period means this way. Non-metallic, है ना? I'll tell you a general thing, है ना? I just before going further, I'll just tell you a general thing here. Along the period, always what happens? Size decreases, ionization enthalpy increases, electron negativity increases, non-metallic character increases, electron gain enthalpy increases. Okay, right? This is what you have to remember. Now you come back here. Now these are some important things. If you talk about the oxides here, because the acidity, basicity of oxides, they ask you, it's a very simple concept, that what will happen along the period, non-metallic character is increasing. So metallic oxides are basic in nature, non-metallic oxides are acidic in nature. That is why the acidic oxide, it will increase, the acidity of the oxides will increase, the basicity will decrease here. You can remember just one thing, along the period non-metallic character increases, down the group metallic character increases. That is why basic character decreases. And if they ask you, let's say this is down the group, okay, this is down the group, what will happen? Basic character will increase. This is again down the group only, right? Again down the group, basic character, basic oxide will increase, acidic oxide will decrease. So if you write the basic order, this will have the maximum basicity, but acidity, this will have the least acidity. Tell me, is that clear? Right? Okay, tell me everybody, is that clear or not? Acidic character, basic character, along the period and down the group, this is how do you write it. Is that clear to everybody? All of you, is that clear? Right? Done? Tell me, students, if there is any problem in that. Now let's understand oxides of same element. If you have oxides of same element, right? Let's say, always remember, if you have same element but the oxides are different, in that case, always remember, more is the oxidation number, more will be the acidity. So directly you can remember this, or you can directly remember this, acidity directly depends upon the oxidation number. Directly depends upon the oxidation number, right? Okay, for example, here the oxidation number is +4, here it is +6, here it is 2x minus 6 is equals to 0, it will be +3. This is 2x minus 10 is equals to 0, this will be +5. So more is the oxidation state, more is the acidity. Similarly, here it is +2, here it is 2x, this is 2x minus 6, that is +3, this is x, this is +4, right? So more is the oxidation number, more is the acidity here, a simple funda. But here also you have one exception, and can I tell you that exception? Tell me. Very important exception here. That is H3PO4, H3PO3, H3PO2, right? If I talk about these, right, this is P double bond O. How do you write it? This you must know, right? This is double bond O, right? And here it is OH, OH, and OH. This one is P double bond O. When you take one P and one O, you are left with two OH and one H, right? And here you will have P double bond O, right? You are left with one OH and two H. See, if you technically see what is the oxidation state, in that case here oxidation state will be this is x minus 8 is equals to minus 3, that is x is equals to plus 4. This is x minus 3 to 6 is equals to minus 3, that is x is equals to plus 3. This is x is equals to x minus 4 is equals to minus 3, that is x is equals to plus 1. So according to you, which one should be more acidic, right? Which one should be, this is a very important question, okay? So which one should be more acidic according to you? According to this thing, though, more is the oxidation number, more is the acidity, right? So it should be this one, right? That should be the answer. But in reality, that is not the answer. More is the number of hydrogen, more is the acidity. So here answer is this one. Okay, tell me, is that clear everybody? Is that clear everybody? Tell me. Okay, that is the exception in that order that I have told you, that acidity and oxidation number are directly proportional to each other. Now let's see period wise trends that you will have, right? Period wise trends. One by one we'll see the period wise trend, right? Yes. Done. Let's see the period wise trends that you will have. Period wise trends, firstly though you have this trend over here, that is if you talk about lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, right? That is your if I talk about the atomic radius, right, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, but neon has the maximum. Can you see what is happening, ma'am? What should happen along the period? Size should decrease. So size is decreasing only, but neon has the maximum because neon has van der Waals interactions. Its octet is fully complete. That's why it is fully happy, and that is the reason it has maximum size here, right? So order is going to be this, right? You can see it from the data as well, right? Always noble gases has the maximum size here, right? Okay. Then if I talk about all the periods here, right, all the periods here, in this case hydrogen and this is helium. Helium has van der Waals radius, this has covalent radius, right? If I talk about this thing here, in these cases nitrogen neon, or you talk about argon, they have the maximum radius because they form van der Waals radius, right? So firstly you will write neon, then you will start from here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, similarly you will do it here. First you will write argon, then you will start from here, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, right? So always remember it will decrease, but noble gases have the maximum size along the period, right? Okay, this is from your periodic classification that I'm telling you some orders that you must know. Okay, now ionization enthalpy order is very important here. Let's understand that because it has a lot of irregular trend. See, expected order is this thing, lithium, beryllium, because what do we expect? Size and IE is inversely proportional, right? Ionization enthalpy means you want to take out, remove energy required to remove the outermost electron. If size is very big, that means attraction with the nucleus is very small, so it can easily take out the electron. right? So according to you, if the size is decreasing, ionization enthalpy should increase, right? So order should be this. But what happens, you will see over here, wait a minute, over here and here, you will see the order is different, right? Why so? Because lithium, beryllium, boron, instead of that, you have boron, beryllium. Because if you talk about beryllium, it is 1s2, 2s2. Isn't it a very stable configuration, fully filled? For nitrogen, it is 1s2, 2s2, 2p3. It is half filled. That is the reason group number 2 and group number 15. What I am saying? Group number 2 and group number 15, they have a very stable configuration, and because of this stable configuration, it is very difficult to take out electrons from there, and that is the reason what you will have here, beryllium will have more as compared to boron, and nitrogen will have more ionization enthalpy as compared to oxygen. Tell me in the chat box if that thing is clear to all of you, and this order has been repeated a lot of times. Okay, this is a very important order, right? Done. Tell me everybody. And fully filled. Very good. Now see, till now though they have asked you these two things, right? But maybe they can ask you this as well. Here it is same. Like nitrogen is more, similarly phosphorus is more, because nitrogen, phosphorus, then arsenic, they all are same group, na? And here it will be this. Okay? So that is along the same. Like you have beryllium, magnesium, calcium, boron, aluminium, gallium. You can just say, I'll just write one simple thing here, right? A very simple thing. Group number, this is group number 2. Okay? Group number 2 has more as compared to group number 13, right? And group number 13 has more as compared to group number, wait a minute, this is group number 15 now. Group number 15 has more ionization enthalpy as compared to group number 16. That's why group number 15, they have more as compared to group number 16 here. That is oxygen, sulfur, selenium. Right? Group number 2, beryllium, magnesium, calcium, they have more as compared to group number 13, that is boron, aluminium, gallium. Tell me, is that thing clear to all of you? Okay, done. So this is quite important. Now let's see ionization energy of 3D series. If I talk about, right, this is ionization energy. This we'll talk about later also in D block also we'll talk about this. If you talk about 3D series, now remember that IE of 3D series is equal to IE of 4D series, and 4D series is less as this I'll teach you in D block only why it is so. Till now you just see that this is the order. Okay, this I'll teach you in 3D series as well. When we'll talk about that now, I'll teach you that there. Now let's talk about electron gain enthalpy. If you ask me, ma'am, is this order important? I will not say yes. Okay, the order that are important that I am telling you, but I have written because this is a very complicated order. You will see neon, then beryllium, then nitrogen, then boron, then lithium, then carbon, oxygen. There is a very weird order this is, and they have not asked this order, but still I have written it here for you. If you want to do it, you can do it, but this is not important, right? Okay, I'll only teach you important orders. This is not important, right? Okay, electron affinity, as you can see this over here. Wait a minute. Here the order is again the same thing that I have told you. It's quite a weird order. This one you can remember, that electron affinity of lithium is greater than beryllium, then beryllium is less than both lithium and boron, right? Magnesium is less than both sodium and aluminium. Can you tell me why? Why? Because this group number 2, it has fully filled. This is S2. So it does not want to gain any electron. That is why it is less than both lithium and boron. Magnesium is less than sodium and aluminium. right? And if you see in this case, the same thing that I told you, this neon, beryllium, nitrogen, boron, lithium, carbon, oxygen, fluorine, you can learn this one. Okay, this one you can learn, but this is a very difficult order to be learned, but I would not advise you to learn this one, right? Okay, low voice ma'am. अच्छा, okay, ठीक है, चलो. Now let's see. Third period has more affinity than second period. If I talk about third period, they have more affinity as compared to the second period, right? The reason is because smaller size and extra electron repulsions in the third period, right? If you talk about the third period now, if you talk about the third period, what you have in third period, this is the third period. 1, 2 and 3, this is the third period, because here there are extra electrons. That is why it has more electron affinity as compared to second period, right? Okay, then what you have, this is all from DNF block. Okay, so sorry, DNF block, I am saying this is all from periodic classification. I am not marking things important here because this I have just written for those students who want to do every exception. But wherever I mark this important, okay, just remember, wherever I mark this important, these stars, wherever I mark that, you can't skip. Now this one is a very repeated order, you can't skip this. Okay, others are parallel only, right? These are not repeated, but this one, or this order is quite repeated. This order is quite repeated, but I'll do this in D block, right? I'll do this in D block, right? Okay, now see, then you have second period, right? This is the electron affinity of second period. This is for the third period. You can do this, but it's not that important, right? Now come here. Electron negativity is important, right? You must know which is highly electronegative. Fluorine with the 4 electronegative is highest, right? What you do, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, then start with 1, 1.52, 2.53, 3.54. Okay, nitrogen and chlorine have 3, carbon, iodine and sulfur has 3.5, hydrogen and phosphorus has 2. Okay, right? If you don't want to remember all of this, just remember that. Okay, that fluorine has maximum of 4 electronegativity. Now is the major task that we are going to start. Okay, S block is not in your syllabus, but this much you can do. Okay, that is atomic radius for group number 1 and group number 2, right? It will increase down the group. Lithium, sodium, potassium, rubidium, cesium, francium, it will decrease down the group. There is no exception. Decreases down the group, there is no exception in that. No exception is there. No exception. Sometimes they ask you without exception as well, so don't create exception where there is no exception. Okay, in S block you don't have any exception, but now we will start with the major task is now started, that is group number 13. From here, right, the question, right, now I'll give you marks and you'll have to catch it. Okay, till now the 1, 2 orders were important. Acidity, that part was important. Oxides part was important till now. But now we are going to see the very, very important trends that they directly ask you in the exam. Directly they ask you these trends in the exam. Okay, let's see that. Are you all ready for that? Right? Okay. So now what you have, group number 13, that is boron, aluminium, gallium, indium, thallium, right? So there was one very nice mnemonic, then one of the students only told me, that is bag it. Bag it. Okay? Boron, aluminium, gallium, indium, thallium. Okay, bag it. Okay, just that way you can remember this. Now let's see, this is the chart from your NCERT, and from this whole chart I have picked up, because NCERT data, according to NCERT data only I will teach you, not from any other book. Okay, so From NCERT data, first thing is atomic number, so you don't have to remember. Achha, one more thing, you must remember the electronic configurations here. Can you tell me what is the electronic configurations of this one? It should be baguette, right? Now electronic configuration will be NS2NP1. And you know what is the lower oxidation state? Lower oxidation state. Lower oxidation state is going to be always only the NP electrons, and higher oxidation state. Higher oxidation states will be NS plus NP. NS plus NP electron. So lower oxidation state here is +2, +1. Higher oxidation state is +3 here. And always remember that lower oxidation state decreases stability. Lower oxidation state stability increases down the group. Increases down the group. And higher oxidation state stability decreases down the group. This will be valid, this what I have written here will be valid throughout every single group. Okay, every single group this thing will be valid. Like lower oxidation state, you have NP electrons, that is +1, right? And higher oxidation state you have +3. Now if you see, thallium is more stable in +3 or +1, right? Where it will be more stable? Tell me, where it will be more stable? Thallium will be stable where? It will be stable more in thallium lower oxidation state, it will be stable in +1 state, right? Boron will be more stable in +3 oxidation state as compared to +1, right? So that you must remember. Bangan, aloo, gajar in thela, whatever you want to remember, you can remember for the mnemonic, right? Okay, so electronic configurations we have seen here. Atomic radius and ionization enthalpy for group number 13 is the most important order. You can't skip it. It has been repeated again and again and again and again. So here you have atomic radius. It is very important. I'll tell you what exactly is the exception. It should be bal gaye Indian te. Okay. But here you can see the exception. Where you can see the exception? I'll just mark the exception with red pen. Okay. This is the exception that you can see. Can you tell me the reason behind that? Reason is always same. Due to poor shielding effect of 3D orbitals, right? Because in gallium, what you have, this is boron, this is aluminium, this is gallium. Before gallium, you have 3D electrons. And that is the reason suddenly its size will increase, its size will decrease. Why its size will decrease? Because of poor shielding effect of 3D, right? Similarly, you will have this ionization enthalpy order. That is a very weird order. So that's why I'll write it here. How do you remember that? Mark this W. Wait a minute. Okay. This is the W, right? Bal, gaye, or bag it, right? Okay. This is what you will write here. Now maximum is boron, then you have thallium, then you have gallium, then you have aluminium, then you have indium. That's it. That's how you learn this, right? Okay. Tell me. Understood? Tell me. Okay, that's how you remember this, right? So these two orders are highly important. You can't afford to skip this. Like very high chances, one of you, or you know, at least in 1-2 shifts, so you will definitely see this, right? Very important, very highly repeated order this is. Then electronegativity has a very simple order. You have boron, then you have thallium, then indium, then gallium, then aluminium, right? Okay. So boron has maximum, then aluminium, gallium, indium, thallium will be like this. Okay, so what you write? Boron, then write aluminium, gallium, indium, thallium, and write it in the decreasing order, and that's how you will get your order of electronegativity. Oxidation state, two oxidation states are there, lower and higher oxidation state. Which one is more stable down the group? Lower oxidation state is stable down the group. +1. Always in all the cases, lower oxidation state will be stable down the group. Right? Metallic character always increases down the group in any way. Right? It will increase down the group. Melting point, if you see, this is boron, aluminium, then you have thallium, then you have indium, then you have gallium. Can you see gallium has exceptionally low? It is so low, it melts in our palm. It melts in our palm, in the palm of the hands. In the hands only this will start melting. It is so low, right? So that's why this is very important. These all orders are there here, right? So boron, aluminium, thallium, indium, gallium, that is the order, right? So what you have here, it is supposed to be Bal, Gai, Indian, Te. And what just happened here, right? Thallium will switch here and gallium will switch here. This is what just happened. Okay, that's how you should remember these things. But always remember gallium has the least one. Then boiling point decreases down the group, density increases down the group. That does not have any exception here, right? Reactivity with air, let's see that. What are the important points of chemical reactivity? Reacts with air to form oxides and nitrides. Crystalline boron is unreactive. Amorphous boron is very reactive. It reacts. Aluminium, it forms an oxide layer, and that's how aluminium is protected. Aluminium forms oxide layer and does not further react, right? When acids and alkalis, what you will see, boron does not react. Aluminium reacts with both acids, means aluminium is amphoteric in nature. Aluminium is passive with concentrated nitric acid. Why? Because it forms a concentrated nitric acid is an oxidizing agent. It forms an oxide layer. That is why it is inert with nitric acid, right? Then this is important. Reacts with halogen to form trihalides, except triiodide of thallium. So what you will see, TLI3 does not exist only, right? TLI3, they can ask you one thing, which of the following does not exist? So you will write TLI3 does not. And whatever I am writing here now, these are important, whatever I am especially writing. TLI3 does not exist, right? This one is very important, that boron oxides are acidic, aluminium and gallium are amphoteric, indium and thallium are basic in nature, because down the group metallic character increases, so basic character also increases. Now let's see some of the important lines of NCERT, right? Okay, shall we see this? Yes. P block, this is P block. Okay, we are doing P block. So let's see this. Gallium with unusually low melting point could exist in liquid state during summer. It's high boiling point. Now gallium is that kind of element that has very low melting point that you can melt it in your palms, right? It is so low, right? And it has very high boiling point, and that is the reason it is useful material for measuring high temperature, right? So that is very important. It has very low melting point, but it has very high boiling point. So it is useful material for measuring high temperature, because it will not it will melt, but it will not boil. That's why it can be used for measuring high temperatures, right? Then very important, this question also they have asked you so many times, why boron form only covalent compounds? Why boron forms covalent compound? Very important. Due to small size of boron, the sum of, very important, first three ionization enthalpy is very high, right? So that is why when it's first three, see, for ionic compound it will have to lose 3 electrons. For covalent it just have to share. So it is very difficult for boron to lose the 3 electrons, to give up on 3 electrons. It's very difficult for boron. And that is the only reason that it forms covalent compounds, very important. Its sum of first 3 ionization enthalpy is so high that it will not be able to give up on those electrons, and that is the reason it shares the electron. It does not lose the electron, right? Okay, very important. Then some reactions here, let's see. Reactivity towards air, as such you don't have to remember any reaction. I'll tell you what all you have to remember here. Okay, this all I have taught you there as well. So this also I have taught you only. Okay, this we can delete. Okay, this I have taught you in table only. This table now, in the table form I have taught you this here. Okay, I have taught you this here. So you don't, I have taught acidic basic oxides also I have taught you here. Right? Okay. Now you have the nature of these oxides varies down the group. Boron trioxide is acidic, reacts with basic oxides forming metal borates, right? That means the nature of oxides varies down. Boron trioxide is acidic and reacts with basic oxides forming metal borates. Just remember, boron is an acidic oxide. Aluminium and gallium are amphoteric. Indium and thallium are basic in their properties. This also, beta, we have done it in that table itself, right? So as such, it's not required, right? Okay. Group number 14. What is group number 14? Beta, what all I am telling you, you can't skip that, okay? I am doing very selected things from P block because it's a very big chapter, but only the exceptional trends and all they will ask you, and some important lines that I am telling you, right? So group number 14 is Kasi Gai Sant Prabhu, right? Whatsoever you can remember this. Here the electronic configuration is Ns2Np2. Lower oxidation state is going to be +2. Higher oxidation state is going to be +4, right? Okay. So down the group, what will happen? Down the group, the higher oxidation state will exist. That means Pb 4 2 positive is more stable as compared to Pb 4 positive. Why so? Because lower oxidation state is more stable down the group, right? Okay, that is a very important question, right? That Pb2 positive is more stable. That is why Pb4 positive, no, Pb4 positive, that is the reason Pb4 positive, it wants to get converted to +4 to +2, and that is why oxidation number decreases. That is why it itself get reduced, and that is why this is a very good oxidizing agent. Pb4 positive is a very good oxidizing agent. Okay, this is one of the questions. This is your PYQ only that I am writing here, right? If you talk about Sn, which one is more stable? Inert pair only. Very good. Now here in tin, 2 positive, tin 4 positive is more stable. That is why what happens from tin 4 positive, if you have tin 2 positive, it will get converted to tin 4 positive. Here oxidation number will increase. So it is a very good reducing agent because it itself is getting oxidized. So it is a very good reducing agent. See, when oxidation number increases, it is oxidation. So if itself it is under oxidation, it will reduce someone else. So it is doing reduction. So that means it is a good reducing agent. Got it? So these are two important questions that you have, right? Okay, these are very two important questions. Sn2 positive is a good reducing agent. Pb4 positive is a good oxidizing agent. It wants to get converted to Pb2 positive. It wants to get converted to Pb4 positive, right? Okay. Next is this table directly from your NCERT that you have. Based on this table, I'll give you some important trends here, right? Here atomic radii, you will not see any trend. Kasi, Gai, Sant, Prabhu, there is no exception. But in ionization enthalpy, this also is important. They will ask you, right? Instead of Sant, Prabhu, instead of tin and lead, you have lead and then you have tin, right? So again, it is because of poor shielding effect of, see, reason is same everywhere. Reason will be same everywhere, right? Okay, yes, done. Then electronegativity, this is a very important question asked in already in your JEE. They have asked one question here. Now, you know, wait a minute. silicon, germanium and tin, they all have 1.9. So what exactly is the order? Maximum is carbon, then you have lead, then all of them will be same. So what you have? Carbon, then lead, this is 2 point something, this is 1.9, these all are 1.8, right? So in your Google or any other book whatsoever is written, in your NCRT this is written, so we will take this as correct. Okay, then oxidation state +2 +4, but +2 oxidation state is more stable down the group, as I have told you. Metallic character also increases down the group. Then melting point, if you see, it decreases up to 10, then it starts increasing, as you can see this over here, up to 10. Melting point will decrease up to 10. Wait a minute. Up to 10 it is decreasing, then it is increasing from here, right? Okay, so you can say lead is more as compared to tin, right? That's why ionization enthalpy and melting point will have the same order, right? This is also the order of, this order is also of melting point. Okay, this order is also of melting point, they will have the same order, right? It will decrease up to 10, then it will increase, right? Okay, done. Then what you have, boiling point, it to decreases only. Density, how you will do it? Density, firstly carbon, silicon, germanium, then it will be lead, and then it will be tin, right? If you see the density order here, right? Density order here, wait a minute, density. Acha, one more thing na, here they have given you density. If you see this over here, this is the density I think they have given for graphite, right? Because graphite is a more thermodynamically stable state, so they have, I think, given the density of graphite here, right? So then it is decreasing, then it is increasing, then it is increasing, it is increasing. So what we can see over here, ठीक है? Wait a minute, density is increasing only na, so it will be increasing only, right? Wait a minute, density is decreasing, then it is increasing, so it will be silicon, carbon, germanium, tin and then lead. Firstly it is decreasing, then it is increasing, right? Okay, right? So this now, wait a minute, this according to the NCRT data I am writing here, right? Because they have not given you for carbon, they have given you for this. So it is carbon, then it is decreasing. So I will write maximum for silicon, then you have carbon, this. Wait a minute. Increasing. Okay, this is how you will write it. Then catenation, carbon has maximum. Now in catenation, na, that is self-linking property. Carbon has maximum, then you have silicon, then germanium and tin has almost same, and Pb has no tendency of the catenation here, right? Pb does not have any tendency of catenation. Then guys, let's see the reactivity with air. Reacts with air to form monoxides and dioxides. Only tin reacts with steam. Rest all do not react with water in any form. This is a very important line, that only tin will react with steam. Rest all of them will not react at all. Reactivity with halogens is that reacts with halogen to form dihalides and tetrahalides. And some hydrides also will talk about this here. See, here if you talk about the property of catenation, that is carbon, silicon, germanium and tin almost have same. Due to property of catenation and p-pi bond formation, carbon is able to show allotropic form like diamond, graphite, Buckminster fullerene. All these are the allotropes of carbon. Okay, I would advise you just go through them once. Graphite has free electrons. This also you have done in lower classes as well. Just go through them once, right? Then Pb has no tendency of catenation. If you see down the group what is happening, their bond enthalpy is decreasing. That means this bond is very strong, then the bond enthalpy is decreasing. The bond enthalpy, if I say bond enthalpy is decreasing, right, that means the strength of the bond is also decreasing. Bond strength is also decreasing, right? That means the bond length is increasing here, right? These are the things that you must know. Then let's see this. These are 3-4 lines from your NCERT. They are very important lines from NCERT, right? Let's focus on these important lines. So what you have here, the central metal atom in these halides undergo sp3 hybridization and the molecule is tetrahedral in shape. Exceptions are this. Now, usually they are covalent in shape. The tetrahalides are covalent, but SNF4, very important, SNF4 and PbF4, they are ionic in nature, that you must know. Okay. Pb, very important question. PbI4 does not exist. This is a very important assertion reasoning question, that PbI4 does not exist. Now the question is, ma'am, why PbI4 does not exist? Let's talk about that. Because PbI bond initially formed during the reaction does not release. The first PbI bond that you have does not release enough energy to excite. So basically what happens here now, you have NS2 NP2, right? This is the case. Now you want to form 4 bonds. So this is S and this is P. What should happen? They all should have 1-1-1-1 bond, right? Now all are half filled. What should happen with all of them? There should be 1-1 bond. So as soon as the first bond is made, right, it should release the energy to unpair this. So basically what is happening here, earlier you have CS2 6P2 6S2 6P2, it is as it is, and here P is unpaired. Let's say P is unpaired. Okay? It is making the first bond. First bond is made with I. But now it should release enough energy so that this electron can also jump here and it can form 4 bonds. But it does not really release enough energy to unpair the 6s2 electrons, and that is the reason, right? This does not exist only. Excite one of the higher orbitals to have 4 unpaired electrons around lead atom, which does not exist, and that is the reason. And that is the reason, students, that is the reason we can say that PbI4 does not exist. It's a very important question, right? Okay, very important assertion reasoning question that is. Then you have reactivity towards oxygen. If you talk about oxygen, here you should remember that which one is acidic, which one is not acidic. CaO2 only exists at higher temperature. Oxides of higher oxidation state of elements are generally acidic, right? Okay. Then those with lower oxidation state, right? So higher oxidation state are generally acidic. We know that acidity and oxidation state are directly proportional. This particular point till here is very important, from here to here, right? These all lines, because they are telling you which one is amphoteric, basic, neutral, very important. CO2, SiO2, GeO2 are acidic, SnO2, PbO2 are amphoteric. CO is neutral, GeO is acidic, and SnO and PbO is amphoteric. This is very important, right? The acidic nature of oxides, right? Okay, understood? Chalo. Now let's see over here. Achha, this is so radius as a simple order it is. That if you talk about, it is simple only, there is no abnormality here. But what you will see now, what you will see, there is considerable increase in covalent radius from this to this, from silicon to lead. A small increase is there. That means carbon to silicon, there is very high increase, again because of the same thing, because of inert pair effect, it is the same situation. Due to presence of completely filled DNF orbital in heavier elements, poor shielding effect, this happens, right? This is very large increase, this is very small increase. This is what they want to tell here, right? Then ionization enthalpy, as I told you, the order is this, right? Now, since the sum of first 4 ionization enthalpy is very high, plus 4 oxidation state are generally covalent in nature. We are saying plus 4 oxidation state will be just like in boron, plus 3 oxidation state is covalent. Here plus 4 oxidation state will be covalent in nature, right? Okay. Then you have group number 15, right? Okay. Let's see group number 15. Yes, everybody? Chemical properties, so I am not teaching you only. Okay? I am just teaching you some important lines. Okay? That formulas, compounds and all, I am not even touching that, right? Oxides, you must know. If you see, na, very selectively I have written that what you should do and what you should not do. Very selectively I am doing that. Very selectively, right? That this does not exist. Very selective thing, right? They ask you these questions, right? Okay, I know that these things are very tough for you, to do yourself, that what to remember and what not to remember. So this whole next 1.5 hour, I'm going to tell you that what you should remember, right? Remembering part is yours only, but I have selected few things for you. Some lines I have specially taken out from NCRT for you. These are all the NCRT charts and NCRT lines, right? This is group number 15, as you can see the chart over here, right? First thing is, in the atomic radii, if you see arsenic to bismuth, only a small increase in covalent radius is observed. So what you will see in case of atomic radius, what is there, where it is atomic radius, here it is, right? You will see it is increasing, it is increasing, it is increasing, but here a large increase you will have, here also a large increase you will have, but here you have a very small increase. For arsenic to bismuth, you have a very small increase. Otherwise, it is increasing only. So you can say it increases down the group. It increases only, but after some time, very small increase is there. Reason is lengthenoid contraction, inert pair effect, same reason everywhere. Electronegativity, again, this is the order, nitrogen, phosphorus, then you have arsenic, then antimony, and then you have bismuth, right? Melting point will be, it increases for nitrogen to arsenic, then decreases from bismuth, oh, sorry, antimony. If you see, this is the melting point, this is the melting point. If you see the melting point here, it is increasing, then from arsenic it starts decreasing and decreasing, right? Okay, so what you have here, firstly it increases till arsenic and then it starts decreasing till bismuth, right? Okay, done. Then boiling point increases from top to bottom, density increases up to arsenic. Density is what? This is density, right? This is density. Density will increases up to, this is increasing up to, wait a minute, 5. This is only increasing only, na? Right? Wait a minute. What is written here? Decreases from, after that it is decreasing, then there is no tension. Okay? Chalo. Now let's see this, because here now these this density at all, this is not important here. I'll tell you what is important here. These are not so much asked, so that's why I'm not giving that much importance here. -3 oxidation state, if you see, it's -3. See, otherwise if you see group number 15, what is group number 15? Group number 15 is nitrogen, phosphorus. Group number 15 is what? Group number 15 is what? Tell me. Group number 15 is na PSE sharab bhai, right? Nitrogen, phosphorus, arsenic, then you have antimony and bismuth, right? In this case, the general electronic configuration is this thing, right? Lower oxidation state is +3, higher oxidation state is +5, right? But ma'am, how come ±3 oxidation state is there? Because of its electron negativity, it also can gain 3 electrons, and down the group electron activity is decreasing. That is the reason its -3 oxidation state stability is also decreasing down the group, right? Then you talk about physical properties here, right? All the elements of this group are polyatomic. Dinitrogen is diatomic gas, while other are solids. The boiling point increases here, melting point increases up to arsenic, then it decreases up to bismuth, right? This is important, melting point, right? Metallic character increases, except nitrogen. All atoms will show allotropy. Nitrogen will not show allotropy. That is also an important thing. Except nitrogen, all will show allotropy. Now, from hydrides, they ask you the question, okay? Mark it, very, very important. From hydrides of from hydrides of nitrogen is what they ask you the questions, okay? Right? Okay? Yes. Tell me. Revising inorganic parts for previous, more than enough, right? See, now always remember one thing. I'll just tell you one thing here, right? That is, this thing you must remember. I'll be just writing this thing here. If you talk about the acidity, okay, stability that decreases or increases, that decreases down the group, okay, that decreases down the group. And remember that stability down the group, it is less stable, okay. Down the group, what is happening? The size of nitrogen phosphorus, the size is increasing, bond length is increasing, right? Bond length is increasing means it is difficult to break it, it is difficult to dissociate it. So what is happening down the group? I'll just write one order here. Stability and acidity, they are inversely proportional, or reducing power is inversely proportional, okay? Basicity is directly proportional. See, down the group, the size is increasing. That is why its bond length is increasing. That is why its stability is decreasing, because bond length increases, na? So it is difficult to break the bond. So stability is less there. And if you can break the bond easily, you can give H positive easily. That means down the group acidity is increasing, right? So if acidity increases, basicity will decrease. Down the group, because bond length is increasing, so bond dissociation enthalpy, bond enthalpy will also decrease, right? Okay, because stability, it is less, down the group, it is length is high, so that is why it is easy to break it. Stability is less, bond dissociation enthalpy is less. Okay, this is all what you have to remember, right? Okay, just remember this part. Now see what I am going to do here. Very simple. Thermal stability decreases. Reducing character is inversely proportional to that. Acidic character is directly proportional to stability. If this is decreasing, this is also decreasing. Acidity will increase as I have written there. Okay, just remember this thing. Okay, you don't have to remember order of acidity, reducing power, basicity, or bond enthalpy. That you can answer easily. But the order of boiling point you must know. Okay, this is a very important order of boiling point. Now, as you can see, nitrogen in NH3, you have hydrogen bonding. So what should happen here? Down the group, the boiling point should increase, right? But what happened? That means NH3 should have least hydrogen, least boiling point. but because of the hydrogen bonding, its boiling point will increase, and this will be there on the third position here, right? Okay, because of the hydrogen bonding, right? Okay, tell me, is that clear? Oh, OMG. I think it's like my PPT is like, I'm done with you. My board is like, I'm done with you, ma'am. Now please go and let students sleep. Koi baat nahi. We are just left with very few things, right? Okay. This block chemistry, though, you will not even know. We will just complete it within 1 hour, right? By 11:30, you will be free. Okay, so it's not like there is too much to understand. Most of it is cramming only, but cramming with logic is there, and you should know, what not to do, right? So basicity decreases, all of this I have already written. Why NH3 has because of this it has higher melting and boiling point than pH3, that we have already written. Okay, understood? Then what you have here next is reactivity towards oxygen. Now it forms E2O3 and E2O oxides are there. Acidity, we know that. Oxides of this nitrogen phosphorus. Now this is important. Nitrogen and phosphorus, E2 oxides are purely acidic. Arsenic and antimony are amorphous. And those of bismuth are predominantly basic. That's it. This is what you have to do from this paragraph. Then ionic radii, if you see, that we have done already, that arsenic to bismuth, only a small increase in covalent observed. This is due to presence of completely filled DNF orbitals, right? This though we have done, right? Then there is this thing, ionization enthalpy. This is very important. Group 14 much greater than group 14 due to extra stability of this NS2NP3. This is highly stable. That is why it is very difficult to take out electrons from group number 15. So it is higher than group number 14. Allotropy, except nitrogen, all the elements will show allotropy, right? Oxidation states. Now this is something important. Okay, just see this. This is a paragraph of your NCRT. Just see this thing here. Okay, what we are going to do now. Just see this thing. In the cases of nitrogen, all oxidation state from +1 to +4 tend to disproportionate. Okay, disproportionate means they will go into lower or higher oxidation state, right? For example, I'll give you just one example here. For example, this is x minus 4 is equals to -1, that is +5. Is it? X minus 4 is equals to -1. It is +3. Okay, it is x minus 6 is equals to -1, that is disproportioning into +5, and this is +2. So it is increase in oxidation state and decrease in oxidation state is disproportionation. So +1, +2, +3, +4, all of them will disproportionate. That is a quality of nitrogen, right? In case of phosphorus, we say all intermediate oxidation state disproportionate into +5 and -3, both in alkali and acidic medium. Intermediate, they will also disproportionate, but here it is fixed that they will disproportionate into +5 and -3 only. However, +3 oxidation state in case of arsenic, bismuth, antimony becomes increasingly stable with respect to disproportionation. What we are saying here, +3 is getting disproportionated. Here phosphorus also, it will get disproportionate to +5 and -3. But in case of arsenic, antimony and bismuth, no disproportionation will be there. +3 is a very stable oxidation state, then there will be no disproportionation, right? Okay. Because beta dekho, two oxidation state, +3 and +5 you have. Down the group, the stability of lower oxidation state increases. So arsenic, antimony and bismuth, lower oxidation state means +3 oxidation state is stable, right? Got it? Yes, everybody, tell me. Then you have Very important line, very, very important. Mark it, very, very important. Your PYQ, very important. NN bond is weaker than single PP bond. Why nitrogen-nitrogen bond is weaker? Because nitrogen has a very small size and it carries one lone pair. Because of this lone pair repulsions, its bond is weaker. NN bond is weaker than single PP because of high interelectronic repulsions of non-bonding electrons owing to the small bond length. Right? Okay. Then reactivity towards halogen, all the trihalides of these elements except for those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable. Okay, only NF3. Trihalides of these except of those of nitrogen are stable. Okay, all trihalides. And in case of nitrogen, no other trihalide is stable. NF3 is stable. Okay, understood? And this was your exact. Achha, one more thing here. This is where I want to teach you Drago's rule. Okay, this is where I want to teach you Drago's rule. So I'll just take it from here. This is the Drago's rule. Drago's rule, I'll drag it here, right? I'll just drag the Drago's. Oh, little bit fast, bhai. इतना time नहीं है. नहीं है. We are very busy people. Board is super slow. My board is so tired at this point. My board wants to sleep, right? So if you see this over here, right, other things so we have seen like we have seen melting point, bond association, boiling point. We have seen all these orders, right? Okay, melting point and boiling point order, now you do it from here only. I'll just write it here, melting point and boiling point order as well, you do it from here only. Like the melting point order, if you see, it is maximum in case of NH3, right? Okay, then you have SPH3, right? Then you have ASH3, then you have PH3. Okay, so it is supposed to be very low, but it is on the highest point here, right? Similarly here, what is supposed to happen? Firstly, so you are thinking that you will have PH3, phosphorus, arsenic, then you will have antimony, but what happens in between? You have nitrogen. So it is this boiling point order, so you have written before as well. PH3, then you have ASH3, then nitrogen will be in between, right? Okay, it is increasing. It is increasing. ASH3, then you have NH3, then you have this SPH3, then you have BiH3. Okay, now can you see the bond angle here, right? Every element group number, every first element is very anomalous, they shows anomalous behavior, right? First element in every group will not be able to expand its covalency. First element will not have vacant d orbital. Very important lines I am speaking, right? Okay, first element will not be able to expand its covalency. First element is very small. It will not be able to expand its covalency. It does not have vacant d orbitals. Okay, all are these the things that are important, right? Okay, thank you. Right, now see this thing, this is very important. This is the Drago's rule. So basically, can you see this over here, that nitrogen has 107, okay ma'am, but suddenly the angle is decreasing to 90. But ma'am, you only said na, when hybridization is same, when only center metal atom is different, hybridization, lone pair, everything is same, then bond angle is directly proportional to electronegativity of central metal. Yes, I only said. Ma'am, then electronegativity is decreasing down the group. Ma'am, so angle is also decreasing. Then what's the need of Drago's rule? Drago's rule says that yes, electronegativity is decreasing. So bond angle should also decrease. But why so much high decrease in bond angle? From 107 to directly 93. Then the decrease is very small. Why so? Why so? This is because this is applied to, like the first this is applied to, you can say, if you talk about nitrogen, phosphorus, right? In this case, what you will see, the lone pair of nitrogen that you will have, I am directly telling you, this will be sp3 hybridized. Other lone pairs will not be sp3 hybridized, they will be pure orbitals. This is sp3 hybridized lone pair, that is why it will have angle near to 109. They are pure orbitals, that is why they have 90-degree angle approximately, and this is what is Drago's rule, right? Okay, right? Characteristics of molecules following Drago's rules are: bond angle is such as molecule approximately 90 degrees, such molecule does not undergo hybridization, pure orbitals overlap to form bonds, right? Okay, understood? Same thing we will do in other groups as well, like you have even in this case na, even in here hydrides, here the lone pairs will be sp3, other lone pairs will be pure, and that is why even in this group number 16 hydrides you will see this kind of bond angle. Okay, thank you beta, thank you. Yes, Shiva Ram, you do CID on me, right? Chalo. Now let's see group number 16. Let's see group number 16. Everybody, let's see group number 16. If you talk about group number 16, right? This is us se te po. Oxygen, sulfur, selenium, beryllium, polonium, right? This is the data that you have, and whole data I have written it over here. Electron gain enthalpy, you will see there is different order of electron gain enthalpy. Usually what should happen, electron gain enthalpy should decrease down the group, because down the group size is increasing. This is a very important order, right? So it should be oxygen, sulfur, selenium, tellurium, polonium. Why oxygen is the minimum electron gain enthalpy? Why oxygen does not want to gain the electron? Why oxygen does not want to gain the electron? Because oxygen has very small size, right? Oxygen very small size. Two lone pairs, electron repulsion will occur. That is why it is like, I don't want to gain more electron, I don't have that much space, so it will not gain the electrons only, right? Okay, so it will not gain the electrons. Ionization enthalpy lower than group number 15 due to fully filled p orbitals. Because see, in group number 15, you have half-filled p orbitals, right? Here, this is ns2 np4. So you can easily take out the electron and make it np3, ns2 np3. And that is why, because after taking out the electron, it is getting converted to a stable oxidation, a stable electronic configuration. That is the reason easily it can give one electron, right? Okay. So -2 oxidation state stability is going to be this. Down the group it is decreasing, right? Then let's talk about the hydrides here. Let's talk about the hydrides. Boiling point and all, so it increases, है ना? Density increases up to arsenic, decreases up to bismuth, right? Then let's see oxidation state. Stability of -2 oxidation state decreases because of decrease in electronegatividity. Tendency, if you see, this is ns2 np4. So higher oxidation state is plus 6 now. Yes. Lower oxidation state will be plus 4, right? So lower oxidation state stability increases down the group. So plus 4 oxidation state increases down the group. Okay, this will increase down the group, right? Due to again inert pair effect, that is the same thing. right? Okay. Acha, thank you, beta. Thank you. Right? It took a lot of hard work. Huh? It took a lot of hard work. Lot of hard work. I would like to thank my my intern as well, right? We know yesterday though we both were talking till like 1 a.m. We were sitting and making your PPT. I was just taking out the snips and attaching it to. She was decorating all these tables and all. She decorated this, right? I was just reading out NCRT and taking out the snips. So it takes a lot of effort. So you have no idea. Yesterday, to it I think I slept at 2 or 3 a.m. because of this PPT, right? Because I knew in the morning I won't be able to do that. Hanji, okay? Welcome the new students here. Acha, now let's see the hydrogen, okay? That I told you, everything will be same. Thermal stability, acidity, basicity, how it increases, decreasing, it will be same as nitrogen, right? So if thermal stability is decreasing down the group, reducing character or acidity will increase down the group. So basicity will also decrease down the group. Bond dissociation enthalpy will also decrease down the group. Okay, that is important, right? Then if you talk about the boiling point should also increase down the group. But what happens? In that case, H2O should have minimum boiling point, but H2O, because of the exceptional hydrogen bonding, it has maximum boiling point. That is very important, right? Okay, right? Then acidic strength, I told you, that will increase down the group, right? Okay, everybody. Now let's see. This is the thing that I want to tell you before going further. Melting point and boiling point order, I'll just write it here, right? See, melting point, if I see this H2O has maximum, then you have same as group number 15, it is same situation, right? Same situation it is. Here it is maximum is H2O, right? Then again you will have H2TE, right? Then you will have H2SC, then you will have H2S, right? So same melting and boiling point order is this, which is same, right? Dissociation enthalpy we have seen. Can you see the bond angle here as well? So can you see this? Can you apply Drago's rule here? Tell me. Can you apply Drago's rule here? Why there is sudden decrease in the bond angle? Why? Because in this case, in oxygen, you have sp3 hybridized orbitals, right? In this case, you have pure orbital overlapping. That is why here you have 90-degree around angle. That is according to Drago's rule, right? Okay. Then guys, next is we have reactivity towards oxygen. So in this case as well, oxygen, you should know ozone and sulfur, they are gases. SO2, selenium dioxide is a solid. Then you must know SO2, very important. You must know that SO2 is reducing while TeO2 is oxidizing agent. Okay, this they can ask you directly. This is important. Then forms this type of oxides. Both type of oxides are acidic in nature. So we just want to say that selenium, sulfur and tellurium, their oxides are acidic in nature, right? Okay. Now electron gain enthalpy, this so I told you why it is why it has least, because of electron repulsions. Here it is going to be least here, right? Then ionization enthalpy also we have discussed why group number 15 has more ionization enthalpy as compared to group number 16, because group number 16 have half-filled extra stability, right? Now this is halogens. Hexafluorides are only stable halides. Then sulfur SF6 is exceptionally stable for the steric reasons. Okay, this you will have to remember that SF6 is exceptionally stable. Okay, it has octahedral geometry. It is exceptionally stable compound. Otherwise, hexafluorides are not stable here. Right? Okay. Chalo. Then you talk about all elements except oxygen form dichlorides and dibromides. These dihalides from sp3 hybridization and tetrahedral structure. This all you can skip. This to you can skip. This you don't need to do. Okay? This you can skip. Right? Then you have group number 17. See in group number 17 what you have. You have fluorine, chlorine, bromine, and iodine, right? Electronic configuration is Ns to Np5. These are halogens, and lower oxidation state is +5. Higher oxidation state will be +7. Okay, most stable oxidation state is -1, right? Okay. This is the order, and here you have 3-4 orders that are very important in halogens that they ask you. Okay, so wherever I am specially writing, in case of group number 16 and 15, hydrides are very important. Okay, in case of group number 16, electron gain enthalpy was very important, right? Now here let's see what are the important orders of this one, right? First thing is you must know about the electron gain enthalpy order, that is this one. Okay, okay. Electron gain enthalpy order. See, ionic radii is simple, only ionization also is simple. In electron gain enthalpy, this minus just tells you that there is release of energy, right? It just tells you that there is release of energy. I'll tell you here only electron gain enthalpy. I have written it here as well. Where it is? Oh, I think here I have written. Yes. Okay. See, atomic radii is simple. Down the group, the size will increase. No exception in that. Electron affinity is very, very important. Electron affinity or electron gain enthalpy, very important. That firstly you will have chlorine, then fluorine, then bromine, then iodine. Matlab, it is supposed to be fluorine, chlorine, bromine. Down the group, what we expect that size is increasing, it should decrease. So it is fluorine, chlorine, bromine, iodine. Why fluorine does not have a good electron gain enthalpy? Because again, the size is very small. It has 3 lone pairs. It cannot accept the electrons. That is why it will jump here, right? Fluorine, fluorine, bromine, iodine, right? Okay. Then acidic strength. What happens down the group, it increases because bond length increases, it is easy to break it. So it's directly you can say this electron, this is very important electron gain enthalpy. Bond dissociation enthalpy is very important, right? Okay, these two order, so you can't afford to skip. Very high chances they will ask you this in the exam, right? So here you have, instead of fluorine, chlorine, bromine, iodine, fluorine will jump to the 3rd position. Again, reason, ma'am, why? Ma'am, fluorine, so ma'am, it has very small size, so it should have a strong bond. Down the group bond should increase, bond length should increase, and it is easy to break it. Ma'am, then bond dissociation enthalpy should be like this: F2, then Cl2, then Br2, then I2. Ma'am, why fluorine is on 3rd position? Because fluorine, again, very small size, electron repulsions will be there, and that is the reason, right? Its bond gets weaker, and that is why it is very easy to break the bond, right? Then thermal stability, as we know, it decreases down the group. Same is the order of acidity, same is the order of reducing power. नहीं, नहीं, same is the order of basicity, Same is the order of basicity. Same is the order of bond dissociation enthalpy. And acidic character, same is the order of reducing power. Okay? Okay? Right, everybody? Ionization enthalpy is same. Electron gain enthalpy, so we have written it here only, that is the same. So all you have to remember is this order is very important. This order is very important. Then you must remember thermal stability and hydride's acidic strength that I have told you. Right? Okay? Now, now let's see this here. Let's see this here. It is here. See, we have not seen the melting and boiling point, so I'm writing it here. Melting point and boiling point. Okay. Melting point, guys, if you see, it will be HI has maximum, then you have HF, then you have HBr, then you have HCl. Right? Boiling point order is, it is HF, then you have HI, then you have HBr, then you have HCl. Okay? So order is same here for melting and boiling point, that you must remember. Rest of it though we have already done. Right? Now let's see few important lines. Right? Let's see that. Non-metallic character decreases down the group. Iodine shows some distinct metallic properties. It shows metallic luster and positive ion like these it forms. Electron gain enthalpy we have done. Why? What is the reason behind that? Physical property, bond dissociation enthalpy also I have told you. Why fluorine has very less bond dissociation enthalpy. You can see the theory part over here. I have taught you that. Right? Okay? Acha. Before ending this group now, this is some important things from your NCRT. Fluorine oxidizes water to, now see, simple thing is that fluorine will oxidize water to O2. Okay, one thing you will just directly write, fluorine will oxidize water to O2. It easily does so. Iodine does the opposite. Iodine, okay. So if you talk about other two, chlorine or bromine, right, they oxidize with water. They get converted to HX and HOX. Okay, that is hydrohalic and hypohalous acid. But I2, what happens? In case of I2, what happens? I negative is getting converted to I2 in presence of oxygen. Okay? So fluorine and iodine shows the opposite thing. Fluorine converts water to oxygen. I negative converts oxygen to water. Again, itself it gets converted to I2. It's an opposite thing. And X2, chlorine and bromine, they form HX and HOX with water. Okay, that's the simple thing. Right? Okay. Then you have this thing. They all react with hydrogen to give hydrogen halides, but affinity decreases from this. Hydrogen halide dissolve in water to form this. Achha, these are all the halides and all that also we have seen. Okay? Chalo. Let's see. Last few thing, and whatever I have told you now, do that much, you're good to go. That much is more than enough. Right? Okay? What to do, ma'am? Beta, I am also, if I am standing here, then you can also stand here. You just have to sit and listen to me, right? Now, this much so you can do, isn't it? This much so you can do. Chalo. Let's complete this. Let's complete this, everybody. Everybody, let's do this. Let's do this, right? So group number 18 you have over here. Now in group number 18, first thing is you should know that its electronic configuration is this. Due to stable electronic configuration, they exhibit very high ionization enthalpy. You can't take out the electron from there. They have positive value of electron gain enthalpy. Positive value means If electron gain enthalpy is positive, that means they never want to gain any electron, right? Okay, so as such order and all you don't have here in this case, right? Just remember electron gain enthalpy. This is the order of electron gain enthalpy: neon, argon, krypton, xenon, radon, and helium. Helium has lowest melting point of any known substance. Remember this, lowest melting point of any known substance. It has unusual properties of diffusing through commonly used laboratory materials such as rubber, glass, and plastics. Right? That is a property of helium. Okay. Now guys, fatafat say, let's see some questions of P block. Let's see some questions of P block, everybody. Right? Let's see the questions of P block, everyone. After that, we are going to start with DNF block. Right? Okay. So the first ionization enthalpy of group 14 is higher than that of corresponding melting point. See, I am thinking that I should give you this for homework. Okay, fatafat se I'll do, right? Okay. So in this case, because my brain also is not in that condition to solve the questions. The first ionization enthalpy of group number 14 is higher than the corresponding of group number 13. Group number 14 is higher than group number 13. First ionization enthalpy, see, group number 14 is Ns2Np2. Group number 13 is Ns2Np1. So if you lose one electron here, and if you lose one electron here, that will be converted to first ionization enthalpy. Here it is very low, right? Okay, this will be still higher, yes, because here it is so low because it is getting converted to a stable electronic configuration, so it easily wants to give up on that electron. So definitely this will have higher ionization enthalpy as compared to this one. Melting and boiling point of group number 13 are in general much higher than those of corresponding group number 14. That is false, right? Group number 13 are in general much higher. There is no relation like that. Okay, so we can say first statement is true, second statement is incorrect. Then there is given below are the pairs of group number 13 elements, show their relation in terms of atomic radius. Identify the element in the incorrect pair and find out this higher ionic radius more than this. Atomic number of the X is what? Okay, so let's see this over here. What they are saying? They are saying that the size order is aluminium is greater than gallium, right? That is written over here, right? That they are saying that in this case, any relations they have given, identify the elements present in the incorrect pair, and in that pair find out the element X that has higher ionic radius than the other one. First you have to pick out the wrong pair here. So we know that aluminium, if you see, has more size as compared to gallium. Other order are same because here it is okay, down the group size is increasing, but here what will happen? This will inverse. This is aluminium, isn't it? This is the size, and here we know this is a pair. This is a pair, that is a wrong pair. So they are saying the pair that find out element X that has higher ionic radii. Now here which one has higher ionic radii? Al has a greater radius as compared to gallium. So aluminium 3 positive and gallium 3 positive. Gallium will have higher radius as compared to that. So answer is going to be which one has higher? That is gallium. So answer is atomic number is 31. Okay. Next question is the correct order of ionic radii of this. Now this one is also very important. This I forgot to tell you, right? Isoelectronic species these are. Now remember that always in case of isoelectronic species, the size is directly proportional to the anion charge inversely to cation. Inversely to cation charge. It is inversely proportional to the charge on the cation. So anion charge has maximum, then N3, then O2 negative, this. So answer will be A is the correct. More is the charge on cation, lesser will be the size. Isoelectronic means which has the same size. Correct order of electron gain enthalpy, we have already done this. Oxygen will have the least. So answer will be A is the correct answer. Next is the electronegativity of the element increases in which order. So you can find the electronegativity. The order will be nitrogen has maximum, then carbon, then phosphorus, then silicon, right? This I told you in the electronegativity itself that you should know. Ionization enthalpy of the elements of group 13 follows what? Ionization enthalpy. From that W, you can solve this answer and you will get your answer, okay? So I'm quickly doing this because I know that much the energy even you don't have. Stability of +1 oxidation state among this. Lower down the group +1 oxidation state stability will increase. So down the group you can see this over here. This is down the group +1 oxidation state, lower oxidation state, stability is going to increase, right? Okay. Now we are left with only D and F block. Tell me. Do you want 5 minutes break? Tell me. Because now that was the question part. Tell me, do you want 5 minutes break? Tell me. Everyone? Carry on if you have energy. It's okay with it, ma'am. 10, ma'am. Please, ma'am. No, ma'am. Acha. Chalo, theek hai. Let's do it. Let's finish this, okay? Let's finish. Energy kya? My to legs have started paining, right? But I'll complete this, right? Thoda sa hi we are left with. As such, so it's not that much. It's not that much. Frankly, I'll tell you, it's not that much. Easily in 1 hour we can complete it. 1 hour is more, I am telling you, because see, we have, it's not like DNF block is, I have taken some snips from your NCRT, but I will be very frank with you, right? DNF block also, I'll tell you what to do, what not to do. I'll teach you few things that are to be understand, that you should understand. But in the end, right, you have to go through block chemistry again. Okay, but I'll teach you what exactly you need to do, and what are the topics that, conceptual topic I'll teach, right? Okay. Chalo, I'll sit for then 5 minutes. Okay. Chalo, wait a minute. Yes. Actually, now that I have just sit now, I think I need rest for 5 minutes. Okay. Chalo. I'll then see you in 5 minutes. Okay. I'll just take a rest. Hello, hello. Okay, so let's start, huh? Let's start with DNF block. Let's start. Acha, tell me, on Saturday I have another marathon of yours. I'm thinking to take, shall I take it at 11 a.m. in the morning or 12 maybe? Shall I start at 12 in the afternoon? Do let me know in the comment section if you will be there or not. You can bunk your schools and come there in the class, because now after this so it gets tiring for me as well. That's what I was thinking na, कि inorganic chemistry so we can complete by starting at 3 p.m. Okay? So just let me know in the comment section what you want. Right? I am to thinking if you will be there na, I'll start. Acha, see now in DNF block what you have, this is the D block. Now in D block, just remember this is the 3D series, this is 4D series, this is 5D series, this is 6D series. In 5D and 6D series, you have the addition of 4F and 5F, and that is why here you have lengthenoid contraction, here you have actinoid contraction, right? Then remember one thing here, that in this case what else you have here, this is also called as first transition series, second transition series, third transition series, and fourth transition series. Now what all you have to remember here is simply one thing, that is the general electronic configuration is n minus 1d 1 to 10 and n is 0 to 2. So where n is 0, that is platinum, that has ns0. Others, this is the exception, that platinum has ns0 electrons, right? Okay, others have either 1 or 2 electrons, right? So fourth period, that is the 3D series, like this is the 3D series, this is 4D series, 5D series, and you have 6D series here. Out of this scandium to zinc is what you have to remember, like thoroughly. Its electronic configuration, everything you must remember here in case of 3D series, right? Okay, right everybody? Now let me just tell you some important exceptions, the 3D, 4D, 5D and 6D series, right? And from here you will start the inner transition series, that is F block. From here you will start F4F, and here you start the actinoids, that is the 5F inner transition series, right? Now the mnemonic to learn 3D series is this one. You can remember it from any other as well. 6D series you don't have to remember. 3D series is must to remember. 4D series also and 5D series also, if you remember, that will be good for you. But 3D series, so you can't even skip. You cannot skip 3D series. If you skip 3D series, you will end up skipping a lot of things. So 3D series you can't skip. 4D and 5D, I would advise you to remember that, because some things are important there as well. Then there comes electronic configuration. So now I'll mark all the exceptional electronic configurations here. First is chromium, that is 4s1 3d5. Copper, that is 4s1 3d10, that is exception. Others have, can you see 0 0, sorry, others have 4s2. This is all 4s 4s2 2 2 2 2. Here also it is 2 2 2 2 2. Here in this case you can see 1, here in this case you can see 1. So that is the different part, right? Okay. Then if you see this here, this has exception. In this case now, over here everywhere you will see the exception. Okay. Over here so you will see everywhere there is the exception, that is 4s1. And here also you have, oh, okay, and here also you have 4s1. But can you see one very important exception here, that has 5s0, that is this one. In this case you have 5f0 and 4d10. So that is a very, very important exception that you have. You must remember this. Baki you can remember NB, MO, TC, RU, RH and AG. They all have 4s1, right? Okay, sorry, 5s1. Then in this you don't need to remember, but because the exceptional cases are very rare here. So platinum you can remember, right? And this AU you can remember. That's it. Rest of it though, it is same only. In fourth series you don't have to remember anything. Okay, you can skip that part. That part you can skip. Here and whatever I have marked now, that you must remember. That one PD you must remember, and this though full all the electronic configurations you must remember. Right? Okay. Now let's see, these are some of the exceptional electronic configurations that I have written here. Like in 3D you have chromium, copper. Here you have new what was that? Oh, चलो कोई ना, ठीक है. Let's see. Then you should remember all the things that I have marked there. I have marked here as well, because they all have, this is 5s1, 5s1. In technetium also, if you see, that is over here. That is also 5s1, this 6. Okay, it is also wrong written here. Wait a minute. This will be 5s1, 4d5. But I don't remember it from here. This page now I am deleting only. Okay? Remember it from this. This is your NCRT snip that I have taken. Right? This is your NCRT direct. So whatever I have marked here, you must remember this. Okay? Whatever I have marked here, remember all those electronic configurations. Right? These are the important electronic configurations that you must remember. Right? Now, this is again a snip of your NCRT. Here they can ask you which of the following does not exhibit any definite structure. So zinc, cadmium and mercury, you will see this over here. Zinc, cadmium, you can see cross over here. Zinc, cadmium and not mercury, manganese. Zinc, cadmium, mercury and manganese. Okay? What do you have? Zinc, cadmium, mercury and manganese. They don't have a specific structure. They don't have specific structure. Don't have specific structure. Okay? That is an important point to remember. Right? Okay? Then from here to this is the electronic configuration of 3D. Okay, now this is the table of your, this whole is the table that you have for 3D elements. This is the table of 3D elements. Okay, this is the table of 3D elements. Here now the trends that are important that I have already written. I'll tell you what are the trends that are important. Okay, let's see the trends that are important. Okay, this you have to learn, that I can't do anything about it, but you have to learn those trends. See, enthalpy of atomization has a very weird trend like this. This is the enthalpy of atomization. The question that they have asked in JEE 2026 was which has maximum enthalpy of atomization, right? And remember, zinc has minimum enthalpy. If you don't want to remember the trend, at least remember which one has maximum and which one has minimum. Okay, this though you must remember, because this is a previous year question. Right, that which one has maximum enthalpy of atomization, right? Then you talk about order of first ionization enthalpy. This is the order of first ionization enthalpy that you have, right? And this is the order of second ionization enthalpy. From both of this, they can ask you the question, right? Okay. Acha, in first ionization enthalpy, the simple thing is you write Saktiv Karman Fi ko ni ku jan, right? Now along the period ionization enthalpy should increase, so it should be like this, right? But here what will happen? In front of V ko ni, the sign will be opposite. That's it. That's it. This is all you have to do, right? That's it. right? So this is all you have to do, and after that trend will be this. The exact trend is this. Then bacha, you have order of density. As such, so they have not asked you this trend, but you know, last year even enthalpy of atomization trend was also new for students, so this trend also you must remember. Okay? Why I have taken inorganic first? Because I know you will take time to remember all of this, but beyond whatever I tell you today, you don't have to do anything else. Okay, whatever I tell you, it is from NCERT main thing only. Okay, so all the important trends we have taken out from here, right? Now see this diagram. From this diagram, what you must know, that the melting point in 3D series is maximum for chromium, in 4D it is maximum at molybdenum, and in 5D it is maximum at tungsten. Maximum melting points, and usually at D5 there should be peak, but manganese being D5 as well, there is decrease. Technetium being D5 as well, there is decrease. That is the exception here. Okay? There is abnormal decrease here that you will see in technetium and manganese, right? That is written in your NCERT. In this paragraph, you will see it is written here that in any of the melting point of these metals rise to maximum at D5 except for anomalous behavior of Mn and Tc and fall regularly as atomic number increases. Okay? So that you must know what we are doing here, right? Okay, right? Then guys, you have order of radii. Okay? This is the order of radii. Firstly, what is happening? Firstly, scandium, titanium, zinc, vanadium, chromium, manganese and iron are equal. Then copper, then cobalt, then nickel, right? This is the 3D series radius, right? Very, very important, right? Okay. Done. After the class, so beta, you go through whatever I have discussed in this P and DNF block now. Go through them again. Go through my notes again, right? So in this case, I'll just make the round of the one that are more stable. In oxidation state, this is +3, +4 is more stable, +5 is more stable, +6 is more stable, +7. Then here you have +2 and +3. Here you have +3. Here you have +2. Here you have +2. Here you have +2. So what we have seen, this is a NCERT line, that till manganese you have higher oxidation state is the most stable. After manganese, lower oxidation states are becoming stable, right? So till manganese, this is a line of NCERT that higher oxidation states are more stable till manganese, right? After that, lower oxidation state are also stable, right? Okay. Okay. Now one important thing I want to write here related to this thing, that is ionization enthalpy. Dekho, always remember guys, if I say you are going into a unstable to a stable oxidation state, to a stable configuration, ionization enthalpy will always be low. If you are going from a stable to unstable electronic configuration, ionization enthalpy will be very high. For example, I'll just give you one example of this ionization enthalpy kind of questions that they ask you. They ask you questions like, you have Mn, it is like ionization, like second ionization enthalpy of Mn to manganese is higher than second ionization enthalpy of iron. Why? Okay, let's see. This is a question. Okay, let's understand it with the help of this question. Second ionization enthalpy of manganese is higher than second ionization enthalpy of iron. Why? Okay, all you don't have to like cram these things. There's nothing to cram here. These are the most doable questions of DNF block. This is one category that I am showing you. whatever element is given to you, you just write the electronic configuration. Manganese is 4s2 3d5. This is iron is 4s2 3d6. Take out first ionization enthalpy IE1, it will give you 4s1 3d5. Second ionization enthalpy, here now we will actually write third ionization enthalpy. Okay? Question I wrote wrong. Third ionization enthalpy you will write. I'll tell you whatever you can write here. With respect to second also what you will write. Dekho, it is going to give you 3d5, right? After this you take out the electron, this will be 3d4. In this case, you take out first ionization enthalpy, it will be 4s1 3d5 3d6. You take out second, it will be 4s0, this is 3d6. You take out third, it will be 3d5. Dekho. See, if I want to write it in the form of second ionization enthalpy, right? Okay. If I want to write it in the terms of second ionization enthalpy, what I will write? This ionization enthalpy is easy. This work is very easy. When the work is easy, ionization enthalpy will be very low, right? When the work is easy, so I can say ionization enthalpy of second of manganese is very low as compared to ionization enthalpy of second of iron. Iron to as such, there is no comparison. Here to you're not getting into a stable oxidation state. So what are all the conclusions that you can draw from here? Let's draw a conclusion of third ionization enthalpy. 3-4 conclusion I'll tell you from here. Here you are taking out the third ionization enthalpy from a very stable, this is a very stable oxidation state, and you are getting converted to an unstable. So here IE will be very high, right? So ionization, third ionization enthalpy of manganese will be very high as compared to here you are getting converted to a stable oxidation state as compared to third ionization enthalpy of iron. That is the first question, kind of question that they can ask you. Then they can ask you that ionization energy, in ionization energy, third of manganese is very high as compared to ionization enthalpy second of manganese. Yes, why so? Because here you are getting converted from stable to unstable. But this particular ionization enthalpy, in this case, the third ionization enthalpy of iron, it is not high or low, right? Because here nothing stable and unstable you are doing, right? Okay, so what you have to remember here is that when you get converted to unstable to stable, and E is low, when stable to unstable, it is very high. Okay, this is one category of question that you must know. Okay, everybody, understood? Now let's talk about electrode potential. It also follows the same sequence. I'll tell you some important lines here from this. See, if you talk about standard electrode potential, first is what you should remember, that copper has unexpectedly, copper has positive electrode potential. Wait a minute, where is that? Okay, we don't have here it is. I'm so sorry. Yes, here it is. Copper has positive electrode potential, right? First thing is this, that copper has positive electrode potential. That's a very weird thing that copper is showing, right? So because of this thing, what exactly happens here? There's a very important line of NCERT. The unique behavior of copper having positive E0 accounts for its inability to liberate H2 from the acid. So when copper is reacted with acid, it does not liberate H2 gas. Why? Because here if this is getting converted to +1 to 0, this is undergoing reduction. So this should undergo oxidation. That means copper, let's say 2 positive should be converted to Oxidation, if this is undergoing reduction, that should undergo oxidation. So that means copper in zero oxidation state should be converted to some Cu2 positive. It is not happening. Copper is not, because here we are saying that its oxidation should be high, right? But if you see the reduction potential means Cu2 positive to Cu is very high, reduction potential is high, then oxidation potential will be low, because oxidation and reduction potentials are opposite to each other. So if its reduction potential is high, its oxidation, always this will happen. Simple thing I am telling you, we are discussing reduction potentials, right? If reduction potential is high, oxidation potential will be low. That means oxidation will not happen easily. That this is oxidation, so that will not happen easily. So that is why this reaction does not take place. Okay, that is the first thing that they can ask you. Only oxidizing agents, they can react with copper. That means easy, this is not possible. The high energy to transform copper to copper 2 positive is not balanced by its hydration enthalpy. Then generate reverse E naught across, it is given to you. This is the general trend. You will see there is decrease in manganese, copper and nickel. You will see this decrease. Let's see why this is decrease, right? Okay. Okay, so you will see it is interesting to note that this point, manganese, nickel and zinc are more negative than expected from the trend, right? See, here they were expected, this is manganese, right? And then there is, wait a minute, nickel and zinc, right? Nickel and zinc is written now. Manganese, nickel and zinc, they have more negative value as expected from the trend. What is the reason? Reason, it will be there. The stability of half-filled d orbital in Mn2 positive, this is d5 configuration, that is very stable, right? See, if you have to convert Mn, we are saying reduction, right? Reduction means 2 positive to Mn. Okay, this is the reduction. We are saying that this is D5. Chalo, let's see this. Manganese to manganese 2 positive. This is 3D5 4s2. This is 4s2 3D5. 4s2 3D5. This is 3D5. Okay. It is getting converted to a stable oxidation state. That means oxidation potential should be high. It is easy. So reduction potential should be low. That is the reason the expected value is lower. Because if this conversion is easy, that means the opposite conversion is difficult. That means if oxidation potential is higher, that means if oxidation is easy, reduction will be tough. Okay? Similarly, you have in case of zinc. In zinc, what you have? Zinc to zinc 2 positive. This is 4s2 3d10 and this is 3d10. So here you can see oxidation potential should be high because it is easy. So reduction potential should be low. That is why the value is very less. Okay? That is the reason the value is very less. Now for nickel, it is different. Whereas, this is I am marking it. Whereas for nickel, nickel is related to the highest negative in hydration enthalpy. If you see, copper and nickel has the maximum hydration enthalpy here. Because of nickel's maximum hydration enthalpy, its E naught value is very negative. Okay, these are very, very important points that you have. Then if you see this over here, in this case, so beta, everything is written about 3 positive to 2 positive. So I'll just give you 1 or 2 things here I can write. Okay, let's talk about the highest value of zinc is due to removal of an electron. The comparatively high value of manganese show which one to take. Let's see manganese and iron. Okay, they are saying that manganese have manganese 2 positive, 2 3 positive. Manganese 2 positive is 3d5 and this is 3d4. So it is very tough. Reduction, this oxidation potential is low because this is not undergoing into a very stable oxidation. It is already stable, it is undergoing into unstable state. So oxidation potential is low because oxidation is not easy. Oxidation potential is low, reduction potential should be high. That's why they have written that high value of manganese. Why reduction potential value is high? Because of this reason. Similarly, you can see it for, let's say, iron or whatsoever you want to see. You want to see for zinc, you can see that. Let's see iron, okay? Fe2 positive to Fe3 positive. This is 3d6 and this is 3d5. So it is getting converted to a stable oxidation state. When it is getting converted, that means oxidation is very good. Oxidation is very good, that means reduction will be very less. Okay? So that's why it has very low value of iron. Reduction potential value is low. Got it now? How do we find that? Tell me. Tell me. Okay, done. Okay, then see this thing here. In this case, chromium, see, in case of fluorides, manganese does not exist in highest oxidation state, chromium exists in highest oxidation state. And here what you will see, in case this is the same thing only, wait a minute, yes. Wait a minute, let me just show you that. In this case, if you see, manganese exists in the highest oxidation state with oxides, because reason also they can ask you. Reason is because with oxides they form multiple bonds, with fluorides they don't form multiple bonds. That is why manganese exists in higher oxidation state in that case. Okay. Acha, now here I'll give you some important points to remember. This also you can do yourself as well. Okay, just go through these slides. This is nothing but this is just the facts that are written here, right? This is important, right? So if we talk about Cu2 positive and 4i, what exactly happens? Cu2 positive, right? When it reacts with I negative, it gets converted to Cu2I2. However, many copper positive compounds are unstable. They dissociate into this thing. But the question is, they ask you that Cu positive is 3d10, then why it wants to get converted to 3d9? Why so? Why Cu positive gets converted to Cu2 positive, right? Why so? That is a question that they ask you, and the answer is here. The stability of Cu2 positive rather than Cu2 positive is due to the much more negative, highest hydration enthalpy of Cu2 positive than this, which more than compensates for the second ionization enthalpy. That means then from Cu you can convert it into Cu2 positive by taking the second ionization enthalpy that is provided by the hydration enthalpy. Okay, right, everybody? Understood? Then this was the ability of oxygen, this is important line, to form multiple bonds to metal, explains its superiority, right? Because oxygen can form multiple bonds, and that is why manganese is existing in the highest oxidation state in terms of oxides, right? Okay, then guys, you have this magnetic moment here. Directly I have told you before as well, when we were doing coordination chemistry, that for 1 it is 1.72, it is 2.83, 3.84, 4.9, 5.9. Directly you can tell the magnetic moment from there, right? Now if you see this over here, directly you can see the magnetic moment. Easy it is, I have already done this in coordination chemistry. For example, you have chromium. This, if you don't know this, then how you will be able to do coordination chemistry? We have already done this. Let's see iron. Iron is 4s2 3d6. You take out 2 electrons, it will be 3d6, and 3d6 means 1 2 3 4 5 6. That means 4 unpaired electrons. So 4 unpaired means 4.9 is the correct answer. Okay, that's how you calculate the magnetic moment here. ठीक है, I'll just solve one question based on that magnetic moment, right? Okay, let's see that. Magnetic moment pair of transition metal ion have the same number of unpaired electrons. See, Ti is 22. First, we write it 4s2, 3d2, right? Ti 3 positive is what? Ti 3 positive is 3d1. So, same number of unpaired electron. Manganese 2 positive will be 3d5. Okay? Titanium 2 positive will be what? 3d2, right? Cobalt 2 positive will be 3d7, right? Iron 3 positive will be 3d5, and chromium 2 positive will be 3d4, right? Vanadium 2 positive will be, vanadium 2 positive will be, this is 3d2, 3d3, 4s2, है ना? 2 positive will be 3d3, ठीक है? Cobalt 2 positive again will be 3d7. Acha, see, you have to find out the number of unpaired electron here. In this case, so you will have 5 unpaired electron. In this case, you will have 2 unpaired electron. Here you will have 1 unpaired electron. In this case, 1, 2, 3, 4, 5, 6, 7. So you will have 3 unpaired electron. Iron, you will have 5 unpaired electron. This you have 4 unpaired electron, 3 unpaired electron, and 3 unpaired electron. So answer, you can see this over here. D is the correct answer, which has 3 unpaired electrons here. Okay, that's how you answer this. Yeah, directly write down the electronic configurations and then solve it the answer. Acha. Now let's see, this is the color that is written in your NCERT. Okay, I know this table is difficult to remember. That's why I have converted this table into this sequence. Okay. Why I have given you this particular table here, why I have made it, why it is important to learn it, because they have given you in one of the previous year questions that vanadium 3 positive is of which color. Okay, last year they asked you a lot of questions on color, so that is why you need to remember the colors here, right? Okay, everybody, chalo. Now let's see one question on this, right? The first transition, this is your question that I was asking you. So they have given you the one has highest enthalpy of atomization, that is vanadium. Now you have vanadium 3 positive. They are saying that one of the equated ion exists in green color. Vanadium 3 positive is green color. है ना? Highest enthalpy of atomization means they are talking about vanadium. Green color means they are talking about vanadium 3 positive. Now they asked you that vanadium 3 positive is what kind of oxide? So that is a basic oxide. So answer is going to be A is the correct answer here. This is again the cramming part that you have. The catalyst and their work, right, written on the next table here, right? Catalyst and their work, catalyst and their work. Okay. Now let's talk about lanthanoids. So guys, lanthanoids, as I have told you, because of the screening, poor shielding effect of 4f orbitals, the lanthanoids, their size decreases. And that is the reason 4d and 5d elements, they will have the similar size. That is the consequence, right? The cause of lanthanoid contraction is poor shielding effect of 4f orbitals, due to which they attract more and they get contracted. Consequence is that because of the atomic radius inversely decrease in atomic radii is there, they are hard to separate because of strong attachment from the outermost electron. Because they are so attracted to the nucleus, they are very hard to separate. It is very difficult to take them out, right? Now this table is very important. Okay, see what you have to learn from this table. Okay, I'll just tell you, you don't have to learn full-fledged. I'll just mark few things, you'll have to learn that. Okay, so like you have F4F0 here, 4F0 here, 4F7 here, 4F7 here, 4F7 here, then 4F14 here, 4F14 here. What are all those things? You have lanthanoid 3 positive. I'm just writing it here, lanthanoid 3 positive. Cerium 4 positive. These electronic configurations should be on your tips. Europium 2 positive. They're all stable electronic configuration. Then you have gadolinium 3 positive. You have dysprosium, terbium. Terbium 4 positive. Then you have ytterbium 2 positive. Then you have lutetium 3 positive. Okay? These are all the electronic configurations that they ask you. Very, very important, right? Okay. See, I have written them there as well, right? Okay. Because of fully filled, half filled and zero electrons in f orbitals, they are stable. Acha, one more thing. Cerium 4 positive exist, but the common oxidation state is cerium 3 positive. Similarly, europium 2 positive exists, but the common oxidation state is europium 3 positive, and that is the reason here it itself wants to undergo oxidation, number decreases, so it itself undergo reduction, so it's a very good oxidizing agent. So cerium 4 positive, this is a very famous question, that it's a very famous oxidizing agent. This undergoes oxidation, so it itself wants to get oxidized, it will reduce someone else, so it is a very good reducing agent. So this is also a very famous question. Okay, it's also quite a famous question that you have. Okay, so the electronic configurations that I have written here now, they should be on your tips. All the electronic configuration that I have written there, right? Okay, then to it's a decrease, it is a regular decrease in the size of lanthanoid ions from lanthanum to lutetium because of the lanthanoid contraction. Great effect increase nuclear, now this greater effect of the increased nuclear charge than the screening effect. Nuclear charge is high because of lanthanoid contraction, it is decreasing it, right? Okay, then this to beta, I have just told you all of this here, that empty and all that, है ना? Which one is strong reducing? This I told you why it is a strong reducing agent, right? These are all the electronic configurations that I just told you, right? Okay, now in the end, let's see KMnO4 and K2Cr2O7, right? Let's see that last part of today, KMnO4 and K2Cr2O7. There are half-filled D shell orbitals which are stable. Yes. Okay. See, potassium permanganate, KMnO4. Firstly, it is made from this pyrolusite ore, right? The reaction process produces manganate, that is this. So what exactly happens? This pyrolusite ore is converted to K2MnO4, that is your manganate. This manganate, that KMnO4, K2MnO4, na? KMnO, ha. This manganate ion, then when you do acidification, this is converted to permanganate ion. This is permanganate ion. This is manganate ion. Okay? This is permanganate ion. This is permanganate ion, that is manganate ion. Okay? So after adding H positive, it is converted to permanganate ion. So what you have? Pyrolusite ore is converted to manganate ion. That manganate ion is converted to permanganate ion. Okay? That is the sequence that you have. Okay? Then I'll give you some reactions that are in your NCRTs firstly, right? Or you can convert manganate ion to permanganate ion by electrolytic oxidation as well, or in the acidic, that's totally your choice, right? Your choice means what whosoever is doing the experiment. Or you can also make permanganate by reacting Mn2 positive with thiosulfate. You will have the formation of manganate here. This is also another, but this is not a very important reaction, but it is written in your NCRT, right? Now manganate and permanganate ion both are tetrahedral in shape. Manganate is green in color, permanganate is purple. Manganate ion because this has Mn6 positive. That is why this has D1, that is paramagnetic. Permanganate is Mn7 positive, that is D0, that is why it is diamagnetic. That is why it is diamagnetic. Okay, right? Done? Acha. Now see next thing. This I told you, magnate 25, why it is permagnetic, why it is diamagnetic, that we have seen. Now see, Achha, this is very important reaction. Decomposition, how permanganate ion decomposes into, that means thermal composition. It's a very famous reaction that permanganate ion decomposes into manganate and MnO2. Okay, when you heat it, it is directly converted to permanganate and MnO2, very famous reaction, right? Okay, then this we have done, that it is converted to its structure is it is isostructural with KClO4. That is also a very important point, that it is has the same structure as KClO4, right? Okay. That is why we keep KMnO4 in dark bottles, right? Okay. Now let's see some one or two questions here. That is, KMnO4 decomposes on heating to form O2 along with what? It decomposes with K2MnO4 and MnO2, right? So answer will be C is the correct answer here. That we have just seen. It decomposes into permanganate decomposes into manganate and MnO2 and O2. Okay, that is a full-fledged reaction. It's a very important reaction. Okay. Now, acha, these reactions now, they are not so important, right? But there are some extra reactions that you have. They are not in your NCRT, so I'll not mark anything here, right? So you just have to do KMnO4 with constant H2SO4. It gives you Mn2O7, Mn2O7, right? Okay, it gives you. And if you talk about KMnO4 with concentrated HCl, it gives you MnCl2. Okay, just remember this, right? Acha, this though we have seen it. Let's see how it is oxidized in acidic medium. What happens? Basic, what happens? In acidic medium, permanganate ion is converted to MnO2. Very important, right? In the basic medium, if you see, in the basic or alkaline medium, it is converted to MnO4 2 negative. Okay, in neutral medium, it is converted to MnO2. Very, very important. In basic medium, what happens? In acidic medium, what happens? Very, very important, right? Then remember one more thing, that it converts I negative to I2 in acidic medium. Rest of them to are same only. Fe2 positive to this to they will, this is not difference. Fe2 positive always get converted to Fe3 positive only, but that is different, because in alkaline medium you have a different thing. Okay, rest of them are the same only. C2O4 is converted to CO2, S2 negative is converted to sulfur. You don't have to remember these reactions, just remember whatever I am marking here. Okay, this is converted to this is converted to this. SO3 2 negative is converted to SO4 2 negative. NO2 negative is converted to NO3. That's it. You already know that in acidic medium, manganate is converted to Mn2 positive. You don't have to balance all these reactions. You know it from the redox reactions now, how to balance it. Then why you are learning these reactions? Okay? Then see this thing, very important. In alkaline medium, I negative is converted to iodate ion. In acidic medium, it was being converted to I2. That is a very important question. Rest of it to beta same. It is S2O3 negative is converted to SO4. Then this reaction here is different. Okay? This reaction is different. This is your NCRT reaction. Permanganate ion on reaction with Mn2 positive, it gives you MnO2. This is also important. Okay? See, all these are your NCERT reactions. I have just formatted them in a different manner, right? Okay. Acha, this is not in your NCERT. This is also not in your NCERT. This is extra that you have. This is not in your NCERT. Okay. This is like some surprising or some difficult question. If they want to ask, they will ask you from here. Like the structure of Mn2O7 is this one. It has 6 Mn double bond O and 1 MnO bond, right? Okay. These are some other reactions, not so important, but you must go through them, right? Mn2O7 give rise to MnO2 and oxygen. Okay? Okay. Acha, how Mn2O7 was formed? Let me just write it here. It was formed here. Wait a minute. Let me just write it here. KMnO4 on reaction with concentrated H2SO4 forms MnO7, Mn2O7. Mn2O7 get converted to MnO2 on heating. Okay? Better notes will be in the description box. Don't worry about them. Right? That too, I'll make sure that I'll provide you that. ठीक है देखो now question तो easy only they ask you total change in oxidation state of manganese involved in the reaction. Potassium iodide in the acidic medium is what? Total change in oxidation state of manganese. देखो in acidic medium this is converted to Mn2 positive. What else yaar? This is +7, this is +2. The change in oxidation state is 5. So answer will be 5 is the correct answer, isn't it? Right? So answer will be change in oxidation state will be 5 is the correct answer. Simple. Okay? Next is JEE 2024 question. See, product A is neutral and acidic medium disproportionate to give product B and C. Okay. Along with water. The sum of spin only magnetic moment of B and C is what? So product A you have with this, it gives you A and this. This is, it is giving you what? This is actually manganate ion, K2MnO4. This is what it is giving you. Now, to give products B and C. A is neutral or acidic medium, disproportionates into B and C. So if I talk about K2MnO4, K2MnO4 disproportionates into manganate and MnO2, right? Now in case of manganate, there is no unpaired electron. This is D0. So no unpaired electron, mu is 0. In this case, Mn4 positive it is. 4 positive means Mn is 4s2 3d5. 4 positive is what? Though it will be 3. That is 3.8. Okay? So it's just a way of asking, it is different. It's a 2024 question. Okay? So we know that this is from the reaction. I know that A is this. After that, I know it will disproportionate to this. Then I just have to find the magnetic moment and take the sum of that, and that will be the answer. Right? Okay? Let's do the last part. Christmas, so I think I'll celebrate with you only today. Right? So, potassium dichromate. Let's see that, everybody. Let's see potassium dichromate. Okay, let's try to finish it before Christmas. Right? So, potassium dichromate. See, it starts from chromite ore, that is this ore. They directly ask you which of the following is chromite ore. That's why formula is also very important. Then chromite ore is converted to potassium, sodium chromate. That is, this is chromate. This is chromate. This is sodium chromate. Okay? Then sodium chromate is converted to sodium dichromate. Then this is converted to potassium dichromate. Okay? Chromite to sodium chromate to sodium dichromate to potassium dichromate. That is the sequence. Now, this is a very highly important thing, that chromate is pH sensitive, right? What do you mean by that? What exactly you will tell? that whenever you have acidic medium, dichromate will exist. In basic medium, chromate will exist. That is why whenever you add acid, it will shift to dichromate. Whenever you add base, it will shift to chromate. So in acidic medium, only dichromate will exist. It will not exist in basic medium. In basic medium, it will be converted to chromate ion, that is Cr2O4. CrO4, 2 negative. Right? Okay. So this is what we have, that in acidic medium you have chromate, in basic medium you have dichromate. Sorry, in acidic medium you have dichromate, in basic medium you have chromate. Very, very important thing, right? Okay. Now next question they can ask you, why you use K2Cr2O7, why not sodium chromate? Why you have to convert sodium chromate to potassium chromate? Because sodium chromate is not used in redox reaction as primary standard, but this is used. Why? Because of KSP values. Sodium chromate is highly soluble, potassium chromate is not soluble. That is the reason. Okay, ठीक है जी. Then also potassium chromate, if you see, है ना, that on heating it gives you, decomposes into this dichromate, gives you chromate and CrO2, right? This reaction, right? Okay. Then see, देखो in basic medium, though we will not even see the reactions. Dichromate in acidic medium gives you Cr3 positive, that is green in color, right? Important. Now all these are like basic medium, so it is converted to chromate ion only. Okay, so basic medium, it is not behaving as an oxidizing agent, it itself is getting converted to chromate. So only in acidic medium you will see the reactions. Its oxidizing nature is I negative to I2, S2 negative to S, SN2 positive to this, Fe2 positive to Fe3 positive. Okay, okay, and these are the other things that it oxidizes, right? Okay. Chalo. Now here na, this is you can just go through this. Wait a minute. There are some 3-4 tough questions here that I have. Now these 3-4 slides are difficult. This you will not find in your NCERT. This all you will not find in your NCERT. This is like apart from NCERT. So just remember that what happens, chromyl chloride test, it is used for the estimation of chloride ion. Chloride ion, when it is reacted with dichromate ion, it forms chromyl chloride. Okay. So more is the chromyl chloride, more will be the chloride ions here. Right? Okay. Understood? Got it? Then you have, this much to depth you don't have to go. Okay, this much depth we don't have to go here, right? That much is fine. Achha, this one you can do that. Dichromate on reaction with H2O2 peroxide, it gives you CrO5 that has a butterfly like structure, and here it is -2, -1, -1, -1, -1 charge, and here it is +6 charge. Okay, it has a butterfly like structure and it has deep blue color, right? Then these are some different reactions apart from your NCERT that you have. You want to do this, you can do this. You can want to skip, you can skip as well. It's for those students who don't want to take any risk. Okay? But if you can take risk, it's not like they will definitely be asked. Very rare chances they have. Okay? But you can do this. Matlab, I want to say this is not in your NCERT. If they want to ask very tough questions, then they will ask you these questions, right? Otherwise, so you can skip this. Okay? All these reactions are for those students who don't want to skip, like even beyond NCERT they want to do. Okay? And one thing, color of KMnO4 and K2Cr2O7 is due to LMCT, that is ligand metal charge transfer. Right? Okay. Acha. I think we have completed. Now we are just left with 3-4 questions here. Fatavat se we'll do that. Consider the following reactions. You have this. The product A and B is what? See, K2Cr2O7, whenever you react this with KOH, it gives you chromate. With the H2S4, it gives you K2Cr2O7 again, right? Okay, so answer will be what they are asking. The products A and B respectively are what? This is what they are asking, so you can directly answer that. Okay, identify the correct statements below. Chromate ion is square planar. Dichromate is generally prepared from chromates. Green manganate ion is diamagnetic. Okay, dark green colored of this green manganate ion is diamagnetic. That is paramagnetic, na? Manganate ion is paramagnetic, so this is also not true. This is true. This is also not true. Dark green colored, this compound is proportional to neutral and acidic medium to give permanganate. It disproportionates, that is also true. With increasing oxidation number of transition, ionic character of oxide decreases. Okay? As oxidation number of metal increases, ionic character of oxides decreases. So you can say these three are the true statements here. Then this is for what I told you just now, chromyl test. Okay? NaCl reacts with H2SO4 and this to give reddish fumes, that will be of chromyl chloride, which reacts with Na to give yellow solution. What is that? That will be chromyl chloride, and it is going to give you Na2Cr2O7. Okay? That is this solution. Cr2O7 I am saying. It will give you chromate ion. Okay? So firstly, NaCl reacts with K2Cr2O7 to give chromyl chloride. Chromyl chloride reacts with base to give chromate. Okay? So answer will be A is the correct answer here. Right? Okay? So that's it. Now I have completed whatever was my task. Now this is your homework question. Which of the following has lowest melting point? Then the next homework question is, which of the following is diamagnetic in nature? And here we have Merry Christmas. What a timing. Merry Christmas, Merry Christmas. I'll just, I'll be your Santa Claus now, right? Okay. So your Santa Claus. Okay. Do I look like a Santa Claus now? Santa Claus is quite tired, guys. Santa Claus is very tired. Oof. Oof. So, hello. What you want, kids? Tell me. Do you want your J score? Or what else you want? Tell me, kids. Everybody. Santa has given you inorganic chemistry in Monday. Santa is completely tired. Santa wants to sleep. Okay? Chalo. Okay. So, oh shit. Yes. Wait a minute. So I'll just do this. I'm just posing for your photo, right? So, yes. Okay? Inorganic. Now, I want you guys to spam the comment section. Even if you have one student has to do 10 comments, do that. Make 100 comments here in the comment section, okay? Because seriously, it took a lot of effort, right, to do this, right? Chalo. Okay. Okay then, bacha. Right? Okay then, bye-bye. Take care. See you all in the next class. And these are your homework questions that I want you to answer. Take the screenshot. Take the screenshot. And answer me too, okay? Answer me. And that's it, guys. And before going, I also have one more thing for you, right? Merry Christmas, Merry Christmas, Merry Christmas, right? Acha, see, what is the important thing that I want you to know? First thing is Sigma J Crash Batch, guys, that is live here. That is just available at 999 rupees. Right here you have high weightage topics right, in just 60 days, right, that we have done already, right, 93 sessions, right, and 85% of the JEE questions from these 93 high weightage topics that are going on in the Sigma batch, that is available just at 999 rupees. You can see this over here. You also have test series along with that. So few lectures will be recorded that we have already done, few lectures will be live that are currently going on, right? Okay, so I am also in that batch and will be waiting for you in the batch. And one more thing, you can click over here, right? When you click over here now, you will get to the portal where you can see the PDFs, right? All the things that you're asking, ma'am, notes and all, that you will get in the ask wait. Click on that. In the description you will see the PDF. Okay, right? Chalo. Okay then guys, now I'm super tired. I'll see you all in the next class, and spam whatever you have the feedback in the comment section. I'll be waiting for your comments. If you don't make it 100 comments, I'll not do organic marathon. Okay, chalo. Okay then guys, bye bye, bye bye everyone.